Electronic-Photonic integrated systems for signal processing. 1. Ultra-broadband photonic signal processor. Abstract. Flexible ultra-broadband optical wavelength conversion will be one of the key issues in future optical networks that make use of the full low attenuation bandwidth of standard single-mode fibers, SSMF. This chapter outlines the authors' work to realize broadband wavelength conversion between extreme optical wavelength bands using optimized multimodal optical waveguides with high cubic nonlinearity. In a first part, the physical principles of ultra-broadband optical wavelength conversion in a highly nonlinear multimodal silicon-on-insulator (SOI) waveguide and methods to model and optimize its functionality are explained. Subsequently, examples of optimized SOI waveguide designs are presented that enable ultra-broadband conversion of signals within or between various low-attenuation wavelength bands of an optical fiber. In a second paragraph, the fabrication of SOI waveguides is delineated in general, and measured key parameters of samples of various generations of optimized waveguides are revealed. In a final section, the performance of the developed optical converters is demonstrated exemplarily in laboratory experiments. Keywords. Acronyms. Amplified spontaneous emission noise. Additive white noise. All-optical wavelength converter. Back-to-back. Bit error rate. Scattering. Chromatic dispersion. Conversion efficiency. Complementary metal oxide semiconductor. Continuous wave. Digital to analog converter. Digital back propagation. Digital signal processing. Dense wavelength division multiplexing. External cavity laser. Erbium-doped fiber amplifier. Electronic-photonic integrated circuit. Free carrier absorption. Finite difference method. Four-wave mixing. Grating coupler. Highly nonlinear fiber. Insertion loss. In-phase and quadrature. Receiver. Mode add-drop multiplexer. Multicore fiber. Multimode fiber. Multimode waveguide. Multiplexer. Nanorib. Optical phase conjugation. Optical phase conjugation based on four-wave mixing. Optical spectrum analyzer. Optical signal-to-noise ratio. Quadrature phase shift keying. Polarization controller. Photodiode. Praseodymium-doped fiber amplifier. Photonic dispersion and loss analyzer. Polarization division multiplexing. Photonic integrated circuit. Phase matching. Quadrature amplitude modulation. Spectral efficiency. Single-mode fiber. Signal-to-noise ratio. Silicon-on-insulator. Self-phase modulation. Stimulated Raman scattering. Standard single-mode fiber. Space division multiplexing. Single polarization. Tapered asymmetric directional coupler. Transverse electric. Two-photon absorption. Tunable optical bandpass filter. Variable optical attenuator. Wavelength division multiplexing. Waveguide. Wavelength conversion. Wavelength selective switch. Crosstalk. Low attenuation infrared wavelength bands of a single-mode fiber 1.1 Introduction. With the availability of mature, low-attenuation optical single-mode fiber, SMF, in the 1980s, all segments of the worldwide communications network have been transformed from copper to optics, leading to a tremendous boost in transmission capacity. Since then, optical communications networks are continuously upgraded to keep pace with the dynamical growth of the worldwide data load. This traffic increase, typically between 25% and 80% per year too, is not expected to saturate in the mid-future. Network operators keep up with this evolution by exploiting so far unused degrees of freedom, e.g., By extensively modulating in-phase and quadrature components of optical carriers up to 1024 quadrature amplitude modulation, QAM3, and by applying capacity-achieving coded modulation schemes with probabilistic shaping 4/5. Currently, the optical C-band, which exhibits minimum signal attenuation, is fully equipped with wavelength division multiplexing WDM optical channels, approaching ultimate Shannon spectral efficiency. Systems that employ the adjacent L-band are being installed, exploiting the lower wavelength regions of the O, E, and S-band Fig. 1.1 is the straightforward option to gain additional transmission capacity. In the long term, space division multiplexing SDM, using either multi-mode fibers MMFs or multi-core fibers MCFs, or a combination of both, are identified as potential solutions to satisfy a further capacity increase in fiber optic communication networks too. Exploiting the full bandwidth of standard single-mode fiber SSMF according to Fig. 1.1 raises the demand for efficient devices that achieve broadband switching of multiples of wavelength channels between wavelength bands to enable full flexibility of these multiband optical networks. Conventional electronics, which is unable to process data over a multi-bandwidth, is not an option in the foreseeable future. However, a promising solution is all-optical wavelength conversion, utilizing the cubic nonlinearity of several optical materials. While single-mode devices exhibit an obstructive bandwidth limit due to the high phase mismatch of the underlying four-wave mixing (FWM) process, it seemed to be possible to achieve higher bandwidths via nonlinear interaction of more than one propagating mode 6. In this chapter, a survey of the authors, work in the framework of the DFG priority SPP 2111, Electronic-Photonic Integrated Systems for Ultrafast Signal Processing, to design, optimize, realize, and evaluate multimodal SOI waveguide structures that enable optical ultrabroadband wavelength conversion between arbitrary low attenuation wavelength bands of silica fibers is given. First, we introduce the mathematical theory of guided optical waveguide modes and the appropriate modeling of linear and nonlinear perturbations that affect their propagation. The underlying multimodal FWM process and applied methods to optimize the waveguide design are outlined. 3 samples of optimized waveguides are numerically evaluated, showing unique properties to convert signal wavelengths between dedicated optical bands. Several generations of optimized waveguides have then been fabricated and characterized. Results are given in a second paragraph. Finally, the performance of selected samples has been evaluated in laboratory experiments. Exemplarily, successful ultra-broadband C2O band conversion and broadband optical phase conjugation (OPC) are presented in this concluding section. 1.2 Mathematical modeling of optical waveguide modes and propagation. 121 Guided modes in SOI waveguides. Refractive index profile of the investigated regular nanorib waveguide with layer stack and rails. Note the different scaling of the axis. Transversal electrical field distribution of the 4 lowest order modes TE0, TE3. Colors encode magnitudes large, red to small, blue. Arrows visualize the direction of light polarization. Dips etched into the waveguide with parameters and transversal electrical field distribution of the 4 lowest order modes TE0, TE3 of a waveguide with 2 dips. Normalized group delay and dispersion of the 4 lower order modes in a regular waveguide, waveguide 1, and a waveguide with 2 dips, waveguide 2. Figure 1.6 shows group delay and dispersion curves of a regular waveguide and a waveguide with 2 dips. Comparing the dispersion curves of the TE3 mode in plot B and D, the effect of the dips is clearly visible, while the TE2 curve does almost not change. In this way, adding dips can be used for fine-tuning the waveguide dispersion and improve phase matching, PM, for selected modes. 122 4-wave mixing. A good nonlinear interaction with M, O, P, QT 3T 1T 2T2. B poor nonlinear interaction with M, O, P, QT 3T 0T 2T2. We discussed earlier that good PM can be only achieved in realistic waveguides if the interacting modes are selected according to 1.23 or 1.24, i.e. if either one mode is selected for all lasers, or if two modes are used in specific arrangements for two lasers, respectively. These selections yield favorable overlap integrals according to Fig. 1.7a, characterized by positive lobes and high integral magnitudes. 1.2.3 optimization of the SOI waveguide design. Signal and idler combinations covered in this project. OES, CL, and U are the low attenuation wavelength bands of optical fibers. Optimization results of our work 6.12. Each scenario defines the nonlinear wavelength conversion process, BS or OPC, followed by source band target band, and whether two-mode operation was enforced 2M, or there was allowed to use either one or two modes. The used modes are aligned in the order P1 S P2. The last column shows the obtained maximum FWM bandwidth BFWM for the respective realization, where the maximum depends on the width of source and target bands, the FWM process, the pump placement, and the enforced signal to pump separation of 5. Scenario modes TX num dips BFWM BS 000110 3000 70 2 400 150 5295 BS SS2222 1500 70 0 200 70 6565 BS CC2222 1500 70 0 200 70 2930 BS LL2222 1500 70 0 200 70 5455 BS CO1221 1500 70 1 300 70 3535 BS CS2222 1500 70 0 200 70 3535 BS CL2222 1500 70 0 200 70 3535 BS 002M0110 3000 70 2 400 150 5295 BS SS 2M1212 2000 70 2 200 150 6165 BS CC 2M2121 1800 70 1 200 150 2930 BS LL 2M2121 1600 70 1 200 120 5355 BS CO 2M1221 1500 70 1 300 70 3535 BS CS 2M2112 1650 100 1 400 70 3535 BS CL 2M2112 2100 100 1 400 70 3535 OPC CC2222 1750 70 2 200 70 3535 OPC CC 2M2112 1800, 100, 1, 400, 70, 1930. Since the production of SOI waveguides was restricted by the etching process, this optimized solution could not be realized, as further boundary conditions had to be observed. We had to fix the SOI height to 220, slab height to 100, and could only optimize the rib width. Furthermore, it was problematic to etch dips. The optimized alternative solution for the BS-CO scenario that has been identified did not require dips, and used TE0 and TE1 modes for the interacting waves in the arrangement 0, 1, 1, 0 according to the definition in Table 1.1. It has a rib width of 1672, and the required slab height of 100 and SOI height of 220. The device likewise shows the classical case of PM and exhibits the full FWM bandwidth of 35. This solution was then produced and characterized. Results are presented in Sect 141. Group delay and dispersion of the realization BS-CO scenario 12. A 4-wave mixing efficiency for BS-CO scenario. B4-wave mixing bandwidth for BS-CO scenario under variations of rib width and slab height of the SOI waveguide 12. Corresponds to line 6 of Table 1.1. It can be seen in Fig. 1.11 that here the TA2 mode has a very low dispersion in the S and C band. Thus, placing all waves in the TA2 mode, PM, and in consequence, full conversion efficiency is achieved over a very wide wavelength range due to the low dispersion, see Fig. 1.12 The sensitivity with respect to deviations of rib width and slab height from their optimum values is likewise low, as can be seen in Fig. 1.12b. Due to these features, this realization is extremely versatile and applicable to various scenarios. In Table 1.1, the applications BS, CL, and OPC, CC likewise make use of the low dispersion of the TE2 mode in the S, C, and L band. Group delay and dispersion of the realization BS, CS scenario 12. A 4-wave mixing efficiency for BS, CS scenario. B4-wave mixing bandwidth for BS, CS scenario under variations of rib width and slab height of the SOI waveguide 12. Corresponds to line 9 of Table 1.1. Here, both pump lasers are placed in the TE1 mode at very short wavelengths. Signal and idler in the S-band use the TE2 mode. When the signal wavelength is varied, the average group delay of the pumps remains constant, as both pump wavelengths are unchanged. Due to the low dispersion of the TI2 modes, see Fig. 1.13, the group delay at the mean signal and idler wavelength is likewise almost constant. 1.31 holds again. However, this process is very sensitive to the placement of the pump wavelengths. The flat yellow region of optimum FWM efficiency in Fig. 1.14 indicates that the wavelength of P2, and likewise that of P1, should be very stable to maintain PM. The process also shows a high sensitivity with respect to variations of rib width and slab height, as this realization requires an exact tuning of the group delay curves, which depend on the waveguide geometry, see Fig. 1.14b. Group delay and dispersion of the realization BS, SS scenario 12. A 4-wave mixing efficiency for BS, SS scenario. B4-wave mixing bandwidth for BS, SS scenario under variations of rib width and slab height of the SOI waveguide 12. 4-wave mixing bandwidth WRT. Dip parameters for BS 12. 124 modeling nonlinear wave propagation in SOI waveguides. Calculating the idler power at the end of the SOI waveguide with 1.26 is an approximation which is well applicable for the optimization of the waveguide design. However, it does not cover several relevant effects. To be able to predict the idler power along the waveguide with high accuracy, we developed a continuous wave CW frequency domain propagation simulation framework, which computes complex amplitudes as the waves propagate along the waveguide. The effects of mode-dependent attenuation, linear mode coupling, and nonlinear coupling are all considered here. 0M0 a 0220 a 0 a 2 DA M1 plus M2 M30 a 020 a CM a 0 MDA NM1 M2 M3 a 0 a X3 M1 M2 M3 DA. The linear coupling coefficient CM accounts for interactions between modes at the same frequency, whereas the nonlinear coefficient NM1 M2 M3 describes mode coupling across all frequency combinations. The third-order susceptibility tensor X3 mediates these nonlinear processes by characterizing the material's response to combinations of interacting optical fields. The computation of X3 in silicon under specific symmetry constraints is summarized in 1516. These coupling mechanisms give rise to a system of coupled differential equations of the form given in 1.38, which must be solved numerically. The efficiency of both linear and nonlinear processes is governed not only by energy conservation and the associated phase mismatches, but also by the spatial overlap of the interacting mode fields. 125 Numerical evaluation. Coupled differential equations to be solved simultaneously. P1, P2, SOPC, BS, TI0, ZP1 TI0, ZP2 TI0, ZAS TI0, ZAOPC TI0, ZABS TI0, TI1, ZP1 TI1, ZP2 TI1, ZAS TI1, ZAOPC TI1, ZIBS TI1, TI2, ZP1 TI2, ZP2 TI2, ZIS TI2, ZAOPC TI2, ZABS TI2. Refractive index geometry of the NR waveguide, indicating slab, SOI, and dip heights, along with rib and dip widths 15. An SOI waveguide is considered, featuring a rib width of 1800, a slab height of 100, a total silicon height of 220, and a propagation length of 2. A single dip structure with a width of 400 and a depth of 70 is included. The waveguide geometry, illustrated in Fig. 1.16, is identical to that described in 12. Simulation parameters, wavelengths and modes of propagating waves with high conversion efficiency, input powers, and mode-dependent attenuation coefficients. The asterisk on IOPC indicates that PM was optimized for the OPC process. Input generated. Input power D. dB. P1. P2. SIOPC IBS. P1. P2. STI0. 1. TI1. 1535. 1519. 1529. 20. 2. TI2. 1524. 1540. 20. 10. 3. A simulated power evolution of pumps, signal, and idlers along the waveguide without linear mode coupling. The mode distribution corresponds to Table 1.3. B. Simulated power evolution of selected waves, including both linear and nonlinear coupling. See vertical zoom on the OPC idler in TA0 mode from B15. 1.3 Design and fabrication of all optical signal processors and their components. Nonlinear optical signal processing in the silicon material system is severely hampered by effects associated with free carriers that are inevitably created due to two-photon absorption, TPA. Free carriers introduce loss and therefore pose a challenge to nonlinear devices using CW light in the and wavelength range. However, by studying free carrier lifetime in Silicon Nano Waveguide 17, we could show early on that pin assisted waveguide structures very effectively suppress free carrier associated loss and therefore permit e.g. much enhanced FWM efficiency in waveguides 18. The here presented work for the first time extends the approach of using pin-assisted silicon waveguides for nonlinear optical signal processing to the domain of waveguides. The substructures of the here studied photonic signal processor were fabricated in IHP's 200 MBCMOS facilities using SG25 PIC or SG25H5 EPIC technology, contrasting with earlier experiments that relied on dedicated technological flows 19. Our photonic integrated circuits have thus been manufactured using a full technology flow, which at the same time served a multi-project wafer client base. The advantage of this approach compared to other techniques that increase nonlinear efficiency is the use of standard SY material, which is fully compatible with additional thermal budgets typically encountered at later stages of device fabrication or integration. In addition, these advanced technologies provide much enhanced system integration perspectives. This chapter will provide a brief overview of the photonic integrated circuits technology platform used for the fabrication of pin-assisted waveguide structures, followed by CW device characterization. 131 Foundry Design. Principal design flow for photonic integrated circuits and electronic-photonic integrated circuits in IHP's silicon photonic technologies. The photonic integrated circuits realized for the present study were mostly designed using the IPKISS framework of photonics. 132 EO Waveguide Platform. Exemplary cross-section of IHP's photonic integrated circuit technology, SG25 PIC. WG waveguide GRC grating coupler, PD photodiode, TM top metal, M metal. 133 components and integration into an all-optical signal processor. Sketch of a typical all-optical wavelength converter, AOWC, with its main components. The waveguide is drawn straight, but can be wrapped into a spiral to reduce the footprint. The design goals for those components can be summarized as follows. Multimode waveguide, MMWG, and benz-optimized dispersion for ultra-broadband operation in different bands. Small effective area for large nonlinear coefficient. Low loss and low linear crosstalk, XD. Optimized dispersion for ultra-broadband operation in different bands. Optimized dispersion for ultra-broadband operation in different bands. Small effective area for large nonlinear coefficient. Small effective area for large nonlinear coefficient. Low loss and low linear crosstalk, XD. Low loss and low linear crosstalk, XD. Pin diode neglectable additional linear loss. Efficient removal of carriers generated by TPA. Neglectable additional linear loss. Neglectable additional linear loss. Efficient removal of carriers generated by TPA. Efficient removal of carriers generated by TPA. Mode add-drop multiplexer, MADM low insertion loss, IL broadband operation, not limiting the overall performance of the devices. Low XD. Low insertion loss, IL. Low insertion loss, IL. Broadband operation, not limiting the overall performance of the devices. Broadband operation, not limiting the overall performance of the devices. Low XD. Low XD. Grating coupler GC low IL across the relevant bands for pump, signal, and idler. Low IL across the relevant bands for pump, signal, and idler. Low IL across the relevant bands for pump, signal, and idler. In the following, design considerations for individual components are discussed. 1331 Multimode Waveguide and Bend Design. The overall PM optimization was extensively discussed in Sect. 1.2. In practical devices, however, the tuning parameters are more limited. Therefore, no dips were used for most devices, and in all but one device, the standard slab thickness 100 was used. In the following paragraph, a MMWG width of 1200 and wavelength of 1550 is assumed, when not stated otherwise. Schematic of the two bend types considered in this work: a circular bends with piecewise constant curvature, which exhibit a mode mismatch at the straight-to-bent interface, both mode fields as green-bounded insets, and bends with piecewise linear curvature. The red dashed lines indicate waveguide center paths, which are the reference for all radii and curvature. Transmission of multimode waveguide MMWG bends with 1-2-0-1 excited by 1550 in the TE1 mode. Arrows indicate worst ratio of IL and XD. The XD of 21.9 dB achieved for the circular bend may seem sufficient, but for a compact design, a large number of bends is required, and the XD may add up coherently to large powers. For example, even a small design with 8 of those circular bends would result in unacceptable 21.9 dB 20 log 10838 dB worst-case XD. The simulated bends, on the other hand, exhibit a high XD of 45.7 dB per bend, which yields enough headroom for larger designs. For actual devices, bends with a 50 and 100 have been used, where the larger radius was used in later devices to further suppress XD. 1332 Design of Mode Add-Drop Multiplexer. Schematic top view of a TADC used to implement mode multiplexing and its relevant dimensions. Effective index for isolated top and coupled bottom, waveguides with 100, 200, and 500 at 1550. Simulated transmission for TE1 MADM designed for 1550 with 200, 1190, and linearly tapered from 480 to 530 in the TADC section. Cross-section and dimensions of MMWG with integrated pin diode. Red, white, and blue shades indicate different levels of P, I, and N doping. 1333 Design of pin diode to suppress free carrier absorption. The usage of a reverse-biased pin diode has been explored only for single-mode waveguides, so far 17. The extension towards multi-mode waveguides is one main contribution of this work. Figure 126 gives an overview of the different doping regions that form the pin diode. The intrinsic region is introduced, where the optical mode is guided to prevent additional linear optical losses in the doped regions. Moderately doped P and N regions are added next to the intrinsic region. These have lower optical losses than the heavily doped N+ and P+ regions next to the contacts. There is a clear trade-off between better electrical performance, faster carrier removal at lower voltages, and better optical performance, lower linear losses, which can be optimized in the design phase. When the geometry parameters and are already used to optimize the FWM phase matching, and HSOI and the doping levels are given by the PIC Electronic-Photonic Integrated Circuits EPIC process, only the separation between waveguide edge and doping region can be optimized during design stage. The widths of the P and N doping regions had virtually no influence on the diode performance, as long as it is large enough such that the high doping regions do not overlap with the mode. Steady-state solution of reverse-biased pin diode under optical excitation. Electrical IV characteristic of an MMWG with 17-01-025 excited by 100 MW red and 500 MW blue in the TE0 mode. The current shows a typical diode behavior. Above about 1 V, the forward current starts to increase exponentially, which is accompanied by carrier injection and very high optical loss. With large negative bias, the diode will break down with a breakdown voltage that depends on the injected optical power. In between is the desired operation region, where current is almost constant with voltage and carriers are efficiently removed at saturation speed. Optical losses of the TE0 mode at 1550 in a reverse-biased diode MMWG with 17 and 100 under different bias conditions. Optical excitation is by 100 MW at 1310 in TE0 and 100 MW at 1550 in TE1. 134 Summary of fabricated devices. Summary of fabricated devices, their design parameters and measured performance. Design, characterization, gen, width features, length FWM process, mode, GC's center wavelength. Worst dip for 11.7 dB. Lost dB. I1190. 7.1, 11.7, 22.3. C to L wavelength conversion, WLC. TI0. 15 50. 2.6. 0.8. TI1. 15 50. 6.9. 2.5. TI2. 15 50. 21.1. 7. TI0. 15 50. 1.7. 0.8. TI1. 15 50. 5.5. 1.8. I1850. 7.1, 11.7, 22.3. C to L WLC. AI2. 15 50. 5.2. 1.8. II1672. 7.1, 11.7. C to O WLC. TI0. 1310. 3.2. 0.9. TI1. 15 50. 13.8. 1.8. TI0. 1310. 2.7. 0.9. II. 1698. 7.1, 11.7. C to O WLC. TI1. 15 50. 16.9. 1.8. II. 1722. 7.1, 11.7. C to O WLC. TI0. 1310. 3.8. 0.9. TI1. 15 50. 15.8. 1.8. TI0. 1310. High. II. 1640 with dips, larger bends. 27.1. C to O WLC. TI1. 15 50. High. II. 1850 larger bends. 38.1. C to O WLC. TI0. 1310. High. TI1. 15 50. High. TI0. 1310. High. II. 1800 with dips, larger bends. 7.2, 16.9, 27.3, 38.3. C to O WLC. TI1. 15 50. High. IV. 1800 with dips, larger bends. 15.9. C to C OPC. TI1. 15 50. High. TI2. 15 50. High. TI1. 15 20. 1. IV. 1700 straight 150. 12.1. C to L WLC. AI2. 1580. 1. 1. IV. 1700 straight 150. 10.7. C to S WLC. TI1. 1490. 1. 2. AI2. 1520. 1.5. 4. IV1750 straight. 8.3. C to S OPC. AI2. 1520. 1, 4, V1700, 72 larger bends. 30, multipurpose SCLTI2, 15 50, 35, 2. The devices marked with an asterisk are further investigated in system experiments in SECT. 1.4. For devices with dips, the loss was too high to perform further characterizations. In generations IV and V, no separate MADM test structures have been implemented. Therefore, losses are only estimated by assuming a 1 dB loss of each MADM. 135 Component characterization. Particularly in the first device generation, several test structures have been implemented to characterize performance of individual components. After fabrication of each iteration, those structures have been characterized to improve the following designs. 1351 Mode Add-Drop Multiplexer. Measured IL and XD for first-generation device with 2 back-to-back MADMs, only showing 2 dominant XD contributors. All traces are normalized to the TE0, TA0 case to cancel effects of GCs. 1352 Multimode Waveguide Dispersion and Loss. Group index simulations, solid and measurements dots of the first 3 2-guided modes for a first and B second generation devices. Black dashed lines indicate phase matching. Measured IL and XD spectra for a 1190 mmWg with 11.7 length, only showing 2 strongest XD contributors. All transmissions are normalized to back-to-back GC response. Second-generation MMWGs designed for C to O band conversion. Measured transmission of 11.7 long devices normalized to TE0 TE0 back-to-back responses for TE0 left and TE1 right. Measured transmission of fourth-generation devices with lengths of a 12.1, B 10.7, and C 8.3 as described in Table 1.4. 1.4 Performance evaluation of SOI waveguides for ultra-broadband all-optical wavelength converters and optical phase conjugation. In this section, we present the experimental verification and system-level evaluation of silicon-photonic chips designed for ultra-broadband wavelength conversion and optical phase conjugation, OPC. Building upon the theoretical principles, dispersion engineering, and design methodologies outlined in the previous chapters, we focus on the key performance metrics, the experimental setup used for testing, and the interpretation of results in both linear and nonlinear regimes. The objective is to validate the chip performance under real-world signal conditions and assess its suitability for deployment in long-haul and high-capacity optical networks. The PICs were characterized using a temperature-stabilized coupling stage maintained at a constant temperature by a temperature controller to ensure stable operating conditions. Since all the PICs under test used GCs for light coupling, the PICs were connected using 2 cleaved SSMFs, which could be adjusted for arbitrary coupling angles at the PIC input and output. 2 6-axis manual positioning stages were employed to achieve efficient coupling, providing full control over both linear X, Y, Z, and spherical R coordinates. For the characterization and system measurements, the input and output coupling angles were matched and tuned to achieve symmetric transmission around the desired center wavelength. As the PICs discussed in this chapter all utilize GCs, which are inherently polarization dependent. A polarization controller, PC, was placed before the input to adjust the state of polarization and ensure optimal alignment with the grating coupler's acceptance profile. As it was discussed in SECT 135, linear characterization, including insertion loss and bandwidth, was performed to establish a baseline reference. With the linear properties characterized, we proceeded to the nonlinear evaluation of the PICs to gain insights into the behavior and limitations of the FWM process under varying optical power levels. Nonlinear characterization was carried out using a CW optical signal and pump, both polarized to match the TE mode of the waveguide. They were combined using a WDM or a 3 dB coupler. The combined output, containing both signal and pump, was coupled into the PIC via grating coupler. The idler generated through the FWM process was then measured at the output using an optical spectrum analyzer, OSA. By sweeping the input signal power, the FWM efficiency and idler generation could be evaluated. The signal CE was defined as the ratio of the idler power at the waveguide output to the signal power at the waveguide input, as shown in 1.25. These nonlinear measurements help to define the optimal operating conditions for the PICs and establish a robust foundation for system-level integration and performance optimization. After completing both linear and nonlinear characterizations, we advance to the system-level experiments. In this phase, a data signal was generated at the transmitter and received by the receiver. To establish a reference for the optical signal-to-noise ratio (OSNR) penalty introduced by the transmission system, a noise loading stage was implemented. In this setup, the bit error rate (BER) was recorded at various OSNR levels and compared against the theoretical BER curve derived from the additive white noise (AWGN) model. With the OSNR penalty characterized, full system measurements were conducted using high data rate signals, either in single-channel or WDM configurations, employing advanced modulation formats. In the following sections, we discuss the nonlinear characterization results, as well as full system measurements performed on two devices, a multimode SOI waveguide designed for ultrabroadband CO wavelength conversion, and a multimode SOI straight waveguide designed for ultrabroadband COPC. 141 multimode SOI waveguide for ultra-broadband CO wavelength conversion. 1411 experimental setup. The PIC employed for ultra-broadband CO wavelength conversion in this section was designed as described in Sect. 123. Figure 135 illustrates the setup used for the following measurements 26. It consists of the transmitter, the AOWC stage, the transmission stage, and finally a receiver, KK. The transmitter was used to generate a 32G bead single polarization, SB, quadrature phase shift keying, QPSK signal. In the AOWC, this signal was combined with pump 2. This combination was sent to the TE1 input of the PIC, while pump 1 was connected to TE0. The pumps are amplified by an erbium-doped fiber amplifier, EDFA praseodymium-doped fiber amplifier, PDFA, power-controlled by a variable optical attenuator, VOA, and filtered by a tunable optical bandpass filter, TOBPF. The PIC was temperature-controlled and reverse-biased with 20V. The output coupling angle was optimized for flat CE. Then, pump and signal polarization, as well as the fiber-to-chip coupling, were optimized for high CE. From the TE0 output, the converted signal idler is either sent through a noise loading stage or over a 100 SSMF link. Experimental setup for CO conversion, including transmitter stage brown box, AOWC stage red box, noise loading or optional transmission stage blue box, and KK stage, including optical spectrum at PD input as inset yellow box 26. 1412 experimental results. For the following experiments, the input powers at the PIC were measured to be 11.3 D for the signal, 24 D for pump 1, and 19.3 D for pump 2. Starting from simulated optimum values, the pump wavelengths were iteratively adjusted to maximize both bandwidth and CE. Eventually, pump wavelengths of 1540 and 1300 were selected for pump 1 and pump 2, respectively, facilitating broadband operation with a 240 wavelength shift, a range rarely demonstrated in prior experimental work. Experimental results of the AOWC, pumped by 24D at 1540 and 19.3D at 1300, measured CWCE for signals in the C-band. B spectrum at the PIC input and output. CBER of 32 SB-QPSK signals, received after noise loading stage, and D after 100 SSMF using different launch powers for a signal at 1548. E-constellation diagrams after the transmitter I, after the AOWC, and after transmission over 100 SSMF, 26. CO band conversion experiments were then conducted using data signals at 1542, 1548, and 1562, with a back-to-back B2B reference measurement at 1548. In the B2B scenario, the transmitter was directly connected to the noise loading stage, and the ECL, PDFA, and TOBPF in the KK were replaced by C-band equivalents. Results are shown in Fig. 1.36c, which indicates an OSNR penalty of less than 0.4 dB at the hard decision forward error correction HDFEC threshold compared to the B2B case. For consistency, OSNR values were corrected to a 12.5 G noise bandwidth. In the 1548 case, the noise loading setup was replaced by a 100 SSMF transmission link with 35 dB IL. A VOA was used to adjust the launch powers of the converted signals. The resulting BER performance is shown in Fig. 1.36d, demonstrating that a launch power of only -11.5 D is sufficient to remain below the HDFEC threshold after 100. According to Fig. 1.36b, Pump 1 still exhibited considerable power at the AOWC output. Despite a TOBPF suppressing this pump by approximately 30 dB, it remained dominant at the input of the following PDFA, thus constraining the allowable launch power of the converted signal. Future implementations are expected to incorporate on-chip pump filtering to address this. Figure 136E presents the received constellations after the transmitter, after the AOWC, and after 100 of transmission, all recorded at the highest achievable OSNR. No significant degradation is observed after the AOWC stage, suggesting compatibility with higher order modulation formats. These results collectively demonstrate that the integrated AOWC, capable of translating the full C-band into the O-band, operates effectively using intermodal FWM in a PIN diode-assisted MMWG. A CE of -41 dB was achieved under moderate pump powers. Across all evaluated wavelengths, the AOWC introduced an OSNR penalty below 0.4 dB, and its performance was validated by successful transmission over 100 of SSMF for a single channel. Leveraging a PIC platform also enabled the on-chip integration of MADM, offering a scalable, compact, and cost-efficient solution that would be impractical with conventional fiber-based architectures. 142 Multimode SOI Straight Waveguide for Ultra-Broadband C Optical Phase Conjugation. In this section, we present the use of a multimode SOI straight waveguide as a nonlinear medium to perform OPC. This device is specifically used as a mid-link element in a real optical fiber communication system to mitigate the signal data's nonlinearity and chromatic dispersion, improving the data quality after approximately 300 of SSMF transmission. Schematic design of an OPC setup over a 300 SSMF link. Figure 137 shows the schematic setup used for the midlink OPC measurements in this work. It consists of a transmitter, 352.8 spans of SSMF forming the first half of the link, the OPC device, another 352.8 SSMF spans forming the second half of the link, and a digital coherent receiver. The transmitter was used to generate the desired data signals. As shown in Fig. 1.37, each fiber span is preceded by an EDFA and a VOA. The signal was first launched into the EDFA, which was operated at its optimal gain to minimize noise figure and maximize the SNR. The VOA was then used to control the launch power into the fiber spans. To monitor the signal throughout the setup, 20 dB optical splitters were placed after the EDFAs and VOAs. The main output branch, carrying 99% of the power, transmitted the signal into the fiber link, while the 1% branch was directed to an OSA for monitoring purposes. 143 Nonlinear Characterization. Experimental OPC setup used for characterization of the OPC chip. In a first step, the nonlinear characterization of the chip was performed using the setup shown in Fig. 1.38. A CW signal at 1543.87 and a pump at 1547.4, both polarized to match the TE2 mode of the waveguide, were combined using a WDM. In contrast to the theory in SECT. 1.2, only one pump is implemented, i.e. P1 Pi2 P in the OPC scenario. This results in an idler generation according to IP plus PS. The maximum used pump power was at plus 25D at the PIC to avoid damaging the GCs. The combined output from the WDM, containing both signal and pump, was coupled into the PIC via grating coupler. To mitigate the effects of TPA and reduce free carrier accumulation, a reverse bias voltage of 10V was applied across the integrated pin diode. As shown in Fig. 1.4d, the idler generated through the FWM process is observed at 1550.95 in the OSA output. The input signal power was swept from 6D to plus 18D to evaluate the FWM efficiency, and the idler generation, while the pump wavelength was fixed at 1547.4 with a power of plus 25D. As expected, the idler power increased linearly with signal power at lower input levels, indicating effective FWM interaction, see Fig. 1.4b. However, at higher signal powers, a saturation in the idler power was observed. This saturation can be attributed to several factors. Despite the reverse bias, residual TPA still generates free carriers, and at high optical intensities, the sweep out of these carriers becomes less efficient, leading to increased FCA. Additionally, thermal effects and pump depletion may also contribute to this behavior by altering the PM conditions and reducing the available pump energy, respectively. These effects could limit the FWM CE28. The efficiency of signal conversion can be ultimately defined by the idler power at the waveguide output over the signal power at the waveguide input C. 1.25. Figure 140C presents the idler power CE as a function of the input signal power. In this experiment, the signal wavelength was set to 1543.87, while the pump was fixed at 1547.4 with a power of plus 25D. The CE remains relatively constant, about 39 dB, for a broad range of signal powers. However, at higher input signal powers, a noticeable linear decrease in CE is observed. This decline at elevated signal powers is consistent with the saturation behavior discussed earlier. To summarize, the nonlinear characterization of the OPC device provided key insights into the behavior and limitations of the FWM process under varying optical power levels. It was found that, to prevent damage to the GCs, the pump power should be limited to a maximum of plus 25D. Similarly, to avoid degradation in CA due to nonlinear distortion or saturation, the signal power should not exceed plus 16D. Experimental setup used for OPC system measurements over a 300 SSMF link. 144 system experiment results. A calculated loss of a single grating coupler based on B2B reference measurements. B measured idler power as a function of input signal power, and C resulting efficiency of the FWM process. D measured optical spectrum of the pump, signal, and generated idler wavelengths, demonstrating successful FWM in the OPC device. EBR performance versus OSNR for a 32 JBead SB16 QAM signal in a B2B configuration. Results are shown for both a single-channel case with and without OPC, 1543.87, pink circles and blue squares, and a 3-channel WDM setup with 100G spacing blue triangles. The dashed line represents the theoretical BER curve based on the AWGN model. FBER versus launch power for a 300 link with a 32 GBead SB16 QAM signal in a single-channel configuration. Results are shown for the case with and without the OPC stage. In the final experiment, the OPC stage was incorporated into the middle of a 300 SSMF transmission link, as illustrated schematically in Fig. 1.37 and in more details in Fig. 1.39. Figure 140F shows the BER performance as a function of launch power, ranging from 4D to plus 8D. This measurement was performed under two conditions, with and without the OPC stage. Without OPC, the CD of the link has to be compensated in the signal processing unit of the coherent receiver. With OPC, Psi-D is inherently compensated by the link itself. At launch powers below 0D, the system operates in the linear regime, and increasing the power improves BAR. However, at higher launch powers, nonlinear effects become significant, leading to BAR degradation. With the OPC stage, we observe an improvement in BAR by 1 to 2 orders of magnitudes in the nonlinear regime. This clearly demonstrates the OPC's effectiveness in mitigating both nonlinear distortion and chromatic dispersion. To conclude, the results from system-level measurements provide clear evidence that the multimode waveguide structure, enabling OPC, can mitigate the adverse effects of nonlinearities and dispersion in transmitted optical signals. However, one notable challenge identified during the experiment was the significant loss of 10 dB, see Fig. 1.4, caused by the GC used for signal coupling into and out of the waveguide. This loss and the loss of the waveguide itself contribute to a considerable reduction in the OSNR, which limits the overall performance of the system. Despite this, the measurements serve as proof of concept for OPC using multimodal SOI waveguides, showing its potential for improving signal quality and enabling advanced optical processing techniques. The promising results indicate that the core design is solid, but further optimization is required to overcome the challenges posed by the coupling losses. Future work will focus on addressing these limitations by exploring the use of other high nonlinearity materials for the waveguide core, which could further enhance the performance of the system. Additionally, investigating edge coupling techniques holds potential for significantly improving the OSNR and minimizing losses, making it a promising avenue for future development. Overall, this work lays the foundation for continued research into optimizing multimode silicon waveguides for enhanced optical communication systems, opening new opportunities for ultra-broadband signal processing. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1NTYURCIGL 2022, Ultra-Broadband Optical Wavelength Conversion Using Nonlinear Multimodal Optical Waveguides. In 2022 13th International Symposium on Communication Systems, Networks and Digital Signal Processing, CSNDSP. IEII 832-835. 2 PJ-DT 2017, From Scaling Disparities to Integrated Parallelism, a decathlon for a decade. J. Technol 35-510-991115. 3R KM Going R SU-X, J 2017, Constellation-Shaped 66 Transceiver with 400 Transmission over Standard. In 2017 European Conference on Optical Communication, ECOC. IIIA 13. 4TGAN 2015, Coded Modulation with Probabilistic Shaping for Optical Fiber Systems. In Optical Fiber Communication Conference. Publishing Group 2A23. 5JXSGR L Burrows E.A.S. Pan-Wyal 2017, Transatlantic Field Trial Using Shape 64 at High Spectral Efficiencies and Single Carrier Real-Time 250S16. In Optical Fiber Communication Conference. Publishing Group 5B3. 6KT 2023, Numerical Optimization of Ultra-Broadband Wavelength Conversion in Nonlinear Optical Waveguides. D. Thesis. 7KT 2001, Introduction to Optical Waveguide Analysis, Solving Maxwell's Equation and the Equation. New York. 8 Leakes Murphy T. 2008, Vector Finite Difference for Anisotropic Dielectric Waveguides. J. Technol 26, 11 1423 1431. 9GP 2012, Fiber Optic Communication Systems. New York. 10GP 2000, Nonlinear Fiber Optics. In Nonlinear Science at the Dawn of the 21st Century. Springer 195-211. 11G RS-BJ HRKYN 2018, Investigation of Intermodal Four-Wave Mixing for Nonlinear Signal Processing in Few-Mode Fibers. IEEE Photonics Technol 3017 1527 1530. 12TYN 2020, Dimensional Optimization of Phase Matching in Silicon Nanorib Waveguides. In 21st ITG Symposium Photonic Networks. VDI 18. 13 RJ MA R AH RW AR Sun YX Lingle R 2013, Experimental Investigation of Intermodal Four-Wave Mixing in Few-Mode Fibers. IEEE Photonics Technol 25-6 539 542. 14R N Datap J X X IW E Green W YA 2009, Engineering Nonlinearities in Nanoscale Optical Systems, Physics and Applications in Dispersion-Engineered Silicon Wires. Adv Opt Photonics 11162-235. 15 UT N 2022, Analysis of Material Susceptibility in Silicon on Insulator Waveguides with Combined Simulation of Four-Wave Mixing and Linear Mode Coupling. Opt Quant Electron 5412-837. 16 UT N 2021, Modeling Material Susceptibility in Silicon for Four-Wave Mixing Based Nonlinear Optics. In 2021 International Conference on Numerical Simulation of Optoelectronic Devices, NUSOD. IAIA 121-122. 17A LJB K 2011 Design Rules for PIN Diode Carriers Sweeping in Nanorib Waveguides on SOI. OptExpress 1999-159922. 18A LMG HRTCB K 2012 Highly Efficient CW Parametric Conversion at 1550 in SOI waveguides by Reverse Biased PIN Junction. OptExpress 21-3-100-13107. 19HGA-KB L 2012 Fabrication of Low-Loss SOI Nanowaveguides including BEOL processes for nonlinear applications. J. OpSoc, Rapid Pubble 712032. 20L DJB Null D, S Guards FYY Read GT, H Port H 2013, Integrated 10-sec Silicon Modulator with Driver in 0.25 C by CMOS. In Proceedings of 39th European Conference and Exhibition on Optical Communication ACOC 13. 21S Null D C L 2019, Advanced Photonic BiCMOS Technology with High-Performance Photo Detectors. In OED Optical Sensing, Imaging and Photon Counting, From X-rays to T 2019-11088. International Society for Optics and Photonics, SBIE P110880M22C, OMC 2016, Adiabatic Bends in Silicon Waveguides. In 2016 IEEE 13th International Conference on Group IV Photonics, GFP, 108109. 23 Dingwai Su J, FD, BOH, C, 2013, On-Chip Two-Mode Division Multiplexing using Tapered Directional Coupler-Based Mode Multiplexer. OptExpress 21-10376-10382. 24JA 2022, A Semiconductor Device Simulator. J. Open Source 773898. 25TGULN 2021, Numerical Optimization and Measurements of Waveguides for Ultra-Broadband C2O band conversion. In 2021 European Conference on Optical Communication, ECOC. IEIA 14. 26GITUCCNLRK 2021, Efficient Ultra-Broadband C2O band converter based on multi-mode silicon-on-insulator waveguides. In 2021 European Conference on Optical Communication, ECOC. IEIA 14. 27 IRCAL 2018, Practical Trade-offs for Reception. In 19th ITG Symposium Photonic Networks. 28 AK MM NM AJ DJ 2000 transmission in L-band. IEEE Photonics Technol 1215701572. The notation indicates the analytic signal, IA. The complex valued representation of the real physical field containing only positive frequency components. 2. Optic-electronic-optic interferometers for arbitrary digital signal processing. Abstract. This chapter presents the development and experimental validation of an optic-electronic-optic (OEO) interferometer supporting flexible coherent add-drop operations. The system leverages coherent detection, real-time digital signal processing, and in-phase quadrature IQ electro-optic within one interferometer arm to enable programmable manipulation of the optical field. We demonstrate successful add-drop operation of a quadrature phase shift keying QPSK signal and quantify system performance under various conditions. In addition to single-channel demonstrations, we present new experimental results using detection in a dense wavelength division multiplexing WDM scenario, showing scalability to multi-carrier systems. Long-term operational stability is ensured by continuous phase tracking implemented in the digital signal processing DSP chain. These results highlight the potential of the OEO architecture for future coherent optical networks requiring dynamic channel control, integrated processing, and signal. 2 generations of indium phosphide in P-based integrated OEO interferometer PICs are introduced to improve phase and polarization stability. As a preliminary step, a partially integrated OEO interferometer PIC is developed and assembled into a module. Finally, a fully integrated OEO interferometer PIC is presented, incorporating all optical components required for the OEO interferometer setup. Acronyms: Analog to digital converter, amplified spontaneous emission, additive white noise, bit-error ratio, digital to analog converter, digital phase locked loop, digital signal processing, external cavity laser, erbium-doped fiber amplifier, electro-optic, equalizer, extinction ratio, electrical spectrum analyzer, finite impulse response, integrated coherent receiver, in-phase quadrature, local oscillator, lookup table, moving average, multiple input, multiple output, Mach interferometer, Mach modulator, numerically controlled oscillator, optical bandpass, optical delay line, optic-electronic-optic, offset quadrature amplitude modulation, optical spectrum analyzer, optical signal-to-noise ratio, polarization controller, photonic integrated circuits, quadrature phase shift keying, sampled grating distributed reflector, single-mode fiber, transimpedance amplifier, traveling wave electrode, variable optical attenuator, wavelength division multiplexing. 2.1 Introduction. In recent years, advancements in coherent optical transceivers have been driven by the development of high-speed digital-to-analog converters, DACs, analog-to-digital converters, ADCs, and real-time digital signal processing, DSP systems. These technologies have significantly improved bandwidth, efficiency, and cost-effectiveness, primarily benefiting coherent optical communications. However, their potential for hybrid optical-electronic processing is gaining increasing attention. By combining the high bandwidth of optics with the computational flexibility of DSP, new architectures can be designed for more versatile and adaptive signal processing. A growing set of photonic-assisted methods is being explored to overcome the inherent bandwidth limitations of conventional electronics, enabling applications such as high-speed waveform synthesis, optical sampling, and real-time signal conditioning 1.4. In this context, we investigate the optic-electronic-optic OEO interferometer architecture, which enables dynamic and flexible manipulation of optical waveforms by converting them into the electrical domain, applying DSP-based modifications, and reconverting them into optics while preserving phase and polarization coherence. Conventional interferometers, based on transparent optical paths, are often limited to basic operations like phase shifts and time delays, enabling applications such as electro-optic modulators 5 and DPSK decoders 6. In contrast, OEO architectures allow much more advanced processing and control of the optical waveform. This makes the OEO interferometric structure particularly well-suited for coherent add-drop multiplexing, where channels can be selectively extracted, modified, or reinserted. Unlike traditional wavelength-selective multiplexers that operate on fixed channel grids, OEO-based systems can handle baud rate-spaced or even overlapping signals 7. The method relies on coherent detection, digital channel separation, and electro-optic modulation for interferometric recombination. Beyond optical communications, OEO interferometric superposition is also relevant for applications requiring phase-coherent feedback, such as coherent Ising machines 8. By bridging the optical and electronic domains, these hybrid processing techniques pave the way for highly adaptive and reconfigurable photonic platforms, unlocking new possibilities in optical computing and signal processing. Recent advances in interferometric add-drop multiplexing have explored different techniques, including all-optical processing via gated fast Fourier transform, FFT9, and coherent detection followed by recombination through frequency conversion in a highly nonlinear fiber 10. However, these two approaches differ fundamentally from the OEO interferometer, first proposed in 11, 12, and later studied through numerical simulations in 13. The first experimental realization of an OEO interferometer was demonstrated in 14, utilizing electrical processing to manipulate intensity-modulated signals. A piezoelectric fiber stretcher was employed to compensate for phase fluctuations, but its limited tuning range constrained long-term stability 15-16. This issue was addressed in 17 by incorporating a real-time DSP-based processing path capable of supporting complex modulation formats. Additionally, phase correction was implemented using an in-phase quadrature (IQ) modulator, enabling continuous phase tuning without range limitations. In this work, we build upon our previous studies 17, 18, by presenting a generalized framework and a more streamlined implementation of the OEO interferometer. We provide a detailed overview of the necessary DSP steps and an in-depth analysis of the phase control loop, demonstrating its ability to maintain long-term phase stability. Additionally, we describe the experimental implementation using an initial prototype integrated module and the design of the photonic integrated circuits, PIC. The FPGA-based testbed enables real-time add-drop multiplexing functionality, and we present bit-error ratio (BER) measurements for a 3-channel WDM signal with 2.9 G spacing and 2 G bead QPSK modulation. These results demonstrate the potential of OEO-based coherent optical multiplexers to bridge the photonic and electronic domains through dense integration with advanced CMOS technologies. 2.2 Optic-Electronic-Optic Interferometer. Basic structure and building blocks of an optic-electronic-optic interferometer. Amplitude spectra at key stages. A. Input WDM signal. B. After reception. C. After DSP filtering. Receiver and LPF bandwidths shown as gray dashed lines. D. Regenerated electrical spectrum with new waveform shaded and inverted original spectrum solid. E. Final optical spectrum after add-drop operation. Typical sequence of DSP steps in an optic-electronic-optic interferometer, and a version implemented in SECT. 231b. Reprinted with permission from 18 Publishing Group. Next, the phase offset is reapplied followed by and filtering through a transmit filter with an impulse response T. Subsequently, the recovered frequency offset is reapplied, and the resulting IQ components are passed to digital-to-analog converters, DA. If phase preservation is not required at the interferometer output, both the phase recovery and phase modulation steps can be bypassed as indicated by the red dashed lines in Fig. 2.2. The The proposed OEO interferometer architecture can be extended to accommodate dual polarization transmission systems. This would involve incorporating an adaptive multiple input multiple output MIMO equalizer, where the equalizer coefficients are inverted and applied to the add path. However, strong polarization-dependent loss could present challenges in practical implementations. 2.3 Experimental Implementations. This section details the experimental implementation of the OEO interferometer for coherent add-drop functionality. The experiments progress through increasingly advanced coherent detection setups. The initial setup employed coherent heterodyne detection with a single-channel input to establish the foundational DSP framework. Building on this, the add-drop operation is demonstrated using a preliminary integrated module. The final implementation then leverages detection to validate add-drop operation under dense WDM conditions. 231 Fiber-based OEO interferometer with heterodyne detection. The first experimental demonstration of the OEO interferometer is carried out for a single-channel input signal with coherent heterodyne detection. The goal is to validate the core DSP framework needed for real-time operation, including receiver-side signal recovery, transmitter-side signal generation for the added channel, and phase control for coherent interference. As illustrated in Fig. 2.3, the system comprises three main sections: a transmitter 0 that generates the initial optical transmit signal, the central OEO interferometer responsible for the add-drop operation, and a coherent receiver 0 used for signal analysis and performance evaluation. Experimental setup of the coherent add-drop interferometer. The optical and electrical signal paths are visualized in black and blue, respectively. Within the DSP block gray-shaded area, complex signals are indicated by a double arrow, while real-valued signals are shown with a single-line arrow. H transform RI, real and imaginary part, respectively. At the interferometer input coupler, a 50-50 coupler splits the transmitted signal power into two distinct paths. In the lower path referred to as the OEO path, we perform balanced heterodyne detection utilizing a balanced photodetector module, BPD, BPR20M, and a free-running fiber laser, NKT, operating at 193.49 T with 10K serving as a local oscillator, low 1. The detected electrical signal is digitized using an AD converter sampling at 4GS with an electrical 3 dB bandwidth of 4G. From this real-valued digital signal, we form a complex-valued analytic signal by generating the imaginary component using the transform H. The transform is implemented by approximating it as a finite impulse response, FIR, filter in the time domain as outlined in 1920. The analytic signal is next subtracted from a digitally frequency-shifted newly generated data signal, referred to as add data. The add data is also a 1 G-beat RRC pulse, shaped QPSK waveform generated following the same process as before. In this implementation, we apply a fixed frequency shift of 1 G to nominally match the frequency difference of 0 and low 1. However, with the implementation of a real-time carrier recovery algorithm 2124, the estimated carrier phase and frequency offset can be directly imposed onto the newly generated data signal. Subsequently, a small amplitude sinusoidal dither signal at a frequency of 15.6 M is applied, where the dither amplitude is quantized with 3-bit resolution compared to the 12-bit resolution of the received signal. The phase correction value from the phase control DSP block's lookup table, LUT, is then applied to this resulting signal to compensate for the random phase fluctuations between the two interferometer paths. Additional details on the phase control mechanism are discussed later in this section. Finally, the real R and imaginary I components of the signal are fed to 2DA converters, amplified, and used to modulate a portion of low 1 via a second Lie O3 IQM. The resulting optical signal is then combined with the signal from the upper path using another 50-50 coupler. The superimposed signal from the upper output of this coupler is used for data evaluation and bit-error ratio (BER) measurements. First, the signal is amplified using an erbium-doped fiber amplifier (EDFA), filtered using an optical bandpass filter, OBP, of bandwidth 10 G to reduce out-of-band amplified spontaneous emission, ASE noise. An ASE noise source is then used to variably add ASE noise and vary the optical signal-to-noise ratio, OSNR. Another coherent receiver, denoted as 0, then performs balanced heterodyne detection of the signal. The receiver uses a free-running ECL 100K as a tunable local oscillator, Low2, and a 5G bandwidth BPD, BDX3BA. The electrical signal is then sampled at 6.25 GS using an oscilloscope, OSC, DPO 70808B for offline evaluation. The recorded waveforms are first normalized and resampled to 2 samples per symbol. After that, symbol timing synchronization is achieved by applying a feed-forward clock recovery 25. Channel distortions are corrected using an adaptive equalizer based on a constant modulus algorithm 26-27. This is followed by carrier recovery with the and algorithm before hard decision demodulation 28. For maximum suppression of the original signal through destructive interference, both interferometer paths must be well matched in terms of group delay, polarization, amplitude, and phase. In our setup, we begin by coarsely adjusting the delay in the through path with roughly 20 m of single-mode fiber, SMF. A variable optical delay line, ODL, with a resolution of 0.3 is then used for fine adjustments. Amplitude and polarization are controlled using a variable optical attenuator, VOA, and a polarization controller, PC, respectively. Schematic of the phase control module consisting of a phase error detector, a loop filter, and a lookup table, LUT. The control loop includes a photodiode, PD, and an analog-to-digital converter, AD, to measure interference power variation. An error signal around 0 frequency is obtained by mixing with the reference dither and filtering the harmonics using a moving average, MA, filter. After N, the signal is fed into a proportional integral pi loop filter to converge to the correct phase. The LUT converts the phase to a complex sinusoidal. Reprinted with permission from 18, Publishing Group. Figure 2.4 depicts the steps of computing the phase correction value in the PLL. First, a low-bandwidth photodetector, PD, DC 200M, converts interference power variations into an electrical signal, serving as a feedback signal. Next, the signal is digitized by an AD converter bandwidth, 10M to 1G, then by the cosine component of the reference dither signal. The resulting output comprises 3 frequency components, one DC term, one component at the dither frequency, and/or another at 2. A moving average MA filter extracts only the DC component by eliminating the oscillatory terms, which serves as the phase error value. The phase error signal is by a factor of 1024 relative to the FPGA clock of 250 M, and then fed to a proportional integral pi controller loop filter 33. The controller parameters are optimized using the method 34. Finally, the loop filter output is mapped into a lookup table LUT that provides the complex valued phase correction. The LUT functions as a numerically controlled oscillator around 0 frequency, and due to its inherent modulo operation on the input index, continuous phase adjustment across the entire range of 0 to 2 is achieved. 2311 Results and Analysis. Measured optical spectra, 20 m resolution bandwidth, recorded at the interferometer output coupler for the upper, through path and lower, OEO path without any interference for constructive and destructive interference, and for the case where the former signal is dropped and a new signal is added. Reprinted with permission from 18, Publishing Group. Figure 2.5 shows optical spectra measured with a 20 m resolution bandwidth at the output coupler for 5 different scenarios. The solid blue trace represents the spectrum when only the through path is connected, while keeping the OEO path open. In contrast, the dashed red line corresponds to the OEO path spectrum with the through path open. At the signal carrier frequency of 193.489 T, the optical power levels are adjusted to achieve similar spectral intensity in both paths. It is visible that the OEO path is able to regenerate the original signal without any noticeable distortion. However, at 193.49 T, the residual carrier from low 1 is visible alongside minor spectral broadening of the signal spectra caused by modulator nonlinearity. The digital transform effectively suppresses the upper sideband near 193.491 T by approximately 25 dB when both interferometer paths are simultaneously connected and the controller is tuned for constructive interference, solid gray. The signal power increases by 6 dB, verifying phase coherence. Conversely, setting the controller to destructive interference yields the solid cyan spectrum, where the signal is suppressed by approximately 17 dB relative to the through-path-only scenario. Finally, when a new data signal is introduced while maintaining destructive interference, the resulting spectrum, dotted orange, exhibits a slight frequency shift, attributed to manual tuning of low 1 and inherent laser drift. Measured photodiode voltage over time, and corresponding histograms of the measured voltage signal B. Reprinted with permission from 18 Publishing Group. The BER performance of the add-drop process is examined under varying OSNR conditions. Amplified spontaneous emission, ASE noise is injected after the OEO interferometer, and the OSNR is determined within 0.1 reference bandwidth. BER values are obtained for 4 distinct cases and compared with a theoretical benchmark solid black, derived analytically for a 1 Gb'd QPSK signal over an additive white noise AWGN channel, as plotted in Fig. 2.7. Due to ASE noise folding from the image band in heterodyne reception, an additional 3 dB penalty is included, in accordance with prior studies 3538. The BER measured using only the through path, shown by solid purple line, establishes a baseline for optical back-to-back characterization. BER measurements for the OEO path alone are first obtained without dither dashed orange, and then with dither-enabled solid cyan, showing a sensitivity penalty of approximately 0.5 dB at a BER of 10.3. BER measurements with varying OSNR for the transmitted QPSK signal before and after interferometric add-drop operation. The insets show the corresponding constellations, 105 symbols plotted for the cases of through, OEO with dither and add. Reprinted with permission from 18 Publishing Group. 232 Integrated OEO Interferometer Module with Heterodyne Detection. Implementing the interferometer system using a photonic integrated circuit PIC will improve both polarization and phase stability. As an initial demonstration, passive waveguides, 312 MMI couplers, and a 90 optical hybrid-based coherent receiver are integrated on an InP platform. The final PIC is co-packaged with a commercially available transimpedance amplifier, TIA, and edge-coupled to fiber connectors. Experimental setup using an integrated optic-electronic optic interferometer module, ODL, optical delay line, VOA, variable optical attenuator, PC, polarization controller, OBP, optical bandpass filter. Reprinted with permission from 39 Publishing Group. The amplified optical signal enters the integrated module, splitting into a through path exiting the PIC and an OEO path to a coherent receiver. A free-running laser low 1, 10K line width is similarly split within the PIC. In our experiment with balanced heterodyne detection, one BPD TIA output is used while the other is terminated. The resulting electrical signal is digitized by a 4G SAD converter on the C building on the previously described DSP processing. We use the transform H to generate an analytic signal, and then subtract from it a digitally frequency-shifted 1 Gb'd QPSK signal, labeled add, obtained by multiplying with a complex exponential exp. Similar to the previous implementation, the frequency offset is roughly 1 G. The next step involves multiplying the difference signal by a phase dithering term exp and the output of the digital phase-locked loop, DPLL. The real and imaginary components of the resulting signal then modulate a portion of low 1 using a second IQM. Both the optical signal and the through-path signal are then routed back into the PIC, where they are combined and coupled out. The interferometer output is divided into 2 distinct paths. One is used for coherent reception, 0, and bit-error rate BER analysis through offline DSP, while the other monitors optical power fluctuations induced by thermal and mechanical phase drifts with a low-bandwidth photodetector, PD, DC200M. The phase error is extracted by the DPLL through a lock-in technique, as presented in the prior section, and phase correction values are calculated using a pi controller. In the external delay path, the group delay between the two interferometer arms is synchronized using patch cords and a variable optical delay line, ODL. A VOA and PC are then employed to adjust both the interference amplitude and polarization. 2321 Results and Analysis. Measured optical spectra, 20 resolution bandwidth for individual through path and OEO path for constructive and destructive interference and for the add-drop operation AD. Adapted with permission from 39 Publishing Group. BER performance for varying OSNR with the integrated interferometer module for single carrier heterodyne reception at the OEO path. Adapted with permission from 39 Publishing Group. Figure 2.9 presents the optical spectra obtained under 5 distinct conditions, with a portion of the PD input tapped for measurement. The solid blue and dashed red traces represent the spectra of the individual interferometer through and OEO paths, respectively. The solid gray and solid cyan traces represent constructive and destructive interference, leading to a 6 dB power enhancement and an extinction ratio of 15 dB, respectively, compared to the individual paths. The dashed yellow trace represents the spectrum following the add process. Similar to the measurements in the earlier section, all spectra, except for the interferometer through path, exhibit suppression of low 1 near 193.49 T and effective attenuation of the upper sideband near 193.491 T, an effect of the digital transform. Figure 2.10 illustrates the measured BER as a function of OSNR for this integrated module-based setup. While the overall trends align with the previous full fiber-based setup measurements, slight increase in BER penalties are observed. The theoretical curve obtained analytically for an AWGN channel is shown in solid black. The through-path circle marker again serves as the baseline measurement. The OEO path without dithering dash-dotted orange line exhibits a 0.2 dB penalty, while enabling the dither signal solid cyan line introduces an additional 0.6 dB penalty at a BER of 10.3. Both penalties are slightly higher than those observed in the fiber-based measurement. For the add operation triangle marker, the overall penalty amounts to 1.3 dB, which correlates with the 2 dB lower extinction ratio compared to the full fiber-based implementation. The increased penalty may result from length mismatch and polarization misalignment introduced during fiber-chip coupling, particularly due to the off-chip single-mode fiber delay in the through path. In summary, we have demonstrated a functional OEO interferometer module based on an in-P PIC incorporating passive waveguides and coherent receivers. The module achieves a coherent add-drop operation of 1 Gb'd QPSK signals with only a slight penalty increase compared to the fiber-based setup. This small additional penalty, caused by fiber-to-chip coupling issues, can be minimized through methods such as lensed fiber integration, which enhances mode field overlap with the chip's waveguide. With further refinement, such integrated solutions offer a promising path toward compact, scalable, and fully integrated interferometric optical add-drop multiplexing systems. 233 Fiber-based OEO interferometer with detection for WDM signals. Experimental setup of the coherent add-drop interferometer based on reception for WDM operation. Optical and electrical signal paths are represented by black and blue lines, respectively. Within the gray-shaded DSP block, complex-valued signals are denoted by double arrows, and real-valued signals by single-line arrows. ECL, external cavity laser, ODL, optical delay line PC, polarization controller, ICR, integrated coherent receiver. Building on the single-channel heterodyne detection-based experiment, the setup is extended to support a multi-carrier WDM signal using detection. The experimental configuration is illustrated in Fig. 2.11. The transmitter 0 now features an electro-optic frequency comb, IO comb, implemented using a Mach modulator MZM, as detailed in the inset. The MZM is driven in push-pull configuration by a 2.9 G sinusoidal RF tone from a synthesizer. The drive voltage is tuned to produce three spectral lines, the carrier 0th order and the first order sidebands 1. The MZM bias is further adjusted to equalize the power of these three spectral lines. Block diagram of the DSP chain in the OEO path supporting add-drop operation for WDM signals. Functional blocks for coarse frequency offset estimation, received signal correction, and signal synthesis are highlighted with blue, yellow, and red shading, respectively. A fiber delay of 64 m is added to the through path to coarsely align the group delay with the OEO path. As in the previous setup, one output of the interferometer is fed to PD for phase control operation, while the other output is routed to a receiver 0, employing a separate ECL 100K as low 2 and another ICR for performance evaluation after ASE noise loading. The received signal is then sampled using an oscilloscope, OSC, at 4GS and evaluated offline as described in Sect. 231. The DSP architecture implemented in the OEO path is illustrated in Fig. 2.12, with the corresponding filter responses shown in Fig. 2.13. The received IQ signal is processed along two parallel branches, each addressing different signal conditioning tasks. In the first branch, a coarse frequency offset compensation algorithm is employed. A 15-tap bandedge filter, whose frequency response is shown in Fig. 2.13, is used to estimate the frequency offset between 0 and low 140. For efficient implementation, the filter response is decomposed into even and odd components, taking advantage of the properties that the imaginary part of the even filter and the real part of the odd filter are 0. The even filter output is delayed, and with the conjugate of the odd filter output. The real part of the resulting product yields the frequency error estimate. This error signal is smoothed via moving average MA and passed through a pi loop filter. The resulting control signal drives a numerically controlled oscillator, NCO, which synthesizes a complex exponential representing the estimated frequency offset. The correction signal is with the received IQ waveform to complete the feedback path, while its conjugate is applied to the add data signal to ensure frequency alignment. Frequency responses of FIR filters used in the DSP chain, a 15-tap bandedge filter for frequency offset estimation, B low-pass filter designed using a Kaiser window, C 15-tap inverted triangle filter response used for spectral shaping. 2331 Results and Analysis. Comparison of optical spectra for the through-path blue, the OEO path without equalization yellow, and with the equalizer red, measured with a resolution bandwidth of 20 m. Optical spectra 20 m resolution of a 2 G-bead QPSK signal recorded at the interferometer output for individual through OEO paths, constructive-destructive interference, and add operation. BER versus OSNR for detected single carrier signal with corresponding constellations at 2.7 dB OSNR. The BER performance of the single carrier detection configuration is presented in Fig. 2.16. As in the heterodyne case, BER values are shown for 4 distinct cases, and OSNR is determined within 0.1 reference bandwidth. The analytic curve for a 2 G-bead QPSK signal in an AWGN channel is plotted in solid black. The solid purple line with circle markers shows the BER for the through path alone, serving as an optical back-to-back reference. The OEO path without dither dashed orange and with dither solid cyan both exhibit a small 0.3 dB OSNR penalty at a BER of 10.3 due to the optical conversion process. Notably, the addition of the dither signal introduces no further penalty. When the add data signal is enabled dotted magenta, in place of the drop channel, a slight additional penalty of 0.1 dB is observed, attributed to linear crosstalk from the residual drop signal. Overall, the total OSNR penalty from the complete add-drop process including both OEO conversion and crosstalk effects is approximately 0.4 dB. The inset shows constellation diagrams measured at 2.75 dB OSNR, corresponding top to bottom to the through path, OEO with dither, and add data cases. Optical spectra at the interferometer output for the 3-channel WDM signal with add drop of the center channel. The resolution bandwidth is 20 m. Optical spectra at the interferometer output for the 3-channel WDM signal with add drop of the left channel. The resolution bandwidth is 20 m. Optical spectra at the interferometer output for the 3-channel WDM signal with add drop of the right channel. The resolution bandwidth is 20 m. BER measurements for 3 WDM channels before and after add drop of the central channel, left. Corresponding constellations at 3 dB OSNR, right. BER measurements for all 3 WDM channels were carried out before and after performing an add drop operation on the center channel. The Yoakum generator was adjusted to ensure equal peak power across all channels, and the optical spectrum analyzer OSA resolution bandwidth was set to 0.1, wide enough to encompass the full 3-channel WDM signal. The results are summarized in Fig. 2.2 alongside the analytic curve for 2 G-bead QPSK signal. The measurement labeled before add purple curve corresponds to the case where only the through path was active. The after add operation case, magenta curve, reflects the scenario where a new data signal is inserted at the center wavelength using the OEO interferometer. At BER values above 10.3, all 3 channels exhibit similar BER performance before and after the add operation. A minor penalty of approximately 0.4 dB is observed at lower BER values, e.g. at 10.4 for the central channel after the add operation, attributed primarily to residual crosstalk from incomplete suppression during the drop stage. This BER performance is further reflected in the constellation diagrams shown on the right of Fig. 2.2. These constellations captured at 3 dB OSNR illustrate the signal quality for the 3 WDM channels without top and with bottom the add drop operation. BER measurements for 3 WDM channels before and after add drop of the left channel. BER measurements for 3 WDM channels before and after add drop of the right channel. 2.4 Integrated OEO interferometer. As demonstrated in the previous experiments using discrete components, maintaining phase and polarization stability is essential for effective interferometric recombination. An integrated OEO interferometer photonic integrated circuit, PIC, offers significant advantages in enhancing polarization and phase stability. The indium phosphide InP platform, known for its high integration capabilities of active components 41-42, is an excellent choice for developing an integrated OEO interferometer PIC. 2 generations of the InP-based integrated OEO interferometer are introduced. Initially, a partially integrated OEO interferometer is presented. This PIC incorporates waveguide routing for the interferometer setup and a coherent photodetector. After characterizing the PIC, it is assembled into an OEO interferometer module. Subsequently, a fully integrated OEO interferometer PIC is introduced, which is integrating all the active optical components necessary for the OEO interferometer setup. 241 Partially integrated OEO interferometer PIC. In this section, the partially integrated OEO interferometer is presented. The partially integrated PIC essentially combines the waveguide routing for the OEO interferometer and a coherent photodetector. It is an intermediate step towards the fully integrated OEO interferometer. The PIC is assembled into an OEO interferometer module. 2411 PIC design and fabrication. Top view photograph of the partially integrated OEO interferometer PIC. 1 coherent photodetector, 2 heater, 3 couplers, 4 spot size converters. The partially integrated OEO interferometer PIC, Fig. 2.23, was manufactured on the same InP platform as in 43. This PIC integrates a coherent photodetector and waveguide routing for the OEO interferometer setup. The coherent photodetector is based on a 2-4 interference coupler and 4 photodiodes. Due to the DSP delay compensation necessitating an optical delay line of several meters, the reference path is implemented using off-chip fiber. To account for phase shifts within the off-chip reference path, a thermal phase shifter is placed on the chip. For efficient fiber chip coupling, the process chip comprises single-mode fiber spot-size converters as optical interfaces. 2412 PIC measurement. A NB dark current measurement of the coherent photodetector. 2413 module setup. Photograph of the assembled module with its evaluation board, corresponding to the chip schematic shown in Fig. 2.23. 2414 module measurement. Bandwidth measurement of all 4 channels of the assembled module. 242 fully integrated OEO PIC. In this section, the fully integrated OEO interferometer PIC is presented. It comprises all optical components necessary for an OEO interferometer setup. 2421 PIC design and fabrication. Photograph of fully integrated OEO interferometer PIC, 1 coherent photodetector, 2 tunable low, 3 IQ MZM, 4 reference photodiodes, 5 EO phase shifter, 6 converters. 2422 PIC measurement. The coherent photodetector of the PIC is characterized by measuring the and the dark current of all 4 photodiodes. Figure 228 shows the measured of all 4 photodiodes for TE polarized light. The measurement was performed by using an external laser source and a reverse bias voltage of 2V. The maximum is at 0.055 AW at a center wavelength of 1580. The value includes 3 dB inherent splitter loss. The center wavelength indicates that the photodetector is centered within the C and L bands. Figure 228b illustrates the dark current measurement of the photodiodes. At a reverse bias voltage of 2V, the photodiodes exhibit a dark current of 10 Na and B dark current measurement of the coherent photodetector. Tuning range of integrated low. Ratio and measurement of the upper and B lower MZM of the IQ modulator. 2423 module setup. Model of planned fully integrated OEO interferometer module. 2.5 summary. We present the first experimental demonstration of an OEO interferometer performing coherent optical add-drop functionality. The system development is presented methodically, beginning with a coherent heterodyne detection approach for single-channel input and advancing to detection configurations suitable for WDM signals. A comprehensive framework for the required DSP algorithms is established, along with a discussion of critical design aspects such as optical path length matching and phase stabilization. In the current implementation, the achievable symbol rate is primarily limited by the sampling rates of the C's data converters. Advancements in FPGA technology, along with faster, integrated, and synchronous data converters, are expected to enable higher symbol rates in future implementations. The transition to higher-order modulation formats is mainly constrained by the achievable extinction ratio of the destructive interference process, which remains a critical performance factor. Extending the system to support overlapping subcarrier multiplex signals, such as offset quadrature amplitude modulation, OQAM, requires symbol-level signal recovery with complete frequency and phase estimation, as well as reapplication at the stage. System stability is currently affected by phase and polarization drifts, largely due to the use of discrete optical components. This limitation is addressed through photonic integration. To this end, 2 generations of NP-based integrated OEO interferometer PICs are presented. As an initial step, a partially integrated OEO interferometer PIC is designed, characterized, and assembled into a module, with experimental validation confirming the feasibility of further integration. This is followed by the realization and characterization of a fully integrated OEO interferometer PIC. Current efforts focus on packaging the fully integrated PIC into a module and experimentally validating its performance and robustness. These developments contribute to the realization of fully integrated, high-performance photonic systems for advanced coherent optical networking, computing, and sensing. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1D Fang D A Peng HCTGWSTT C 2023 CLEO 2023 Publishing Group PS5C8 Org 101364 CLEO SI 2023 S5C8 2CAT Feng D DT TZW SC 2022 Conference on Lasers and Electro-Optics Publishing Group PS5M3 Org 101364 CLEO C2022 S5M3 3SYNC JASJCT 2020 IEEE Photonics Technol 32241544 Org 101109 LPT 20203 039621 4AOAFSJ 2023 Opt 546 129809 Org 101016J2023129809 5CJW Cole M Dalton L W Al M A S Wolf SC SKJWYS Palmer R D L PC Elder DLT J 2016 J Light Technol 342256 Org 101109 JLT 201524999763 6AP 2005 J Technol 231115 Org 101109 JLT 20048403577 7DM PD A NKYR LJM I 2017 J Opt 911 Org 101364 JOCN 9000001 8-man PLAYRC STHSKRL MMHY 2016 Science 354 6312614 Org 101126 Science 5178 9SJSAEKAD 2015 J Light Technol 33711351 Org 101109 JLT 20152390292 10TCRTT SC 2015 J Light Technol 333685 Org 101109 JLT 20142379472 11 Taylor MG 2011 Coherent Optical Channel Substitution U.S. Patent 8050564 B2 1 2011 12M P 2015 Network Element U.S. Patent 8971726 B2 3 Mar 2015 13 PJ 2013 J Light Technol 31111775 Org 101109 JLT 20132257687 14 MS JN MCAPM WCS 2020 Conference on Lasers and Electro-Optics Publishing Group PSF1L1 Org 101364 CLEO SI 2020 SF1L1 15 Tempus M W Weber HP 1993 B Laser 56279 Org 101007 BF0032524 16 AA J 1995 Opt 26635 Org 101364 2000635 17 MSP MMHC S 2023 CLEO 2023 Publishing Group PSM2I6 Org 101364 CLEO SI 2023 SM2I6 18 MSPJC S 2025 Opt Express 33468885 Org 101364 OE 532854 19 Leon RG 2004 Understanding Digital Signal Processing 2nd Prentice Hall PTR Chap P9 20C MMH Wolf S JNWC S 2019 J Light Technol 37174295. Org 101109 JLT 201929232249. 21 Levin A N UV YK 2007 IAEE Photonics Technol 196366. Org 101109 LPT 2 0078918993. 22 Li L Tau Z ST JC 2008 OFC NFOEC 2008 2008 Conference on Optical Fiber Communication National Fiber Optic Engineers Conference 13. Org 101109 OFC 20084528776. 23 SST OCRM R 2008 IEEE Photonics Technol 2018 1569. 24 HTT SJC Li L Tau Z YKKH 2008 34th European Conference on Optical Communication 12. Org 101109 ECOC 2 0084729128. 25P MSCCW S 2021 Optical Fiber Communications Conference and Exhibition OFC 13. 26 Savory SJ 2008 OptExpress 162804. Org 101364 OE16 000804. 27 M FN KB MS Napoli A B 2009 J Light Technol 27163614. Org 101109 JLT 2 0092 024963. 28 AJ AM 1983 IEEE Trans Theory 294543. Org 101109 TIT 19831056713 MathNet. 29 FKD W 2006 IEEE J Quantum Electron 4210973. Org 101109 JQE 2006881413. 30K W 1999 IEEE LEOS Annual Meeting Conference Proceedings. LEOS 99. 12th Annual Meeting. IEEE Lasers and Electro-Optics Society 1999 Annual Meeting, CAT. No. 99 CH 37009, 1, 295-296. 10.1109, LEOS 1999813599. 31V S 2008, Optic Express 162686. 32R S R A Gupta S 2020 IEEE Photonics Conference, IPC 2020 Proceedings 3132. 33F 2005 Techniques. 34JG NB 1993 J Dine Control 115-2 B220. Org 10111512899060. 35 SD 1971 Bell Tech J51213. Org 10100-2J1538 7305 197102544X. 36 LG 1985 J Opt 6118. Org 101515 JOC 19856 37 Bari JR Lee EA 1990 Proc IEEE 788139. Org 101109558322. 38E 2018 Optical Coherent Detection and Digital Signal Processing of Channel Impairments. Springer, Singapore 170. 39 MS PJAPC S 2024 CLEO 2024. Publishing Group PS1Q6. Org 101364 CLEO SI 2024 S1Q6. 40Q 2018 Wireless Communications from the Ground Up, an SDR Perspective. CreateSpace Independent Publishing Platform. 41S LA 2018 IEEJ Top Quantum Electron 2411. Org 101109 JSTQE 201727545583. 42 Soars FM MT Groden MTP M 2019 98. org 10339 app 9081588. Com 20763417981588. 43P SAKJD ML 2014 IEEE Photonics Technol 2643449. org 1011109 LPT 20132293635. 44 Sartorius B P M 2020. Patent number DE 201910206415201900503. 45 Lee MH Soars F M M W M 2020 Semiconductor Lasers and Laser Dynamics IX. In MRKS International Society for Optics and Photonics SPIE 11356 P 1135605. 10.11171225545541. 46 Gupta YD G Dials WOT M 2023 J Light Technol 41113498. org 1011109 JLT 20233244129. 3. Ultra Broadband Assisted Analog to Digital Converters. Abstract. We present recent progress made towards ultra-broadband assisted analog-to-digital converters that leverage both the low jitter of best-of-class mode-locked lasers as well as the capability of optics to break down broadband signals into multiple lower-speed tributaries that can be better handled by electronics. We review in particular our work on both time and frequency domain approaches and give an outlook on how these architectures can be extended to include further signal processing tasks such as equalization. Optically triggered track-and-hold amplifiers are reported with an equivalent jitter below 80 in a signal frequency range from 20G to 70G. Frequency domain architectures implementing optical arbitrary waveform measurement up to signal bandwidths of 610G are also shown. Finally, an architecture allowing the equalization of PAM4 signals is introduced and modeled for operation in 400S links. Acronyms: Analog to Digital Converter, Arrayed Waveguide Grating, Additive White Noise, Balanced Optical Microwave Phase Detector, Balanced Photo Detector, Bandwidth, Cloud Radio Access Network, Coupled Resonator Optical Waveguide, Constellation Signal-to-Noise Ratio, Directional Coupler, Directional Coupler Splitter, Digital Signal Processing, External Cavity Laser, Erbium-Doped Fiber Amplifier, Electromagnetic, Effective Number of Bits, Electro-Optic, Electronic-Photonic Integrated Circuit, Fiber Grating, Finite Difference, Free Spectral Range, Finite Difference Time Domain, Full Width at Half Maximum, Grating Coupler, High Frequency, Integrated Circuit, In-Phase and Quadrature Receiver, Intersymbol Interference, Local Oscillator, Mode Field Diameter, Mode-Locked Laser, Interference, Maximum Ratio Combining, Mach Modulator, Optical Add-Drop Multiplexer, Optical Arbitrary Waveform Measurement, Optical Carrier-to-Noise Ratio, Orthogonal Delay Division Multiplexing, Electronic Phase Locked Loop, Optical Frequency Comb, Optical Hybrid, Overlap Region, Optical Ring Resonator, Pulse Amplitude Modulation, 4-level Pulse Amplitude Modulation, Printed Circuit Board, Photonic Integrated Circuit, Power Spectral Density, Quadrature Amplitude Modulation, Radio Frequency, Sliceable Bandwidth Variable Transponder, Switched Emitter Follower, Supplementary Information, Signal-to-Noise and Distortion Ratio, Signal-to-Noise and Distortion Ratio, Signal-to-Noise Ratio, Standard Single-Mode Fiber, Thin Film Lithium, Track and hold amplifier. Amplifier. Voltage-controlled oscillator. Wavelength division multiplexing. Programmable optical filter. Yttrium iron garnet. 3.1 Introduction. The sampling rate, analog bandwidth, and effective number of bits, ENOB, of analog-to-digital converters, ADCs, are becoming a bottleneck for the scaling of data rates in fiber optic communications. While ADCs have been an essential component of long-haul fiber optic communication links for several decades, the introduction of higher-order pulse amplitude modulation, PAM, and of asynchronous digital signal processing in interconnects has also moved them into focus there. The ENOB of ADCs in particular is limited by the jitter of electrical clocks, as generated by quartz oscillators in conventional systems. This has motivated the use of mode-locked lasers, MLLs, as low jitter frequency references in analog-to-digital conversion too, since benchtop MLLs have been shown to provide pulse trains with jitter that outperforms that of quartz oscillators by many orders of magnitude 3. This chapter deals with progress on optically enabled ADC architectures, developed with the goals of leveraging the low jitter of such optical clocks, and to reach analog bandwidths and sampling rates outperforming those of pure electronic systems. These are broadly categorized into time and frequency domain architectures, wherein the pulse train of the MLL acts as a time reference in the former, and the comb-like spectrum of the MLL acts as a frequency reference in the latter. Notably, even for the frequency domain architectures, the jitter of the pulse train remains a primary driver of the overall system performance after signal aggregation 4. Section 3.2 deals with optically triggered electrical track-and-hold amplifiers, THAs, in which optical pulses replace an electrical clock transition. In Sect 3.2.1, the THA is directly triggered by the optical pulse, with the simplicity of this approach enabling high analog bandwidth and low jitter. As a disadvantage, this requires the optical pulse train to already have the required repetition rate, which can be problematic as best-of-class MLLs are typically benchtop devices with large cavities and consequently large repetition times. Since in this architecture only the envelope function of the pulse train matters, and not the actual free spectral range, FSR, in the frequency domain, the effective repetition rate of the pulses can be increased with low optical losses with a pulse interleaver 5. Alternatively, a higher repetition rate voltage-controlled oscillator, VCO, can be locked to a multiple of the repetition rate of the MLL with an electronic phase-locked loop, OEPLL, as described in Sect 3.2.2. In Sect 3.3, two approaches are described in which an optical front-end converts an incoming broadband optical signal into several lower-speed tributaries, each of which can be digitized with downstream all-electrical AGs whose bandwidth and sampling rate requirements are correspondingly reduced. In both architectures, signal reconstruction is done in the frequency domain, wherein the first relies in first slicing the optical signal in the frequency domain prior to digitization and stitching, while the second relies on coherent detection of the signal using a frequency comb generated by an MLL as a local oscillator, with different group delays applied to the comb for each tributary. This second method has the advantage of not requiring optical filters and thus facilitates the configuration of the chip, as higher-order optical filters are not required. Such filters are used in the first, frequency-sliced architecture, and typically require several phase tuners each to compensate for fabrication errors and temperature drift. While both methods rely on frequency domain signal processing and do not require narrow pulses, i.e., the optical comb can be dispersed, the second one can be reduced to coherent sampling of the signal by time-interleaved pulses in the case, and can thus also be considered as an intermediate case between the time and frequency domain approaches. A signal multiplexing approach relying on generating orthogonal carriers by delaying an optical comb by different group delays, orthogonal delay division multiplexing, ODDM6, can be reduced to an optical with equivalent functionality 7 that can be further generalized to implement equalization in the optical domain prior to digitization, further reducing the ENOB requirement of the utilized electrical ADCs. Here too, a filterless approach facilitates the configuration of the system and increases its tolerance against temperature drift. 6. 3.2 Optically triggered track and hold amplifiers as analog frontends for time-interleaved ADCs. In the following, we describe two approaches to synchronize time-interleaved THAs with an optical pulse train, the first relying on direct optical triggering and the second on locking a VCO to it. 3.2.1 Track and hold amplifiers with direct optical triggering. Time-interleaved optically clocked triggered ADC concept in a silicon photonics technology. 3.2.1.1 Concepts. The development of suitable on-chip MLLs is an active area of research, however. Best-of-class MLLs currently remain solitary devices 10, so that we envision a partial integration as represented in Fig. 3.1 The light distribution and delay network is implemented on chip together with the BiCMOS electronics in a silicon electronic-photonic integrated circuit, EPIC platform. Only the comb generation and spectral shaping are implemented off-chip. While progress has been made in reducing the RF and jitter of semiconductor MLLs by combining IIIV gain media with silicon photonic integrated circuits PICs, either in extended cavity 11 or in external feedback configuration 12, the limited gain spectrum of semiconductors and the resulting large pulse durations present a fundamental limit to reducing the jitter 13. Promising work on the chip-scale integration of optically pumped rare earth MLLs with a sufficiently wide gain spectrum is, however, in progress 14 and reported in another chapter of this book. Optical clock signal generation. We choose an optical clock configuration in which high power encodes a logical high and sets the THA into track mode, and low optical power, or off, encodes a logical low and switches the circuit into hold mode. This translates short MLL pulses into a sharply defined sampling time and contributes to maintaining a low jitter. As mentioned above, 3.1 shows that with increasing analog input frequency, the effect of clock jitter on the SNR also increases and becomes the limiting factor. This is the motivation behind the use of ultra-low phase noise MLLs. Clock distribution. The MLL pulse train has to be split and distributed to the individual THA ADC channels, for example with discrete fibers or on-chip silicon or silicon nitride waveguides. In Fig. 3.1, the pulse train is first bandpass filtered and then coupled into the EPIC by means of a grating coupler GC. The light is then split into n separate paths with optical delay lines that generate the necessary time delays for interleaving the n clock signals. In Fig. 3.1, a simple power splitter is shown as this maintains the pulse shape. This differs from the wavelength demultiplexing approach used in 2.16 that employs an arrayed waveguide grating AWG and coupled resonator optical waveguide CRO filters respectively to generate interleaved pulses intended to carry the data. Detection and amplification, electronic conversion. Each channel consists of an electronic optically triggered THA. A photodiode converts the optical signal into an electrical current, and a passive, resistive, or active TIA with subsequent clock signal buffer is used to drive the electronic switches. For a high-speed sampler with sampling rates in the range of tens of G, an active TIA is better suited. It allows for a more precise control over the gain, bandwidth, and linearity requirements. Sampling electronics and ADCs, high-speed THAs in C or in P can be used as time-interleaved analog ADC frontends. Subsequently, the electronic input signal RFIN is resampled by slower CMOS ADCs and converted into its digital representation. The resolution of the ADCs needs to be at least as high as the targeted ENOB. Using a BiCMOS EPIC platform, they can be combined on a single chip with the silicon photonics frontend as represented in Fig. 3.1. A single channel of such an optically triggered THA is designed in a silicon photonics C BiCMOS EPIC technology and analyzed by means of simulations in 17. The results indicate a small signal bandwidth of 78 G and over 7-bit effective resolution up to a 50 G signal bandwidth. To verify the high performance shown in these simulations, the chip was fabricated and is described in the next section. 3.2.1.2 Demonstration. A micrograph of an electronic THA. B common base TIA with simple output buffer. A reprinted with permission from 18, Optical Society of America. B is taken from 19, used under CC BY4. The Ceph architecture is chosen because it typically achieves the highest possible bandwidth and sampling rate in a given technology. Advanced circuit techniques like emitter degeneration with capacitive peaking and the inherent peaking behavior of a loaded emitter follower are leveraged to achieve a 65 G3 dB small signal bandwidth with a technology transit frequency FT of 240 G. A measured SNDR-Vs. Analog input frequency reported at the ISSCC and VLSI conferences from 1997 until 2024-20. The triangle represents the best case measurement from 18. BINOB SINAD measurements, depending on signal frequency and amplitude. Dashed lines show the 55, 80, and 100 equivalent jitter limits. B is reprinted with permission from 18, Optical Society of America. Simulations feature a TIA bandwidth of around 30 G. However, since at the time of the experiments only a low jitter MLL from Menhir Photonics with a central wavelength of 1550 and a repetition rate of 250 M was available, they were carried out with a 250 M sampling rate. The sparsity of samples resulting from operating in undersampling mode at high signal frequencies does not, however, prevent the evaluation of the SNR and ENOB at high signal frequencies. The MLL generates an optical pulse train with an extremely low jitter below 10, integrated over an offset frequency range from 100 to 10 M. The measured signal-to-noise and distortion, SINAD-SNDR, is plotted in Fig. 3.3b. Rearranging 3.1 for results in a corresponding worst-case equivalent jitter below 80 in the signal frequency range from 20 to 70 G. The best equivalent jitter of 55.8 was obtained at 41 G. Figure 3.3 benchmarks this result against literature data, making apparent that it would be at the forefront of high-speed samplers if translated to a full AG system. 3.2.2 track-and-hold amplifiers triggered by an electronic phase-locked loop. Unlike the optically clocked triggered THA described in the previous sect. 3.2.1, in which photodiodes and the subsequent TIAs directly convert an MLL pulse train into an electronic clock, the OEPLL employs an MLL as an ultra-stable reference oscillator to stabilize an electronic oscillator that further drives the sampling switches. In particular, this enables upconversion of the optical pulse train repetition rate. 3.2.2.1 Concepts. Concept of a time-interleaved THA triggered by an electronic PLL. A conceptual schematic is shown in Fig. 3.4. The blue frame identifies a high-speed 2-interleaved THA in a fast C technology. A VCO IG. A oscillator is used to generate a clock signal in the range of 100 G. Placing it in between the two THAs and implementing it differentially inherently generates the and 180 clock phases needed to drive the two time-interleaved sampling channels. Best-of-class benchtop MLLs usually do not have such high repetition rates, which can be addressed by incorporating a frequency divider in the OEPLL. A divide-by-4 or divide-by-8 stage can be implemented on the high-frequency HF chip to reduce the chip-to-printed circuit board PCB or chip-to-chip interface requirements. An optional RF amplifier, which could also be already integrated on the HF side, drives a balanced optical microwave phase detector BOMPD. This phase detector can consist of a dual-output Mach modulator MZM, as shown in Fig. 3.4. Lowering the frequency is beneficial because it allows the use of compact silicon photonic forward-biased phase shifters inside the MZM21. After photodetection, a low-pass filtered and amplified control voltage is generated to tune the on-chip VCO. As in Sect. 3.2.1, the MLL is kept as the only discrete element due to the better phase noise performance of benchtop devices. The advantage of this architecture is that the MLL repetition rate can be much lower than the required sampling rate. In fact, the PLL can not only lock to the fundamental frequency of the MLL, but also to any harmonic. Here we picture a hybrid system, using 2 chips or a chip plus PCB combination. Although from a cost and compactness perspective, it would be desirable to have an integrated solution, the available transistors in the EPIC platforms are not the fastest on the market. A hybrid 2-chip approach allows to combine the best-of-class electronics with silicon photonics. HF transistors are then implemented on a purely electronic integrated circuit, IC, on one side, and low-speed detection and control electronics for the OEPLL are integrated with the silicon photonics devices on the other. The OEPLL concept is elaborated on in detail in 10.22, where an yttrium iron garnet YIG oscillator with a tunable oscillation frequency of 220 G serves as the frequency tuning element, and a Menhir 1550 MLL with 250 M repetition rate serves as the reference. Phase noise measurements show an integrated jitter, integrated from 1K to 100 M, of under 4 in the 520 G oscillation frequency range, with typical and minimum values of 4 and 3, respectively. 3222 Circuit Design and Implementation. Schematic of the high-speed THA core, implemented in an advanced C technology. To exemplify the reduction to practice, a high-speed THA is implemented in IHP's SG13G3C by CMOS technology. It provides an FT of 470 G, which is a significant improvement compared to the EPIC platform that has an FT of only 240 G. Figure 3.5 shows the core sampler schematic. A 2-time interleaved architecture is chosen. The input buffer is composed of 2 cascaded emitter-follower stages, first Q1, Q2, followed by Q3, Q4, with 100 resistors RIN providing input matching. After this stage, a switched preamplifier is used. It supplies a gain of 1 dB to offset losses in the signal chain, and to achieve a high bandwidth, several extension techniques are implemented. First, a differential amplifier, Q7, Q10, is used to reduce the Miller effect, which results in a parasitic input capacitance of only +2, with the base emitter and the base collector capacitance. In addition, a negative capacitance equal to is introduced by cross-coupling 2 transistors, effectively canceling out the base collector capacitance of Q7 and Q8. The gain is finally tuned using resistor RC and emitter degeneration RE, while capacitive peaking with CE extends the bandwidth without resorting to space-consuming inductors. Transistors Q11 and Q12 are alternately switched. When Q11 is active, the circuit operates in track mode, allowing the input signal to appear at nodes. When Q12 is active, these nodes are held at a constant voltage, thereby isolating the input during hold mode. The design then employs a pseudo-differential switched emitter-follower configuration as the core sampler. Only the positive side, Q19, is shown in Fig. 3.5. This architecture offers both high bandwidth and fast sampling rates, making it ideal for analog ADC front-end applications. When Q19 is on, the voltage at the hold capacitor CH follows the input. When it is off, the circuit enters hold mode. Feed-forward capacitors further suppress feed-through, enhancing hold mode isolation. A small resistor is also added. Although it slightly reduces overall bandwidth, it decreases the current of the tail current source too, which in turn reduces power consumption and helps maintain a stable hold mode voltage during dynamic operation. Finally, the core circuit is followed by a 50 output buffer, implemented as a differential amplifier. With 50 collector resistors and strong emitter degeneration, this stage achieves a gain of approximately 0 dB. The outputs of each channel are then connected to the chip pads via 50 transmission lines. 3223 Expected Performance. A layout view of the full chip in an M simulator, ADSR. B post-layout simulated S-parameter results. A time domain output of channels 1 and 2. B simulated SINAD, SNR, THD, and ENOB over signal frequency. Figure 3.7 shows the transient differential output signal of channels 1 and 2. It is clearly seen how they generate time-interleaved samples of the input signal, with a sampling rate of 64 GSS per channel. The input signal frequencies are chosen according to the requirements of coherent sampling, described in the IAEE Standard 12412023, fin Kn, where n is the number of samples in the record, k a prime number relative to n, and the sampling rate. Specifically in Fig. 3.7 a K99, N512 and 64G, which result in an input frequency of 12.38 G. In the same way, other frequency points between 1G and 110G are chosen. The transient data is resampled in the middle of the hold phases, and SINAD, THD, and SNR are calculated using the sine wave curve fitting method 23. The circuit is sufficiently linear, as the THD allows for over 6 bits of effective resolution over the entire frequency band, see Fig. 3.7b. The SINAD, which takes into account noise and distortion, stays over 34 dB up to 110 G. The simulation results are very promising and show how a modern and fast C technology allows for extremely high-speed and high-resolution samplers at moderate fabrication cost and high scalability. 3.3 Frequency Domain Optical Arbitrary Waveform Measurement and Photonic Electronic Analog-to-Digital Converters. In this section, several ultra-broadband signal measurement systems are presented covering functionalities of optical arbitrary waveform measurement, OAWM, and photonic electronic analog-to-digital conversion, ADC. A common feature of all these systems is their reliance on breaking down broadband optical waveforms into multiple tributary signals, from which the original waveform is later reconstructed in the frequency domain. This is achieved either by using optical demultiplexing filters 24 or by optical downsampling, which enables parallel signal processing in the frequency domain at relatively lower bandwidths. By leveraging the coherence of optical frequency combs, combined with dedicated signal reconstruction algorithms, these concepts allow for signal reconstruction with high fidelity and superior bandwidth scalability. 3.3.1 Sliced Optical Arbitrary Waveform Measurement, OAWM. OAWM holds significant potential across a wide range of applications, from analyzing ultrashort events 25-26, receiving communication signals with ultra-high symbol rates 27-29, to enabling elastic optical networking 30-32, and sliceable bandwidth variable transponders (SBVT) in cloud radio access networks (CRAN 33). Particularly, OAWM receivers can serve as optical signal processing engines in ultra-broadband photonic electronic AG systems 34, where broadband incoming radio frequency (RF) signals are first converted into optical signals. Among various approaches, sliced OAWM that uses optical demultiplexing filters to subdivide the incoming broadband waveform into a series of narrowband tributaries provides several advantages, such as low crosstalk among sub-channels and straightforward scalability of the signal acquisition bandwidth that increases linearly with the number of parallelized detection channels. 3.3.1.1 Concepts. Concept of a sliced optical arbitrary waveform measurement, OAWM system. The incoming optical signal, described by a complex valued frequency domain signal ASF, is decomposed by a first one into a series of signal slices AS1 ASM, which are coherently detected by an array of in-phase and quadrature receivers IQR1, IQR2, IQRM, using local oscillator tones that are derived from an optical frequency comb via second 2. The signal slices are digitized by an array of electronic ADCs, resulting in complex valued signals U1, FU2, FUMF. The original broadband signal is then reconstructed by DSP. For simplicity, optical amplifiers have been omitted in the illustration. The concept of a sliced OAWM system is illustrated in Fig. 3.8. The incoming broadband optical signal can be described as a STA-ST-XJ2, where denotes the carrier frequency, and AST represents the complex valued time domain envelope, or equivalently, the representation of the signal. In the following, the signal processing steps are considered in the frequency domain, starting from the Fourier spectrum ASF of the signal. The incoming signal is first decomposed into a series of band-limited, frequency-interleaved signal slices, which are again represented via equivalent spectra AS, F, 12M as illustrated in Fig. 3.8. Note that neighboring signal slices exhibit a slight spectral overlap, indicated by the so-called overlap regions, OR in Fig. 3.8. The redundant information contained in the OR plays a crucial role for accurately compensating unavoidable amplitude mismatches and phase drifts between adjacent detection channels in the digital signal reconstruction. See discussion below and 28 for a more detailed explanation. The sliced tributary signals are then fed to an array of in-phase and quadrature receivers, IQR1, IQR2, IQRM for parallel coherent detection, using the spectral lines of a phase-locked optical frequency comb as multi-wavelength local oscillators low. The low tones are located at frequencies, where 12M align with the center frequencies of the respective signal slices AS1F, AS2F, ASMF, and are selected and isolated from a second optical 2 before being routed to the corresponding IQR. An electronic ADC array is finally used to digitize the IQR outputs, producing M-complex-valued signals U1, FU2, FUMF, from which the original waveform is reconstructed through dedicated digital signal processing (DSP) techniques. 3.3.1.2 Demonstrations. Slicing with adjustable slice width using a bank of cascaded Crow filters. The signal ASF is fed into the input bus waveguide input WG and sliced by 4 stages of Crow filters. Each stage consists of 3 rings with heating elements for thermal tuning and is coupled to its own output waveguides, output WG1, output WG4. The spectral widths of the individual signal slices can be flexibly adjusted by appropriate tuning of the first Crow filter red with respect to the edge of the signal spectrum gray, and by adjusting the center frequencies of all subsequent Crow filters according to the desired slice widths. Slicing is achieved by spectral overlap of the various filter passbands, such that spectral components that are not extracted by one Crow filter may be captured by the next one. Experimental results of a sliced OAWM system using silicon-photonic Crow filters. Amplitudes and phases of the measured frequency-dependent transfer functions. The amplitudes have been normalized to the maximum value obtained for the first slice. Reconstructed spectrum of a 100 Gbed 64 QAM signal, obtained through merging the signal slices by maximum ratio combining MRC. The ORs have widths of only 500 m small orange-colored regions, which is sufficient for signal reconstruction. The bandwidths of various slices are slightly different due to the non-uniform transfer characteristics of the Crow filters. See comparison of 100 Gbed optical data signals obtained by a single-slice single-polarization coherent receiver single, and by OAWM-based detection OAWM. The constellation signal-to-noise ratio CSNR for all 100 Gbed QAM signals is slightly better than that of the conventional single-slice receiver, while the requirements with respect to the electronic acquisition bandwidths of the individual ADC are greatly reduced. Figure adapted from 28. For an experimental demonstration, the Crow filters were fabricated on the silicon-photonic platform and subsequently packaged with both electrical and optical interfaces 28. The 4 low tones were derived from an optical frequency comb featuring a free spectral range FSR of 35 G generated by electro-optic modulation. For simplicity, the second optical 2 and the IQR array still relied on off-the-shelf fiber optic components. The frequency-dependent part of the transfer functions of the various detection paths were measured using the aforementioned one-time calibration method and are displayed in Fig. 3.1. To test the performance of our OAWM receiver, 100 Gbed optical communication signals with different modulation formats were used as test signals. An exemplary reconstructed signal obtained from 4 tributary signals is shown in Fig. 3.1b. In this case, the spectral widths of the 4 signal slices amount to 37.9 G, 32.26 G, 31.49 G, and 36.85 G, including the spectral overlap region to 1 slices 1 and 4, or to both slices 2 and 3 sides of the respective slice. This leads to an overall optical detection bandwidth of 140 G for the demonstrated OAWM system. To estimate the quality of the reconstructed signal, the results were compared to those obtained from a conventional high-speed coherent receiver. Figure 310C shows a comparison of the corresponding 16 QAM and 64 QAM constellation diagrams, along with the associated data-aided constellation signal-to-noise ratio (CSNR), obtained by using identical DSP algorithms in both cases. The results show that the OAWM receiver offers better signal quality for both 16 QAM and 64 QAM modulation formats, which can be attributed to less electronic noise being captured in each individual slice due to the fourfold reduced electronic bandwidth needed for the individual ADCs. Note that the scheme can be easily scaled to higher bandwidths by increasing the number of spectral slices. The use of an integrated silicon-photonic spectral slicer also represents an important step towards a fully integrated on-chip OAWM system that can be used in practical application scenarios outside well-controlled laboratory environment. 332 Non-Sliced Optical Arbitrary Waveform Measurement, OAWM. As shown in the previous subsection, sliced OAWM techniques can overcome the bandwidth limitation of conventional coherent detection schemes. However, chip-level integration of high-quality optical slicing filters is challenging and typically requires complex tuning procedures to achieve the desired performance. To overcome these challenges, a concept referred to as non-sliced OAWM has been proposed and demonstrated 35, as will be explained in the following. The non-slice scheme avoids optical slicing filters and instead relies on simple wavelength-agnostic power splitters and optical delay lines, components which are well suited for chip-level integration using high-index contrast platforms such as Silicon-Photonics 29. 3321 Concepts. Concept of non-sliced OAWM. A broadband optical input signal AS-theta with spectrum ASF and carrier frequency is split into N copies and fed to an array of in-phase and quadrature receivers, IQRs. The IQRs are also fed with delayed copies, delays 1, of a frequency comb that is used as a multi-wavelength local oscillator, LO. The simultaneous with all M low comb tones leads to a superposition of M spectral components in the complex valued signals UTT plus JT, 1, and that are extracted from the N IQRs. Spectral components within the overlap regions, OR, are by both adjacent low comb tones if the detection bandwidth B exceeds half the FSR of the low, BFFSR2. B starting from the spectra UF of the captured signals UT, the signal spectrum ASF is reconstructed in 3 steps. First, the superposition of the various spectral components labeled 1, 2, M in the measured spectra UFU1F is undone by multiplying the inverse transfer matrix H plus F with the measured spectra UFC. 3.1. The resulting signal vector ASSF comprises M spectral slices, which in a second step are frequency shifted according to the FSR of the low comb. Assuming BFFSR2, the resulting spectral slices are overlapping within the overlap regions, OR. In the third step, all spectral slices are combined according to 3.11, resulting in the reconstructed signal spectrum ASSF. Note that the signal reconstruction is sensitive to optical phase drifts between the various detection paths. These phase drifts are estimated and compensated by exploiting redundantly measured signal components in the overlap regions. See 35 for details. Figure 311 shows a conceptual setup for non-sliced OAWM. The incoming optical signal ST2 is again described by its optical carrier frequency and by the associated complex-valued time-domain envelope AST and its Fourier spectrum ASF. At the input of the OAWM system, the incoming signal is split into N copies by a wavelength-agnostic splitter. The various signal copies are then routed to an array of in-phase and quadrature receivers, IQRs, which are labeled by subscripts 1. These IQRs are also fed with copies of an optical frequency comb that undergo dedicated time delays and that serve as local oscillator low signals. These low signals comprise M comb tones at optical frequencies 1, M separated by a free spectral range FSR, FFSR. See the right-hand side of Fig. 3.11. Each IQR generates an in-phase signal T and a quadrature signal T at its outputs. These output signals are acquired by corresponding electrical ADCs and can be combined into a single complex-valued signal UTT plus JT, assuming that the frequency responses of the I and Q channel are identical and that both quadratures have an ideal 90-phase relationship. See supplementary document of 35 for a detailed discussion. Subsequently, digital signal processing (DSP) is used to reconstruct the spectrum ASF of the complex-valued envelope AST of the optical input signal from the n-measured complex-valued signals UT, Fig. 3.11b. Because the optical input signal with spectrum ASF is simultaneously by all m low-comb tones, each measured spectrum UF contains a superposition of m frequency-shifted copies ASF plus 1 m of the input spectrum ASF, where the frequency shift is dictated by the respective low-tone frequency, and where the detection bandwidth B is limited by the bandwidth of the IQRs and the ACs. Note that if the detection bandwidth B exceeds half of the FSR of the low-comb, BFFSR2, then spectral components of the input signal located in the overlap region OR appear twice in the measured spectrum UF, once at positive and once at negative frequencies Fig. 3.11b. This redundancy is exploited for estimating unknown system parameters, such as phase drifts in the optical fibers leading to the various IQRs. See 35 for a more detailed discussion. Note that the signal reconstruction relies on the precise knowledge of the transfer functions HF, which include the frequency responses of all system components in the signal path, e.g. optical waveguides, photodetectors, and ADCs. The various frequency-dependent transfer functions HF are determined once in a dedicated calibration measurement 2935. However, as explained above for the case of sliced OAWM, slowly time-variant optical phase drifts between the various detection paths lead to frequency-independent phase offsets of the various transfer functions and require additional phase estimation and compensation techniques 35. This is achieved by again exploiting redundant information that can be found in the complex-valued signals UF if the bandwidth B of the various detection channels exceeds half of the low-comb's FSR, BFFSR 235. More specifically, after recovering the signal vector components AS, STF, and applying the required frequency shift, the resulting spectral slices exhibit spectral overlap regions, OR, as illustrated in Fig. 3.11b, containing signal components that originate from the same spectral portion of the incoming signal. Unknown system parameters such as phase offsets can hence be found by minimizing amplitude and phase errors between the overlapping spectral components. See 35 and supplementary document thereof for a detailed discussion. It is also noteworthy that in the case of encomb with Fourier transform limited pulses, the architecture described in this section reduces to coherent sampling of a broadband signal with pulse trains to which different delays have been applied 36, 37, not so different from the electronic sampling architectures presented in Sect. 3.2 at an abstract level. This consideration also creates a basis for the analogies drawn in Sect. 3.4 in regard to this architecture. 3322 demonstrations. Experimental demonstration of the acquisition of a 610G test signal using non-sliced OAWM35. The acquired test signal comprises 7 QAM signals at symbol rates of 60 G bead and 80 G bead. All QAM signals are demodulated, and constellation signal-to-noise ratio (CSNR) levels between 18 dB and 21 dB are achieved. Note that the horizontal axis indicates the offset of the optical frequency f from a reference frequency 19252T, which was chosen to correspond to the lower frequency edge of the first spectral slice. Demonstration of non-sliced OAWM based on a compact silicon photonic PIC. A microscope image of the OAWM PIC comprising 2-2 and 2-4 multimode interference, MMI couplers as power splitters and 90 optical hybrids, respectively optical delay lines 1, 4, as well as IQ receivers IQR1, IQR4 based on germanium photodetectors. B-test signal comprising 264 QAM data channels, acquired using the 4-channel OAWM PIC shown in panel. See test signal acquired using a single-channel coherent receiver. Panels A and B are adapted from 29 under CC BY 40 license. A second demonstration exploits the amenability of non-sliced OAWM schemes to photonic integration and relies a compact 1.510 silicon photonic integrated circuit, PIC 2939. The PIC comprises cascaded 2-2 interference MMI couplers for splitting the signal in low into 4 paths, as well as 4 optical delay lines for the low 1, 2, 3, and 4 and 4 corresponding IQRs. Each IQR consists of a 2-4 MMI coupler that serves as a 90 optical hybrid and 2 balanced germanium-based photodetectors, see Fig. 3.13. The PIC was tested by contacting the photodetectors via a high-frequency probe and by recording the generated signals with high-bandwidth oscilloscopes, see 29 for details. All contacted photodetectors offered a 3 dB bandwidth of approximately 15 G and a 6 dB bandwidth of approximately 22 G29. The performance of the 4-channel OAWM PIC was demonstrated by acquiring a 160 G optical test signal that was synthesized by combining an 80 G bead and a 60 G bead 64 QAM signal. Figure 313b shows the reconstructed signal spectrum as well as the associated constellation diagrams. As a reference, the same test signal was measured using a single-channel IQ receiver that relies on 2 100G high-end balanced photodetectors, Fig. 3.13b. It was found that the OAWM system offers a better signal quality compared to the single-channel receiver because it relies on ADCs with lower bandwidth that offer a higher ENOB. 333 Photonic Electronic Analog to Digital Converter, PEADC. Combining OAWM systems with high-speed electro-optic modulators finally paves a path towards ultra-broadband ADCs. While BiCMOS or CMOS-based ADCs combine compactness and robustness with the inherent scalability of the underlying technology platforms, the acquisition bandwidths of these devices are limited to typically less than 60 G, with sampling rates of less than 200 G S40. The bandwidth of individual AG can be increased by electronic time domain or frequency domain multiplexing, leading to overall real-time acquisition bandwidths of up to 110 G with an effective number of bits ENOB of approximately 541. However, the bandwidth scalability of electronic demultiplexing schemes is limited by the analog multiplexer circuits and by the jitter of the associated RF oscillators too. Photonic electronic ADCs may overcome these limitations 2, 4, 34, 42, 43. In this section, we present an ultra-broadband photonic electronic AG based on the sliced OAWM technique described in Sect. 331 above. 3331 Concepts. A concept and sketch of the experimental setup of a photonic electronic AG that exploits sliced OAWM as a broadband signal acquisition technique. An external cavity laser, ECL, is used to generate the carrier for optical modulation and comb generation. Electro-optic conversion of the analog electrical input signal analog in is accomplished by a thin-film lithium TFLN Mach modulator MZM. Programmable optical filters WS are used for slicing of the resulting optical signal and the corresponding low comb, which is derived from an C3N4-based comb generator, FCG, FFSR 40025G4446. The 4 spectral slices are detected by an array of optical IQ receivers, IQR1, IQR4, which comprise 90 optical hybrids, OH, and balanced photodetectors, BPD. The overall 8 BPD are read out by 8 synchronized ADC channels. A fiber grating FBG is used to suppress the remaining pump tone after the FCG, and erbium-doped fiber amplifiers, EDFA, help to overcome the optical losses in the setup. B spectrum of the single soliton come along with a zoom-in of the selected low tones. Note that the lower sideband of the signal spectrum was detected in the experiment due to the slightly better optical carrier-to-noise ratio, OCNR, of the comb tones, while the spectral scheme in C illustrates the case of upper sideband detection for easier understanding. See illustration of the sliced photonic electronic AG in the spectral domain, a broadband electrical input signal. B resulting optical signal, generated by modulating the broadband electrical input signal onto an optical carrier, prior to slicing into M tributaries by WS1. See sliced signal tributaries with small overlap regions, OR, between neighboring slices, generated at the output of WS1. D spectrum of the frequency, comb prior to slicing by WS2. The selected tones are color-coded according to the corresponding signal slices. E reconstructed spectrum of the electrical input signal, obtained by merging the M spectral slices in the digital domain. Figure adapted from 34 under CC BY 4 license. The concept of the experimental setup of the photonic-electronic ADC is illustrated in Fig. 3.14a. For conversion of the analog electrical input signal analog in, a high-speed thin-film lithium TFLN MZM biased at the zero transmission point is exploited. The TFLN MZM can handle high optical powers and can reach 3 dB bandwidths beyond 100 G, while still showing a reasonable modulation response well beyond 300 G 47-48. To accurately measure and reconstruct broadband electrical input signals, the electro-optic EO response of the MZM must be compensated for. To this end, sinusoidal signals with known RF powers and frequencies up to 320 G are fed to the MZM, and the EO response can be obtained by dividing the optical sideband power by the known RF input power. See Supplementary Information, SI, of reference 34 for a detailed discussion. For simplicity, we use discrete fiber optic components such as a programmable wave shaper, WS, for spectral slicing to implement the OAWM subsystem. The multi-wavelength low for parallel coherent detection is provided by a soliton with an FSR of FFSR 4025G, derived from an C3N4-based chip-scale soliton 4446. Such combs can easily provide hundreds of phase-locked comb lines while featuring ultra-low timing jitter. The spectrum of the generated comb and a zoom-in of the selected low tones used for the experiment are shown in Fig. 3.14b. The frequency domain signal stitching scheme is illustrated in Fig. 3.14c, in which electrical and optical signal spectra that occur in the architecture concept shown in Fig. 3.14 are color-coded to illustrate how they correspond to each other. Note that the same external cavity laser, ECL, provides the carrier for the MZM and the pump for the C3N4 comb generator such that phase noise of the signal and of the low essentially cancel. Since the spectral width of each optical signal slice corresponds to twice the native FSR/FFSR of the comb, only every second tone positioned in the center of a slice at frequency F1, F3, F2M1 is used as in low tone for coherent reception. This ensures signal acquisition from DC to an upper frequency of 2 FFSR-M for the implementation with M for spectral slices, along with a comb FSR of FFSR 4025G. An acquisition bandwidth of 320 G in the first band can be achieved, corresponding to an effective sampling rate of at least 640 G S3332 demonstrations. Experimental results of a sliced photonic-electronic ADC. A digitized sinusoidal test signals at frequencies of 56 G, 280.8 G, and 307.8 G. Green circles, sampling points. Red curve, least squares fit of a sinusoidal model function. Blue dots only in 2 graphs, interpolated sampling points. The deviations of the interpolated points from the sinusoidal fits are minute, underlining the quality of the reconstructed waveforms. B. Digitized broadband electronic signal. The electronic signal comprises 3 QAM data signals, centered at carrier frequencies 24.4 G, 30 G bead 32 QAM, 233.4 G, 40 G bead QPSK, and 264.4 G, 10 G bead 16 QAM. From the digital representation indicated by horizontal braces, 3 constellation diagrams can be extracted. In the empty region, clock tones from the real-time oscilloscope are visible. In the middle of the empty overlap regions, stitching tones, orange, help to adjust the phases of neighboring slices. Figure adapted from 34 under CC BY 4 license. Offering the full bandwidth of 320 G in the first band is key to the acquisition of broadband test signals. In a second experiment, the Photonic-Electronic ACK was used to acquire a broadband data signal, consisting of a 30 Gbps 32 QAM waveform centered at 24.4 G, a 40 Gbps QPSK waveform centered at 233.4 G, and a 10 Gbps 16 QAM waveform centered at 264.4 G. Figure 315b shows the spectrum of the reconstructed signal, along with the constellation diagrams of the data signals extracted by applying state-of-the-art DSP techniques to the digitized signal. The constellation signal-to-noise ratio (CSNR) of the 30 Gbps, 40 Gbps, and 10 Gbps data signals amount to 18.1 dB, 12.3 dB, and 18.9 dB, respectively. By increasing the number of slices and by exploiting highly stable optical frequency combs with ultra-low phase noise 49, our concept may open a path to acquisition bandwidths in the order of 1 T using a fully integrated photonic-electronic system 28. 3.4 Optical with built-in equalization. As an outlook for the systems explored above, we are giving a brief introduction to an architecture expanding the concept of the filterless OAWM described in SECT. 332 to a configuration aimed specifically at an equalization of a broadband signal generated by a co-designed transmitter. A more detailed analysis including optical power budget, fabrication tolerance, and comb source requirement analyses can be found in 6.7. Architecture of the optical link with built-in optical. Then B. Architecture. The time domain diagrams represent the initial pulse train, left diagram in as well as the pulse trains in the upper and lower branches of the AND, respectively. Circles indicate optical delay loops in units of 0. Reproduced under CCBY and C4 from 7. In the combined signal is fed through an unbalanced interferometer that allows recovering every 1N sample, i.e. that already implements in the optical domain. In the specific example shown in Fig. 3.16, this demodulator recovers the pulses that have been delayed by 3.0. The other signal samples can be retrieved by splitting the light 4 ways, N ways, after uncoupling in the PIC and sending it to 3. N1 more such demodulators, in which the number of delay loops in the top interferometer branch has been modified to 1, 1 plus 3, and 1 plus 6. The functioning principle of the demodulator in Fig. 3.16b can be understood by considering the modulated pulse train to follow the upper branch of the interferometer and the reference pulse train to follow its low branch. The first delay 0 in the upper branch applies to the modulated pulses the same time delay already applied to the reference pulse in the transmitter. The following delays further shift the modulated pulses by multiples of 3.0 and select which of the N interleaved pulse trains are synchronized with the reference pulse and demodulated. The DCS at the end of the interferometer and the following BPD detect the phase difference between the modulated and reference pulse. Of course, the modulated signal also follows the lower branch and the reference signal the upper branch. These paths do not, however, result in a differential signal at the output of the interferometer, as they result in timing in which the modulated and reference pulses continue to occupy different time slots. These do result, however, in a 3 dB optical power budget penalty, as the corresponding light is lost to signal demodulation. Other sources of power loss are the pulse interleaver in the, as represented in Fig. 3.16, but this is a schematic used to facilitate the discussion. Since the pulse interleaver is not required to truly increase the FSR, as the interleaved pulses are not required to have constant phases, this operation can also be done in a lossless manner, for example with a lattice filter 7. The combination of the modulated and reference pulse trains at the end of the also results in 3 dB losses, but these are offset by the differential detection at the, and are the price to pay to transport both through the same fiber. As a final processing step, the architecture relies on the ADC in the to digitize the differential photocurrent after integrating it over 1 mLL pulse repetition time and could, for example, also have its reset function triggered by a properly delayed mLL pulse train, as in SECT. 321 to keep the system synchronous. As for the scheme described in SECT. 332, this architecture does not actually require the pulses to be, and also works in the general case in which the phases between the comb lines are random but locked in slowly varying 6. Another advantage of using the comb both as a carrier on which the signal is modulated and as a reference for demodulation, as opposed to using a single frequency carrier for the former, is that no DSP processing is required to compensate for these phases. This is also taken care of by the demodulator shown in Fig. 3.16b. An extension of the receiver architecture consists in replacing the fixed delays in the upper branch that are in excess of the first one, i.e. the 9 delay loops in Fig. 3.16b by a lattice filter 51 as shown in Fig. 3.17a. This device is configured as a programmable delay line or programmable pulse shaper (PPS) that provides optical paths with delays 0, 30, 60, and 90 with programmable phases and weights. This allows not only to select which of the interleaved pulse trains is demodulated, but also to detect a weighted superposition of the corresponding samples, which we have applied to equalization of intersymbol interference (ISI) in a numerical model of the network. An architecture of a lattice filter used as a programmable delay line in the upper branch of the demodulator for dynamic channel and optical equalization. Histograms of the recovered signal samples with B, fixed demodulator delays, and C, a trained lattice filter. Reproduced under CCBY and C4 from 7. 3.5 Conclusions. Assisted analog-to-digital converters that leverage the low jitter of best-of-class mode-locked lasers and break down broadband signals into multiple lower-speed tributaries allow surpassing the performance limits of all electronic data converters, increasing both the ENOB by means of lower aperture jitter and increasing the optical signal bandwidth that is in reach of digitization. We have reviewed our work on both time and frequency domain approaches and given an outlook on how these architectures can be further extended to include additional signal processing tasks such as equalization. Optically triggered track-and-hold amplifiers with an equivalent jitter below 80 in a signal frequency range from 20 G to 70 G have been reported, which represent a significant advance over the current state of the art. Frequency domain architectures implementing optical arbitrary waveform measurement up to signal bandwidths of 610 G have also been experimentally shown, with systems integrated at the chip scale digitizing signals with bandwidths up to 160 G. The quality of recovered constellation diagrams has been benchmarked against that obtained from commercial broadband receivers and shown to surpass the latter. By combining this OAWM scheme with broadband electro-optic conversion by means of the thin-film lithium modulator, a complete AG with a record acquisition bandwidth of 320 G has been shown. Extension of digitization to further functionalities, such as equalization, can be done at little hardware overhead once optics have been introduced in the signal processing chain and open a path for further offloading of the electronic requirements. As baud rates continue to grow beyond 100 G bead in commercial systems, such signal processing schemes may increasingly come into focus to enable further scaling. The authors would like to acknowledge funding from the German Research Foundation, DFG, for Project Ultra Assisted Analog-to-Digital Converters, 403,188,360, in the framework for the Priority 2111 Electronic-Photonic Integrated Systems for Signal Processing, as well as from the German Federal Ministry for Research and Education for Project Scalable Photonic Circuits. Grant 3 ZU1106BA, in the framework of the Cluster for Future. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1N-RT 2015. Practical implementation of 100S lambda optical short-reach transceiver with PAM4 signaling using modulated laser EML. In Proceedings of the Optical Fiber Communication Conference. Art. ID 3A2. 2A Spectre SJ Grain ME AH CW Sandermai MS Pengmai MW Na JU AJS JP CM MA Sunj Jo GR HJ JL Smith HI Ram RJ MTM EP FX 2012 Photonic ADC Overcoming the Bottleneck of Electronic Jitter. OptExpress 244544469. 3AJJG FX 2012 Optical Flywheels with Jitter. 697-100. 4AJSP FangD JCC J 2020 Fundamental Limitations of Sliced Optically Enabled Data Converters Arising from MLL Timing Jitter. OptExpress 2813-18790-18813. 5AWLT MAN-YG 2011 Optical Fiber Pulse Rate Multiplier for Phase Noise Signal Generation. Opt 3636543656. 6A does AD-L-R J 2024 Scalable Orthogonal Delay Division Multiplexed OEO Artificial Neural Network Trained for TADC Equalization. Photonics Raise 1280-5105. 7A J 2024 Chip-to-Chip Orthogonal Delay Division Multiplex Network with Optically Enabled Equalization. J-Light Technol 42-793-77953. 8M-YT 1990 Jitter Analysis of High-Speed Sampling Systems. IAAE J Solid State Circuits 25-12-22-24. 9J F 2010 Precision Photonics. Laser and Photonics Rev 43-432-456. 10M JC 2021 A 220G phase noise signal source using a microwave oscillator locked to a mode-locked laser. IAEE Trans Theory Tech 69-3-1635-1645. 11 Van K SV SG EB 2019 Recent Advances in the Photonic Integration of Mode-Locked Laser Diodes. IAAE Photonics Technol 30-123-1870-1873. 12J AF J 2019 Semiconductor Laser Mode Locking Stabilization with Optical Feedback from a Silicon PIC. J-Light Technol 30-734-833-494. 13 Ha A 1993 Noise of Mode-Locked Lasers. J Quantum Electron 29-983-996. 14 FX Sing N 2019 Integrated CMOS-compatible mode-locked lasers and their optoelectronic applications. In 2019 IEAE BiCMOS and Compound Semiconductor Integrated Circuits and Technology Symposium, BCICTS. 15 DA-N A 2018 Understanding Jitter and Phase Noise, A Circuits and Systems Perspective. Cambridge University Press. 16 AJIM GMJCW 2022 CN Pulse Interleaver for Optically Enabled Analog-to-Digital Conversion, a Device-to-System Analysis with Cyclic Equalization. OptExpress 34-4444466. 17M FX J JC 2020 Photonic Analog-to-Digital Converters, Comparison of MZM Sampler with an Optoelectronic Switch-to-Emitter Follower Sampler. In 21st ITG Symposium on Photonic Networks, 119-124. 18M JC FX J 2021 Optically Clocked Switch-to-Emitter Follower THA in a Photonic C/CMOS technology. OptExpress 29-16312-16322. 19A J M J FangD A does ADD F FX SC JC J 2021 Optically Enabled ADCs and Application to Optical Communications. IEAE OpenJ Solid State Circuits SOC 12-09221. 20B ADC Performance Survey 1997-2024. Online ComAdC Survey 21T CSM HJC 2025 Forward Biased Silicon Phase Shifter Modeling for Electronic-Photonic Co-Simulation and Validation in a 250 EPIC BiCMOS Technology. J-Light Technol 43-1255-270. 22M Fard S.B. JC 2020 wideband frequency synthesizer with ultra-low phase noise using an optical clock source. In 2020 IAIE MTTS International Microwave Symposium, IMS 12831286. 23 IEEE Standard for Terminology and Test Methods for Analog to Digital Converters. IAIE 12412023, revision of IEEE 12412010, 2023. 24J AG, A does AD, F, J 2021, optimized hourglass-shaped resonators for efficient thermal tuning of Crow filters with reduced crosstalk. In Proceedings of the 17th IEEE International Conference on Group IV Photonics, GFP. 25 in K, RP Joe L. Soars FM Heritage JP, SJB 2010, Real-Time Full-Field Arbitrary Optical Waveform Measurement. Photonics 442-48254. 26 Dr. Roper C. P. B. 2007 Optical Rogue Waves. Nature 457 17210, 541057. 27 NK G Guan B A PJ R A F JY Bool LL S R P A 2012 228 G coherent receiver using digital optical bandwidth interleaving and reception of 214 G bead 856 S PDMQPSK. In European Conference and Exhibition on Optical Communication. ART ID 3A1. 28 Fang D A J D C P A T does A D M S W S J C J C 2022 Optical Arbitrary Waveform Measurement OAWM using silicon photonic slicing filters. J Light Technol 46 170 1717. 29D Fang D C W S C 2024 Non-Sliced Optical Arbitrary Waveform Measurement OAWM using a silicon photonic receiver chip. J-Light Technol 42, 1447334750. 30D AL 2025, a transmission of 300 G-bead QAM signals over transoceanic distances using optical arbitrary waveform generation and measurement, OAWG-OAWM. J-Light Techno 4313, 63496360. Org 101109 JLT 202 535799802. 31D Fang D AL 2025 B Optical Arbitrary Waveform Generation OAWG using actively phase stabilized spectral stitching. Light 14353. Org 101038 S4137702 50193774. 32R Chin C Guan B NK S Castro A RP SJB 2016 Elastic Optical Networking by Dynamic Optical Arbitrary Waveform Generation and Measurement. J Opt 87A171 A179. 33L Castro A M G Chin C R SJB 2017 Meeting the Requirements to Deploy Cloud RAN over Optical Networks. J Opt 93B22 B32. 34 Fang D D Peng HG C A P P R N J M J J C W S T J C 2025 320G Photonic Electronic to Digital Converter ADC exploiting soliton. Light and 14. ART ID 241. 35D Fang D C G T Y Peng HPT W TJ SC 2023 Non-Sliced Optical Arbitrary Waveform Measurement OAWM using soliton. 107888 36X X I Li G H Joby 2009 Coherent Detection using Optical Time Domain Sampling. IAAE Photonics Technol 215286288. 37JK Ludwig R. L. C. CC. AC 2011 High-Speed Digital Coherent Receiver based on Parallel Optical Sampling. J-Light Technol 29 4378385. 38D Fang D C G T Y Peng HPT W TJ SC 2022 Sliceless Optical Arbitrary Waveform Measurement OAWM in a bandwidth of more than 600 G. In Optical Fiber Communications Conference. ART ID M2I1. 39D Fang DC AWSC 2022 Sliceless Optical Arbitrary Waveform Measurement OAWM on a Silicon Photonic Chip. In European Conference on Optical Communication. ART ID We4E6 40 RL AAA Fan A B C C D F F G Hatcher G M M M Fan N P Fan S Ho S T Wu T W Sun Z SL 2024 18.4 200 GSS 8B20 FJCS receiver with 60 G AFE bandwidth for 800S optical coherent communications in 5 FinFET. In IAEE International Solid State Circuits Conference 344-346. 41 UXR Series Oscilloscopes Data Sheets. Online. Commas N Assets 701-806242. Data Sheets 599233132. 42C Z 2022. Frequency Interleaving Dual Com Photonic ADC with 7 bits ENOB up to 40G. In Conference on Lasers and Electro-Optics, CLEO. ART. ID S5M1. 43 Valley GC 2007. Photonic Analog to Digital Converters. OptExpress 15519551982. 44 Hair T V JD CY NM ML TJ 2014 Temporal Solitons in Optical. Photonics 82145-152. 45 TJ AL M ML 2018 Dissipative Solitons in Optical. Science 361-6402. ART. ID 8083. 46 Shenbi LJH Yang QF Xiang CRN HJ TWJD Wu L QX TJ K Bowers JA 2020 Integrated Turnkey Soliton. Nature 582, 7812 365 369. 47 AJ S Yao P L RM DW 2018 Thin Film Lithium Electro-Optic Modulator with Operating Bandwidth. OptExpress 2611-14810-14816. 48Y L Yang J Z K KM DCH M C 2022 Systematic Investigation of Millimeter Wave Optic Modulation Performance in Thin Film Lithium. Photonics Raise 1010-2380-2387. 49J E Raja ASEJ JRN M H R TJ 2020 Photonic Microwave Generation in the X and K band using Integrated Soliton. Photonics 14-8486-491. 50 MI J Y Sinke Mandel P AH T 2023 Orthogonal Sampling-Based Broadband Signal Generation with Low Bandwidth Electronics. IAIA Open J SOCH 429302938. 51 M W PM 2004 Adaptive Distortion Compensation with Integrated Optical Finite Impulse Response Filters in High Optical Communication Systems. J-Top Quantum Electron 10-2-73280. 4. Precise Optical Pulse Synthesizer Digital to Analog Converter. Abstract. Optically Assisted Digital to Analog Converters, DACs, using pulse sequences NPSs, are presented and investigated. Therefore, NPSs are mathematically described and analyzed. Based on this, the operating principle of a precise optical pulse synthesizer digital to analog converter, DAC, is described. Possible architectures of DAC are derived and compared in terms of performance and practicability. Moreover, the limits of DAC systems and their superiority over classical electronic DACs are discussed. Furthermore, discrete building block-based implementations and monolithic implementations in electronic-photonic integrated circuits, EPICs, are presented. To enable a practicable monolithic integration, a shrinkage of the Mach modulators, MZMs, has been performed by applying forward-biased phase shifters, FBPSs. These FBPSs are analyzed and modeled to allow the precise and reliable design of DAC systems with multiple MZMs. Finally, data conversion and data transmission experiments are carried out to demonstrate the system's functionality, quantify its performance, and prove their superiority over purely electronic DACs. Acronyms: Arbitrary Waveform Generator, bipolar and complementary metal oxide semiconductor transistor. Bandwidth, complementary metal oxide semiconductor transistor. Continuous wave, digital to analog converter. Depletion type phase shifter. Emitter follower. Effective number of bits. Enhancement type phase shifter. Extinction ratio. Electronic-Photonic integrated circuit. Forward biased phase shifter. Free carrier plasma dispersion effect. Lithium. Mach modulator. Pulse sequence. Non-return to zero. Optical frequency comb. Optical spectrum analyzer. Pulse amplitude modulation. Precise optical pulse synthesizer digital to analog converter. Pseudorandom binary sequence. Phase shifter. Relative intensity noise. Silicon. Signal to noise and distortion ratio. Space charge region. Segment driver. Signal to noise ratio. Transmission line. Traveling wave electrode. 4.1 Introduction. DACs are important components bridging between the digital and analog domains, enabling the conversion of discrete digital signals into continuous analog signals. They are essential in a variety of systems, such as audio and video processing, digital control circuits, measurement, and communication systems. As the demands on modern electronic systems increase in all these application fields, so does the need for ever more powerful and precise converters. DACs are often designed at the limit of the respective applied technology, but higher precisions are still desired and required. To meet these requirements, assisted DACs, such as the DAC, can be used, as they enable system bandwidths, BWs, that are multiple times higher than the BW of the applied electrical and optical components. Using optical NPSs, multiple digital input signals can be modulated onto an optical carrier in different channels and combined afterwards, resulting into very high BW and precision. In the following, the DAC system is presented and analyzed. First, the fundamental operational principle of the DAC is explained, and an overview on possible topologies is given. The advantages and disadvantages of possible architectures are discussed and evaluated. Afterwards, epic implementations of the DAC channels are presented, and different applicable modulator types are compared. Experimental results are presented, which prove the overall system functionality and applicability. Moreover, theoretical works based on those results are presented, which prove that the DAC system is able to overcome limits of today's state-of-the-art electrical DACs. Finally, a conclusion is given, which summarizes all investigations and results. 4.2 Topologies of electro-optical DACs. A pulse in time domain B pulse frequency spectrum C NPS in time domain N9, D NPS frequency spectrum N9. DAC building blocks. As presented in Fig. 4.2, the DAC consists of three parts. In a first step, NPSs are generated in multiple channels. To ensure and fault-free superposition in the last building block, these NPSs are delayed against each other. Afterwards, these pulse sequences are weighted according to electronic digital input signals within multiple channels. At last, all channels' signals are combined, and the optical signal is converted to the electronic domain. Within the different DAC topologies, presented in the following subsections, only the first building block differs. In both presented topologies, a rectangular optical frequency comb, OFC, is generated in the first building block. This OFC corresponds to the shaped NPS in the time domain, as illustrated in Fig. 4.1d for an NPS with 9 frequency lines, N9. A significant advantage of pulse sequences is that they can be generated by one or more cascaded modulators, offering control over BW and repetition rates while supporting integration within a photonic platform. This technique yields NPSs of superior quality, as the resulting OFC can be ideally flat and rectangular. Moreover, the generated pulse BW can reach 3 to 4 times the electro-optical BW of the modulators used too. The generation of pulse sequences with modulators provides a crucial advantage, as this pulse synthesizer modulator can be integrated into a silicon-C photonic platform, making the complete photonic DAC concept complementary metal oxide semiconductor transistor, CMOS, compatible. The first experimental demonstration of pulse sequence generation was presented in 2, with benchtop lithium Li-O3 modulators. In 3, an integrated MZM generated pulse sequences for optical sampling applications. In a follow-up study, the BW bottleneck of the modulators was overcome by driving a 19G3 dB BW integrated modulator with a 30G signal to generate high-quality pulse sequences of 90G BW4. Once the frequency synthesis has been established, the DAC system can be implemented in 2 different ways, for example in an available C photonics platform. The first option is to apply a single pulse generator and use optical delay lines for pulse alignment, named photonic DAC with single pulse synthesizer, and the second option applies multiple NPS generators aligned with electrical tuning and termed as photonic DAC with multiple pulse synthesizers. In the following section, the complete working principles of the 2 implementations and their advantages are discussed. 421 photonic DAC with single pulse synthesizer. 3-channel photonic DAC with single pulse synthesizer. Afterwards, the output of the first modulator is split into multiple channels. Since the proposed concept relies on the generated NPSs in each channel, the pulses need to be aligned orthogonal to each other. For the pulse alignment, optical delay lines with specific individual delays for each channel need to be incorporated. The input of each channel has to be delayed by 360 n to each other, which corresponds to a time delay of 1 n, with n being the amount of channels, and the modulation frequency applied to the input MZMs in the NPS's synthesis. Thus, in the 3-channel N3 example shown in Fig. 4.3, the first channel with no optical delay, 10, acts as a reference point for the other channels, which require time delays of 213.1 and 323.1, respectively. Depending on the comb spacing, as defined by the NPS's synthesis frequency, these delay lines with specific delays and thermal tuning need to be designed. This is one of the major limitations on the acceptable range of the frequency, which directly limits the overall sampling rate of the photonic DAC. In all channels, the delayed pulses align orthogonal to each other, which means that the peak of the NPSs in one channel aligns with the zero crossing of the pulses in the other channels. This plays an important role in preserving each data point of the resulting signal generated with the photonic DAC. In the next step, the NPSs are weighted according to electronic digital input data. Therefore, low BW electronic DACs generate data signals, which are fed to the MZMs in each channel. Each of these signals carries 1 n of the information of the targeted analog output waveform. By means of additional MZMs, the data points are transferred into the optical domain, defining the peak of the NPS in each channel. Afterwards, the sampled NPSs are combined and converted into electronic domain using a photodiode. Thereby, a high BW signal with a sampling rate of n times the electronic BW of the MZMs in each channel is generated. For example, in a 3-channel N3 system, the pulses with a repetition rate are weighted by data signals with a sampling rate of, resulting in an overall signal of sampling rate FS3. The described prototype employs CMOS-compatible components that can be easily integrated into any C photonic platform. The tuning range and achievable BW of the system are defined by the generated pulses and the optical delay lines. At higher BWs, it is quite challenging to have precisely aligned optical delays with on-chip delay lines, and they are more sensitive to thermal crosstalk. However, this type of implementation has the advantage that the number of modulators required only increases with n plus log 3n, when the number of channels n is increased. In the next section, the concept is upgraded with electronically tunable delays, which provide more flexibility and for the system. 422 photonic DAC with multiple pulse synthesizers. 3-channel photonic DAC with multiple pulse synthesizers. A DAC system with 3 channels and multiple pulse synthesis is shown in Fig. 4.4. The overall design consists of N1 plus log 3N MZMs, leading to 2 more MZMs in a 3-channel system than in the previous design. However, no optical delay lines are required, and the optical alignment of the pulses is carried out with electrical phase shifters, PSs, allowing flexible tuning of phase shifts and therefore also flexible modulation frequencies. The laser output is split into multiple channels, each of them consisting of MZMs for NPS generation and optical alignment, and an MZM to weight the pulses. The pulse alignment is done via phase shifts between the electrical input signals of the NPS generation MZMs. Therefore, the required electrical PSs can easily be integrated in epochs in a tunable and area-efficient manner. This provides a great advantage in terms of range and of the output frequency of the generated signals. 4.3 Epoch implementations in silicon technology. A MZM and B FCPDC PS geometry. 4.3.1 Epoch implementations with depletion-type modulators. Depletion-type phase shifters, DTPSs, are widely used in modern C photonic electro-optical transmitters 7. In DTPS, the junction is operated in reverse bias condition, VPS0, and a space charge region SCR with voltage-dependent width WSCR VPS is built C Fig. 4.6 Inside the SCR, the C is depleted, leading to reduced free charge carriers interacting with the electrical field of the optical signal. Thus, according to 4.3 and 4.7, the phase shift is electrically controlled by the applied PS voltage VPS. DTPS a illustration with SCR-B small signal equivalent circuit. Velocity matching can be achieved by careful TL design with adaptation, which is, due to technology restrictions with given metal stacks, only possible to a limited extent, or by meandering the TL, which is effectively decreasing the electrical velocity. 2 different driving schemes can be applied to connect the PS driver, the TL and the DTPS. In the directly driven traveling wave electrode TWE scheme, which is shown in Fig. 4.7 the TL is directly connected to the DTPS, which causes significant drawbacks because the TL is directly loaded by the DTPS capacitance. Therefrom, the characteristic impedance Z0 L0 C0 plus CL and the electrical propagation delay L0 C0 plus CL are strongly affected. 11. Since the capacitive load is nonlinear, c. 4.9 and changes during operation, permanent conjugate load matching between the driver and the TL is not possible, leading to reduced efficiency. Additionally, the large load capacitance causes microwave losses and reduces the BW8. Depletion-type MZM driving schemes a directly driven TWE BSD. Chip picture of the fabricated Epoch MZM8. Cross-section of the slow-wave TL8. Circuits of the implemented DTPS-based electro-optical transmitter 8, a input driver BSD. In same manner, the SD is designed. As illustrated in Fig. 4.1b, an EF input stage with low output resistance and high input resistance to reduce loading of the TL drives a peaked amplifier. In addition, capacitors are inserted to compensate the input referred capacitance of the SD. Moreover, EF output stages are added to increase the driving capability of the SD and reduce the BW reduction due to the PS capacitance. Measured and simulated S21 electro-optical response of Epoch MZM with external 70G photodiode 8. Measured I diagrams in data transmission experiment 8, a 60S NRZ B80 SPAM4. 432 Epoch implementations with enhancement type modulators. ETPS a illustration with SCR-B equivalent circuit 6. ETPS-based MZM with passive RC equalizer, a block diagram B frequency response for different RC sizings, substrate capacitance and contact inductance neglected, 6C small signal equivalent circuit. Using ETPSs in conjunction with equalizer structures, allows similar characteristics as DTPS MZMs at much smaller footprint. Therefore, ETPSs enable much more complex photonic systems with multiple MZMs, such as the DAC system in one epoch. ETPS-based MZM measurements an electro-optical S31 parameter at different equalizer capacitances, dotted, measured solid, simulated BI diagram measured at 50s data rate in NRZ modulation scheme, 100 MV div 4 div. 4.4 Theoretical investigations on the DAC performance. Considered distortions and noise sources in the DAC system 19. 4.5 Experimental results. 451 NPS generation. 9-line comb NPS generation with cascaded MZMs 23. Measured 60 GBW, a 3-line frequency comb B NPS in time domain. 3-line frequency comb with a 90 GBW and B 120 GBW. Measured optical spectra 23, a 63 GB 81 G C99 G. These results prove that the C-based epoch implementations are also suitable for 9-channel DAC systems, and optical BWs of nearly 100 G can be reached. 452 DAC simulation and experiment results. The proposed DAC concept was simulated using the system software package. The simulation setup mirrored the conceptual design, where each channel included 2 modulators, as illustrated in Fig. 1.3. The objective was to generate a 307-bit pseudorandom binary sequence, PRBS, data signal using low-speed electronic and photonic components. A CW laser operating at a wavelength of 1550 and an optical power of 10D served as the optical source. Its output was divided into 3 branches using a power splitter. In each branch, the first MZM was driven by a 100 G sinusoidal signal to generate shaped pulse sequences, following the same approach previously demonstrated using the C modulator. This resulted in a 3-line frequency comb with 100 G spacing between spectral lines, corresponding to a 300 G NPS. The second MZM in each branch was used to modulate these pulses with predefined 100 shaped data patterns. These data patterns were BW limited to 50 G in the frequency domain to prevent spectral overlap when convolved with the 3-line frequency comb. Accordingly, the first modulator required a BW of 100 G, while the second modulator needed a BW of 50 G. To generate the targeted 300 S-bit sequence, every third bit from the original sequence was selected to create predefined data patterns suitable for generation using arbitrary waveform generators, AWGs, operating at a 100 GSS sampling rate. In the first branch, the predefined data sequence was with the shaped pulse sequence in the time domain. Similarly, in the second and third branches, the pulses generated by the first modulators, which are having the same BW, were weighted with data patterns derived from the second and third bits of the original sequence, respectively. This approach effectively distributed the high-speed data across 3 parallel lower-speed channels. 300 SNRZ PRBS 7 pattern filtered with a 300 G rectangular filter, blue. The red curve shows the generated 300 SNRZ PRBS 7 data pattern using the DAC with only 100 G electronics and photonics, 24. I diagram for the generated a 2-level and B4-level 300S signal generated by using the 3-channel DAC-24. For experimental validation, the DAC concept setup illustrated in Fig. 4.4 was implemented using commercially available fiber optic components, as the proposed epoch was still undergoing fabrication. To ensure stable power levels during the measurement of high BW signals, the original configuration, consisting of a single light source and a 1-3 optical combiner, was modified by employing 3 separate laser sources, as described in 25. Each branch of the system included an MZM driven by a 10G signal, which produced a 30G NPS, as previously discussed. These pulse sequences were time-aligned and multiplexed to form 3 orthogonal pulses. The combined output resulted in a flattened waveform, as depicted in Fig. 4.23. The slight ripples observed in the otherwise flat waveform are attributed to minor power mismatches among the branches. Such inconsistencies are expected to be eliminated in a fully integrated C-photonics prototype. The blue line illustrates the combined output of time-shifted orthogonal pulses from 3 channels, as depicted in A. When these pulses are appropriately weighted and superimposed, they form a 15G sinusoidal waveform, shown in black in B. This result is compared against the theoretical sum of the weighted pulses across all 3 channels, shown in red in B. Consequently, with 3 branches and modulators driven at 20G, the system achieves an effective sampling rate of 30 GS/S25. The individual amplitudes of the 3 branches are shown in black, green, and orange, while their combined output is depicted in blue. The superposition of the 3 channels results in a 15G sinusoidal waveform, with its corresponding electrical spectrum shown in B. By adjusting the amplitude of the weighting signals, additional arbitrary waveforms were generated, as illustrated in C and D26. To emulate the second and third branches of the DAC architecture, the phase of the signal generator was shifted by 120 and 240 degrees, respectively. The outputs from all 3 branches were mathematically combined to generate the waveforms shown in Fig. 4.24. A 15G sinusoidal waveform was produced, as illustrated in Fig. 4.24. The individual outputs from the 3 branches are displayed in black, green, and orange, while their summed result is shown in blue. The corresponding electrical spectrum is presented in Fig. 4.24b, exhibiting a signal-to-noise ratio, SNR, of 32.7 dB. Additionally, a sawtooth waveform was generated by modifying the amplitude of the data signal used to weight the pulses in MZM2, as shown in Fig. 4.24c. Due to the use of only 3 branches, the resulting ramp waveform does not exhibit a perfectly linear slope. A partial implementation of the proposed DAC concept, based on the time-interleaved superposition of weighted pulse sequences, has been demonstrated using 2 modulators integrated on an epoch. Through mathematical post-processing of each channel, the system successfully generates arbitrary waveforms at an effective sampling rate 3 times higher than the modulation rate. To achieve even higher sampling rates, either faster modulators would have to be used or the number of channels would have to be increased. However, the latter would require either large chip areas with the associated costs or miniaturized modulators, such as the forward-biased modulators investigated and presented in SECT. 4.32. Considering available high-speed integrated modulators with BWs beyond 100G27, 28, and appropriate electronic drivers, this architecture has the potential to achieve sampling rates of up to 300 GSS. However, the driving limitation is again defined by the electronic signal and waveform generators. A fully integrated solution would offer low timing jitter and enhanced in the electrical domain, making it a promising candidate to overcome the BW limitations of current state-of-the-art communication systems. 4.6 Conclusion. A new concept of a photonic electronic DAC has been presented and investigated. 2 possible topologies have been found and compared to each other. The topology of a DAC with multiple pulse synthesizers allows higher flexibility at the costs of an increased amount of MZMs required to realize the system, compared to DACs with single pulse synthesizers. Moreover, 2 MZM types have been designed, investigated, and applied in epoch technology. Respecting the size of the DAC system, ETPS-based MZMs fits well to the overall system. Therefore, ETPSs have been modeled and equalizer circuits have been applied to the PS, increasing the BW and raised to DTPS performance levels at very much decreased size. 3 and 9-line NPSs have been generated in epoch technology, which form the bases for the DAC system and enable 3 and 9-fold sampling rates respectively. Theoretical investigations and experimental results both prove the DAC functionality. A DAC demonstrator was built and used to generate various signal shapes with total sampling rates corresponding to a multiple of the electronics used. It is shown that with commercially available laser sources and filters, more than 8 ENOB over more than 100 GBW can be achieved, which is far better than state-of-the-art electronic DACs. Therefore, the DAC is compatible with silicon photonics platforms, shows very high applicability, and enables significantly faster DACs than have ever been realized in purely electronic technologies. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. Shannon C. 1948, A Mathematical Theory of Communication. Bell Tech J 273-379 423 MathNet. 2 MACSLT 2013, Optical Shaped Pulses of Exceptional Quality. 21 111 2013. 3AC Sync SJC T 2019, Integrated Source-Free All-Optical Sampling with a sampling rate of up to 3 times the RF bandwidth of silicon photonic MZM. OptX 27 21 299 7229984. 4AC Sync JT SJC T 2022, Reconfigurable and Real-Time High Bandwidth Signal Detection with Low Bandwidth in Silicon Photonics. OptX 38 13776 13789. 5RB 1987, Effects in Silicon. IAEJ Quantum Electron 23 1123 129. 6TCSMH-JC 2024, Forward Bias Silicon Phase Shifter Modeling for Electronic Photonic Co-Simulation and Validation in a 250 EPIC Technology. J Tech 116. 7A Hermans A B D B Vendy, RG 2021, Taking Silicon Photonics Modulators to a Higher Performance Level, State-of-the-Art and a Review of New Technologies. Ad Photon 320-24003. 8CTHJC 2024 Compact, High-Speed Mach Modulator with On-Chip Linear Drivers in Photonic Technology. IEEE Access 126456164570. 9M 2007, Chapter 2.325 Second ed. Springer, Berlin, Heidelberg, 7385. 10 HWSC, EL 1991, Modeling and Optimization of Traveling Wave Sub-3 Interferometric Modulators. IAEJ Quantum Electron 2736, 08617. 11G Cole C, A, R, C, Liel, Jo Y, J, A, Park B, Buff F, S, N 2015, Hybrid Silicon Photonic Circuits and Transceiver for 50S Transmission over Single-Mode Fiber. J Technol 30 36124 71254. 12CTHS CJ 2022, Broadband Mach Modulator with Linear Driver in Electronic Photonic Co-Integrated Platform. In Advanced Photonics Congress 2022, page IM4C1. Publishing Group. 13 Noel D. S. Onier M. E. C. A. D. S. K. G. Barth R. L. 2015 High Performance C Photonics Platform. In 2015 IIE Bipolar by CMOS Circuits and Technology Meeting, BCTM 8896. 14C Sync T. S. T. JC 2021, High Modulation Efficiency Segmented Mach Modulator integrated with Linear Driver in 0.25 technology. In OSA Advanced Photonics Congress 2021, page IW1B1. Publishing Group. 15 Jaeger R. T. 2010 Microelectronic Circuit Design, Chapter 17.6.1 The Miller Effect and 17.10.3 High Frequency Response of the Amplifier, 4th ed. Hill Education, 1159-1162, 1184-1185. 16 Gray P. Hurst P. Lewis S. R. 2009 Analysis and Design of Analog Integrated Circuits, Chapter 3.36 Common Collector Configuration and 7231 Frequency Response of the Emitter Follower, 5th ed. 191-194, 505-511. 17 Baba T. S. M. T. T. 2015, 25 S. Broadband Silicon Modulator with 0.31, based on forward-biased PIN diodes embedded with passive equalizer. Opt X 2326 32950 32960. 18 YG T. YT S. T. 2022 Highly power-efficient 2-bit, 12816 signal generation of coherent optical transmitter using 28 driver and all-silicon segmented modulator. In 2022 Optical Fiber Communications Conference and Exhibition, OFC 13. 19 CM T. JC 2021 Analysis of the effects of jitter, relative intensity noise and nonlinearity on a photonic digital-to-analog converter based on optical pulse synthesis. Opt X 29 15 2367 123681. 20 M Fard SB J 2020 Wideband Frequency Synthesizer with ultra-low phase noise using an optical clock source. In 2020 IAIE MTTS International Microwave Symposium, IMS 1283-1286. 21 More Photonics. 101-550-165 Ultralow Laser 2024. 22 M 2020, a 120S21 analog multiplexer with high linearity and technology. In 2020 IEEE BiCMOS and Compound Semiconductor Integrated Circuits and Technology Symposium, BCICTS 14. 23 CTC J 2023, generation of 100 periodic pulses using cascaded Mach modulators in silicon electronic-photonic platform. In CLEO 2023, page SF1P6. Publishing Group 24 Sync JSC JCT 2021, optical generation with threefold bandwidth of the employed electronics and photonics. In OSA Advanced Photonics Congress 2021, page 4D6. Publishing Group 25 Sync JASJCT 2020, photonic arbitrary waveform generation with 3 times the sampling rate of the modulator bandwidth. IEEE Photon Technol 3224-1544-1547. 26 Sync JCAT SJCT 2022, emulation of integrated high-bandwidth photonic using low-speed electronics. In next-generation optical communication, components, subsystems, and systems XI 12028-4248. 27 F Mir V X S 2023, integrated O and C-band silicon lithium Mach modulators with 100 bandwidth, low voltage and low loss. Opt X 31452-735289. 28 UAH FHB PAN-S T 2025 silicon modulator exceeding 110 using tunable time frequency equalization. 12-22-03215. 5. Integrated low jitter mode-locked lasers and pulse spectrum shapers. Abstract. This chapter discusses progress made towards the chip-scale integration of ultra-low jitter mode-locked lasers using rare earth gain media with CMOS-compatible fabrication. Such lasers generate ultra-stable pulse trains and optical frequency combs that are instrumental for signal processing systems such as optically assisted analog-to-digital converters. We also review work made towards the co-integration of optical filters for the interleaving of pulses or of the comb's free spectral range, as a further step towards a complete system integration. Acronyms: analog-to-digital converters, chirped grating, amplified spontaneous emission, complementary metal oxide semiconductor, coupled resonator optical waveguide, directional coupler splitter, digital signal processing, deep ultraviolet, erbium-doped fiber amplifier, effective number of bits, free spectral range, full width at half maximum, group delay, group delay dispersion, insertion loss, low pressure chemical vapor deposition, light detection and ranging, large mode area, mode-locked lasers, multiple input, multiple output, nonlinear interferometer-based saturable absorber, noise figure, optical add-drop multiplexer, optical frequency comb, optical ring resonator, optical spectrum analyzer, photonic integrated circuit, quality factor, radio frequency, root mean square, signal-to-noise ratio, silicon nitride, transverse electric, time interleaved, transverse magnetic, wavelength division multiplexing. 5.1 Introduction. Optical pulse trains with ultra-low jitter and phase noise are essential for many high-performance signal processing applications. Examples include precision light detection and ranging (LiDAR) for autonomous vehicles, optical clocks for satellite-based navigation, optical frequency synthesis for scientific metrology and high-speed, optically enabled analog-to-digital converters (ADCs). One of the most effective ways to generate such signals consists in using mode-locked lasers, MLLs, which produce periodic trains of ultra-short pulses with repetition rates ranging from 100 m to several G. In the spectral domain, these pulse trains correspond to evenly spaced, mutually coherent lines that form a frequency comb. Upon the generated microwave comb corresponds to a set of equally spaced beat tones that can be used as high-frequency reference signals. Optically pumped MLLs based on rare earth-doped amplifiers are particularly well-suited for applications requiring low jitter and phase noise, since they support femtosecond pulses and provide high power from lasers with large mode areas and extended cavity lengths. As explained in Sect. 5.2, this suppresses the influence of noise sources on the timing jitter of the pulse train and improves timing stability. In systems that rely on optical pulse trains with ultra-low phase noise, such as those employing MLLs for optical sampling, clock distribution, or frequency synthesis, the timing jitter of the pulse train is a critical performance metric. It refers to variability in the arrival time of individual pulses relative to an ideal periodic pulse train. When such a pulse train is used to generate a radio frequency (RF) signal through, timing jitter manifests as the synthesized signal's phase noise, which directly impacts the performance of high-speed ADCs whose achievable resolution is fundamentally limited by the aperture jitter inherited from the sampling clock 1. MLLs are a particularly well-suited technology for this application because they can have much less timing jitter than conventional microwave oscillators that operate at similar power levels. This performance is the result of basic physical properties of ultra-short optical pulses, which concentrate a large amount of energy into an extremely short time interval. This combination of high pulse energy and short pulse duration makes the pulse timing less susceptible to noise. Furthermore, rare earth-doped gain media reduce the coupling between gain and refractive index fluctuations, and therefore pulse timing. The quantum limit of timing jitter increases proportionally to the pulse duration and decreases with the square root of the pulse energy too. This favors designs that maximize the energy stored in the gain media and provide a large gain bandwidth to support ultra-short pulses. Theoretical and experimental studies have shown that tabletop femtosecond MLLs can produce optical pulse trains with timing jitter of a few, integrated over offset frequencies above 1K3. Due to the scaling of jitter with pulse energy and pulse duration, one can expect that on-chip femtosecond lasers can still achieve sub-level jitter. The lowest jitter femtosecond sources demonstrated to date are based on either free-space solid-state or fiber-based lasers. These systems are bulky, sensitive to alignment, and difficult to scale. Therefore, these platforms are difficult to use for emerging applications that demand compact, robust, and thermally stable devices, such as mobile frequency metrology, integrated radar, and chip-scale microwave sources and digitizers. This has motivated intensive efforts to implement low-jitter MLLs at the chip scale, especially in CMOS-compatible platforms for cost reduction, and for co-integration with electronics at a later stage. Integration provides several advantages beyond footprint reduction. It enables the integration of electronic and photonic subsystems, which is essential for realizing assisted AGs. It also allows for monolithic co-integration of stabilization loops for scalable manufacturing. Specific architectural choices, such as the use of large mode area waveguide amplifiers, support higher pulse energies while limiting nonlinear effects and provide a path towards increasing the performance of integrated chip-scale devices. The integration of rare earth gain media in CMOS chips is another essential aspect, since they provide both the wide gain spectrum and the low noise figure required for these applications. While progress has been made towards reducing the jitter of semiconductor MLLs, by combining the semiconductor gain medium with low-loss cavity 4 or extra cavity 5 optical delay lines at the chip scale, the high nonlinearity and limited gain spectrum of these devices fundamentally limits peak power, pulse energy divided by pulse duration, and therefore severely limits the performance with regard to jitter. In this chapter, we present progress towards the design and fabrication of an integrated low-jitter MLL using rare earth gain media, as well as its integration with on-chip pulse and spectral shapers. First, we review the origin and scaling of timing jitter in ultra-short pulse MLLs SECT. 5.2 Architectural Strategies for Jitter Suppression in Chip-Scale Devices SECT. 5.3 and recent experimental progress towards integrated devices with performance approaching that of fiber-based systems SECT. 5.4 We then give an example of an application in the form of a time-interleaved, assisted high-speed AG SECT. 5.5 and focus, in particular, on the implementation of a suitable pulse shaper that can be integrated in the same photonic integrated circuit (PIC) technology as the laser. For applications that require a free spectral range (FSR) in the frequency domain that is wider than what can be achieved at the chip scale 6/8, we implement an on-chip filter in a CMOS-compatible silicon nitride technology that can also be cascaded with the MLL on the same PIC. The concept of the filter is described in SECT. 5.6 with details of its implementation in SECT. 5.6.2 and first experimental results in SECT. 5.6.3. We summarize the chapter in SECT. 5.7. 5.2 Timing jitter in mode-locked lasers, fundamentals, scaling laws, and comparison with electronic oscillators. In an electronic oscillator, timing is defined by the zero crossings of a microwave signal with period t0. The underlying reference oscillator, dark blue curve, indicates a noise-free signal, while the light blue curves represent a signal that suffers from phase advance or phase retardation that builds up over time due to noise. In a femtosecond laser, ultra-short pulses of duration are emitted at regular intervals tr. The short temporal extent of each pulse limits the time window during which noise can directly perturb the pulse timing, effectively reducing the impact of the noise per cavity round trip. A microwave oscillator consists of a resonator and an amplifier in a feedback loop configuration. The resonator supports an oscillating electromagnetic mode at a specific frequency with stored energy in steady-state oscillation. As the oscillator generates a microwave signal, part of this energy is emitted through the output port, while additional losses occur internally due to dissipation in the cavity. The amplifier must compensate for both the outcoupled power and the intrinsic cavity losses to maintain steady-state oscillation. The loaded quality factor, Q, is defined as the ratio of the energy stored in the resonator to the energy lost during 1 radian of the oscillation cycle. The corresponding cavity decay time, QT02, where T0 is the oscillation period, characterizes how quickly the stored energy would decay in the absence of amplification. We use this decay time not only to describe how energy leaves the cavity, but also to calculate the amount of thermal noise that must be injected to maintain equilibrium, since decaying thermal noise is replenished by the environment. The coupling of the cavity to loss reservoirs leads to thermalization of the field in the passive resonator. At equilibrium, the average thermal energy stored in the cavity mode is kBT, where kB is the constant and T is the cavity temperature in Kelvin 9. This results in a continuous thermal power loss of kBt, which must be balanced by an equal thermal noise power entering the cavity from the environment. In an oscillator with active elements, this thermal noise influx is at least doubled by the noise of the feedback amplifier that compensates for the cavity loss. This additional noise contribution that arises from non-ideal amplifier behavior is described by a dimensionless excess noise factor, a comparison of 5.1 and 5.2 reveals two key differences. The first concerns the fundamental noise level. Assuming similar stored energies and cavity decay times, the noise power in optical systems is higher than in microwave systems because of the ratio kBt32 at typical operating points, 200T, T300K. Under typical conditions, quantum noise at optical frequencies is thus higher than thermal noise at microwave frequencies. However, the dominant factor determining the jitter performance of MLL pulse trains compared to that of microwave oscillators arises from the difference in time scales. The timing jitter in MLLs scales with the square of the pulse duration, whereas in microwave oscillators it scales with the square of the oscillation period. For example, for a 10G microwave oscillator with T0-100 and a femtosecond laser with a pulse width of 100, the ratio T0-22106, or 60 dB. This dramatic difference in scaling explains why MLLs can achieve timing jitter levels that are orders of magnitude lower than even the best microwave oscillators, despite operating with higher intrinsic noise power. Taken together, the higher noise energy in optical systems is overwhelmed by the far shorter pulse duration possible at optical frequencies. Consequently, the timing jitter noise floor of MLLs is often 40 dB or more lower than that of typical microwave sources, with similar energy storage capabilities and cavity decay times. 5.2.1 timing jitter and its impact on ADC performance. We have reviewed the origin of timing jitter and explained why femtosecond MLLs outperform electronic oscillators in terms of timing stability. Here we describe how this advantage improves performance in high-speed systems, especially in ADCs, in which timing jitter affects the achievable resolution. We quantify the relation between timing jitter and the effective number of bits, ENOB, and show the importance for high-resolution sampling of high-frequency signals. Survey of ADC performance presented as ENOB versus analog input plots. The light blue circles correspond to the original data from the Survey 11. The dark blue circles represent updated data for electronic ADCs based on the 2024 version of the survey by 12. The orange circles denote assisted ADCs from the recent literature, including results from Al. 13 Al. 14 Su Al. 15 Al. 16 and Feng Al. 6. Dashed lines indicate the ENOB limits imposed by timing jitter levels ranging from 1 blue to 0.1 red. 5.3 Architecture and design of integrated mode-locked lasers. Architecture of the integrated rare earth MLL. The device is fabricated using a silicon nitridon insulator waveguide platform combined with a rare earth doped alumina film for optical gain. A wavelength division multiplexer, WDM, couples the pump light into the gain section. The laser cavity includes a large mode area, LMA, waveguide design for high-energy pulse operation, implemented within the region highlighted by the green box. LMA sections are connected through adiabatic tapers and tight bends. Mode locking is achieved using a nonlinear interferometer-based saturable absorber, NLISA, which splits the pulse into two arms via a directional coupler and reflects them back through integrated mirrors. Thermo-optic phase tuning is implemented via high-power H1 and low-power H2 heater arms. Dispersion compensation is achieved via unchirped grating ACG. The pump light is introduced into the cavity via an integrated wavelength division multiplexing WDM coupler 21, which combines the pump and signal into the gain section. This device is also referred to as a pump signal combiner. In our implementation, 1610 pump light is injected into the thulium-doped amplifier for amplification of signals around a 1890 center wavelength. The WDM has a 130 bandwidth at the 1 dB level, while providing over 90% transmission at the pump wavelengths. In reverse, the WDM guides the amplified signal to the ACG that closes the cavity for the signal 20. The signal is amplified in a thin 1 rare earth doped alumina gain film, which is deposited on a thin silica top cladding above the silicon nitride (CN) waveguides. The waveguides have been specifically engineered to support weakly guided modes with large mode area, 10-2, and a high overlap between the pump and signal within the gain film. More than 86% of the pump mode is confined within the gain film, exhibiting over 99% mode overlap with the signal. The structure is designed for low-loss, single-mode operation at the pump and signal wavelengths, with higher-order modes being suppressed 22. Unlike conventional CN waveguides, which typically have limited mode area, the larger mode area of the gain film provides several critical advantages, including reduced nonlinear effects, increased saturation power, larger energy storage, and a reduction of thermorefractive noise. These features are essential for generating low jitter pulses. Experimental results related to the separately tested amplifier components will be presented in Sect. 541. After the gain section, the amplified signal at 1890 is transferred back into the silicon nitride core that is adiabatically tapered up to pull the light back into it. The light then enters a nonlinear interferometer-based saturable absorber, NLISA, with an unequal power splitting ratio between the two interferometer arms. This structure operates as an intensity-dependent reflector and serves as a passive mode-locking element based on the nonlinearity. For a specific bias phase between the two arms of the interferometer that can be selected via the heaters, at low incident pulse peak power, the NLISA reflects the signal with a significant extinction. At higher input peak powers, the unequal nonlinear phase accumulation in the two interferometer arms leads to increased constructive interference in the reflection path and thus to a higher reflectivity. This mimics the behavior of a saturable absorber and supports pulse formation by preferentially reinforcing the high-intensity portions of the signal. Experimental results validating the nonlinear response and saturable absorption behavior of the NLISA will be presented in Sect. 542. End mirrors are integral components of the MLL architecture. They define the cavity boundaries and provide optical feedback. One end mirror is positioned at the signal port of the WDM coupler. The others are placed at the extremities of the NLI arms. They can be implemented as either loops or integrated gratings. Loops use waveguide loops and directional couplers, requiring careful design for 3 dB splitting ratios, insertion loss minimization, and broadband operation. In contrast, ACGs offer a compact footprint, typically a few hundred micrometers, broadband reflectivity, and the ability to engineer dispersion within the cavity, which is crucial for ultra-short pulse generation. However, realizing such gratings in a silicon photonics platform poses fabrication challenges, particularly to achieve precise chirp profiles that are compatible with deep ultraviolet DUV lithography. The output signal is directed to the second reject port of the NLI. The amount of light that is transmitted out of the cavity is determined by the interference between the signal reflected in the two interferometer arms and the unequal power splitting ratio. The details of the layer thicknesses and of the device geometries are given in the next section. Simulations and experiments were performed for transverse electric TE, polarized light for the Q-switched laser, and for transverse magnetic TM, polarized light for the power amplifier described in the following. 5.4 Experimental results, key components and Q-switched laser operation. This section presents experimental results for the main building blocks used in the integrated MLL, including rare earth-doped amplifiers, a saturable absorber for passive mode locking and broadband gratings in silicon nitride technology for dispersion compensation. To date, Q-switched laser operation has been achieved with all these components integrated in a single device fabricated in a silicon photonics platform, with the exception of the ACGs that remain to be integrated with the rest of the components in order to provide the necessary dispersion compensation for stable mode locking. 541 Rare earth doped aluminum oxide optical amplifier for high power operation. A cross-section of the gain section of the on-chip amplifier. B. Schematic of the amplifier waveguide structure, with mode profiles shown for the low confinement LMA region and for high confinement bends. To separately test the gain section of the laser device, we fabricated a single-pass amplifier with an identical LMA design as in the laser and thoroughly investigated its amplifying properties 24-25. A schematic of the amplifier waveguide structure and its cross-section are shown in Fig. 5.4 and the layer stack is fabricated by creating a local opening in the top CO2 cladding of the passive waveguide structure, such that only about 300 of the CO2 remains on top of the CN waveguide core that is itself etched into an 800 thick stoichiometric CN layer. A roughly 1 thick thulium-doped Altuo-3 film is then deposited via reactive RF co-sputtering on top of the chip, such that the local opening is filled with the active gain film. The measured doping concentration is around 410203, which is more than an order of magnitude higher than in typical fiber-based laser and amplifier systems, to achieve high gain within a very short amplifier waveguide. To create a large mode area in the gain film, the CN waveguide width is reduced to 280 in the straight gain sections, located inside the green box in Fig. 5.4, which pushes the optical mode into the gain layer with a confinement factor of over 85%. Before entering the waveguide bends, the CN width is slowly tapered back up to 900 to create an adiabatic transition pulling the mode back into the CN core, with this high confinement allowing for a compact bend radius below 85 with over 99% transmission. A input and amplified output spectra of a filtered pulse. B. On-chip average amplified output power of the pulse signal as a function of on-chip pump power for various signal input power levels. Measurements of the small signal gain have also been performed for a 10-long amplifier waveguide with a continuous wave signal at a 1818 wavelength and input power levels between 2W and 15 MW on chip. Small signal net gain was measured to be 28 dB, and a high output saturation power was also measured. A high output saturation power means that even high-power signals are still able to achieve high net gain. The output saturation power is not identical to the intrinsic gain medium saturation power described by 5.4, as the output saturation power is also dependent on specific amplifier conditions such as amplifier length and pump power, but in both cases a larger mode area helps to increase the saturation power. The saturation power PSAT out increases roughly linearly with pump power and reaches beyond 100 MW for the highest pump power used here, which is exceptionally high for integrated optical amplifiers, for which typical saturation power levels in the order of 10 MW have been reported to date. 542 Nonlinear, interferometer-based saturable absorber. The operation of the nonlinear interferometer-based saturable absorber, NLISA, is governed by several key parameters. A 2-2 directional coupler splitter DCS, with an unequal power splitting ratio, divides the input signal into two arms with power fractions R and 1R. After reflection from integrated mirrors at the ends of each arm, the signals recombine at the same DCS. Some of the recombined light reflects back into the laser cavity, while the rest exits through the output port. The reflectivity R of the device is defined as the ratio of reflected energy to input energy, and varies depending on the differential nonlinear phase shift accumulated between the two arms. The reflectivity is maximized near a differential phase shift of, and the slope of this response determines the saturable absorber coefficient, a key figure of merit for the saturable absorber and its mode-locking driving force. The modulation depth of the artificial absorber, i.e., the variation of the reflectivity over a phase shift of 2, gives the maximum attainable absorption change. The NLISA operates on the upward slope of the first reflectivity peak, where the device exhibits intensity-dependent reflection. In our implementation, the directional coupler has an 80-20 splitting ratio at a wavelength of 1.9, with more than 50% reflection modulation depth. The reflectivity curve of the realized device is offset relative to simulations due to imperfections in the fabrication. However, this can be compensated by the device with the embedded thermal phase shifters. There are two main approaches to characterizing the reflection response of an NLISA. The first is a direct power sweep method, where a train of optical pulses is launched into one arm of the NLI and the average input power is gradually increased. The reflected power is then measured as a function of the launched power. A challenge with this approach arises at higher powers due to significant nonlinear spectral broadening, particularly in waveguides exhibiting anomalous dispersion, which can lead to pulse splitting. As a result, the extracted response is highly dependent on the specific characteristics of the input pulse. A peak pulse power dependent NLI reflection curve has been extracted with a 200 pulse width 20. An alternative method involves keeping the pulse power fixed, typically at low levels to avoid nonlinear effects, while applying an externally tunable phase shift to one of the interferometer arms, for example using an integrated thermal heater. This phase tuning modulates the reflected power without introducing any nonlinear distortion in the input pulse. This approach allows the extraction of a more general NLI response that is independent of the specific pulse shape or peak power, and avoids strong self-phase modulation effects present in the first method. Using this technique, multiple phase shifts can be mapped out and the maximum modulation depth extracted. Once the reflectivity curve is known, the device can be thermally tuned to operate in the desired regime. To generate high-energy Q-switched pulses, we bias the device around the highest upward slope. Conversely, operating closer to the base of the slope leads to lower energy pulses. Overall, the NLISA offers a tunable and fast saturable absorber, with negligible thermal crosstalk between the arms due to their spatial separation. 543 Broadband Dispersion Compensating Silicon Nitride Gratings. For mode-locked operation with femtosecond pulses, careful dispersion compensation must be achieved taking all dispersive elements in the cavity into account. For complete flexibility in dispersion compensation, we designed ACGs operating in the TE polarization with a reflection band centered on 1890. The CN waveguide is 800 thick and has 3.3 thick top and 4 thick bottom oxide claddings. We used deep ultraviolet DUV lithography to pattern the gratings during fabrication, which required us to use fixed corrugation periods. We implemented a linear chirp in the grating by tapering the waveguide from a narrower to a wider width along the propagation direction, resulting in a linear increase in the effective index. In order to suppress reflection side lobes and minimize spectral ripples in the dispersion response, we applied a squared cosine when varying the waveguide width and corrugation depth. The primary design objective was to realize a broadband flat group delay dispersion (GDD) profile with high reflectivity. A measured reflection full opacity curves and transmission reduced opacity spectra of silicon nitride ACGs centered at 1890, showing high reflectivity stop bands spanning over 150. The short and long gratings, with 1000 and 2000 periods respectively, are shown in blue and black. B extracted group delay dispersion (GDD) and group delay (GID) from white light interferometry measurements. Solid lines represent GDD right axis, and dashed lines represent GD left axis. The GDD curves reveal flat dispersion of approximately 70,002 for the short grating and 140,002 for the long grating, showing that the dispersion level can be precisely controlled by adjusting the grating length. These results confirm that ACGs are capable of supporting broadband dispersion compensation and enabling sub-100 pulse formation. Similar gratings centered at 1550 were used in separate experiments to demonstrate their suitability for high-performance ultra-short pulse shaping with pulse compression down to 6327. Flat dispersion over a wide bandwidth is also crucial for minimizing the time duration of the pulses and therefore timing jitter in MLLs. Our measurements using two different ACG lengths demonstrate both broadband and engineered dispersion control. It is worth noting that the Q-switched integrated laser described in the next section employed loop mirror reflectors without ACGs, since its design was not yet ready at that time. We believe that integrating ACGs with a tailored dispersion profile is key towards achieving stable mode locking in future integrated MLLs. 544 Silicon Photonics High-Energy Passively Q-Switched Laser. Realizing fully integrated, low-jitter MLLs is a critical milestone for enabling next-generation photonic ADCs. In this section, we present a first step into that direction by presenting results on a high-energy, passively Q-switched laser built on a Silicon Photonics Platform 20. This laser integrates the essential functional components discussed before, especially a rare earth-doped alumina amplifier, a fast nonlinear interferometer-based saturable absorber, NLISA, and integrated waveguide reflectors. While the system has not yet achieved stable mode locking, observing energy buildup and pulse formation validates the performance of the amplifier and the function of the saturable absorber within a fully integrated cavity. This result is a crucial step towards on-chip sources in which dispersion control, nonlinear dynamics, and gain saturation must be engineered simultaneously in a low-loss silicon photonic technology platform. A measured optical spectrum showing broadband lasing from the integrated cavity. B. Average output signal power with respect to the pump power. C. Q-switched pulse train recorded with an oscilloscope. D. Zoomed-in trace showing the shape of a single pulse. Q-switched pulses are generated by thermally tuning the NLISA so that the signal is on the positive slope of its reflectivity curve. In this regime, effective loss modulation initiates periodic energy buildup and depletion. A pump at 1.61 is coupled into the amplifier section via a lensed fiber. As the pump power increases, the laser transitions from continuous wave to passively Q-switched operation. This transition is governed by the interplay between gain dynamics and the saturable absorber response. With 400 MW of coupled pump power, the laser emits Q-switched pulses centered at 1.89, which is aligned with the optimal reflection and transmission characteristics of the WDM and loop mirror interfaces. These pulses have a low repetition rate below 1 m, a pulse width around 250, and a pulse energy exceeding 150 Nj in the output waveguide of the NLISA outside of the laser cavity. The on-chip power conversion slope efficiency is 40%, with a lasing threshold of about 20 MW. These results confirm stable Q-switched operation and good energy scaling with pump power. Figure 5.7 shows the experimental output, including the optical spectrum, pulse train, and a zoomed-in single pulse. Again, the current laser cavity used loop mirrors without dispersion compensation, which hindered short pulse operation. Future designs can address this issue by incorporating ACGs to engineer dispersion and promote mode locking. Finally, in the Q-switching regime observed here, dynamics must be managed carefully to prevent excessive power levels that can otherwise damage waveguides. Despite these limitations, demonstrating stable, high-energy Q-switched operation validates the saturable absorber function and confirms the functionality of the fully integrated platform, including the performance of the gain medium. 5.5 Photonic ADCs, application of low-jitter mode-locked lasers and integrated pulse shaping. In this section, we summarize the architecture of time-interleaved T-assisted ADCs, as an example of systems that leverage the low jitter of MLLs to overcome the limitations of purely electronic approaches. We then describe in more detail the implementation of a pulse shaper required for such systems that is implemented in the same technology platform as the laser and could thus directly be implemented with it. 551 Photonic ADC architecture. Schematic of the pulse shaper and of its utilization in an assisted TADC. A schematic of a TADC with 4 channels that allow the sampling rate accordingly. B. Layout of the pulse interleaver and C. of the coupled resonator optical waveguide, CRO, optical add-drop multiplexer, OADM, used in it. The shown in D utilizes identical CRO OADMs to facilitate spectral matching. Figure adapted from 28 under Open Access License Agreement 2022. The system, whose diagram is represented in Fig. 5.8 builds on an ultra-low jitter MLL, which generates a train of optical pulses at a repetition rate FR1TR. These pulses serve as the sampling clock with sub-10 femtosecond timing jitter, and potentially even lower in optimized configurations. To overcome the bandwidth limitations of electronics, the sampling rate is increased by interleaving n pulses with different center frequencies, wherein n is also the number of interleaved channels. The result is a pulse train with an effective repetition rate of n. Fr. The electro-optic sampling is performed by modulating this interleaved optical pulse train with the analog RF signal using a broadband Mach intensity modulator. Each optical pulse acquires amplitude information corresponding to the analog signal at the instant of sampling. The resulting modulated pulse train thus encodes the waveform of the input signal as a sequence of intensity-modulated optical pulses. Because the interleaved pulse rate NFR may exceed the capabilities of conventional electronic ADCs, the modulated optical signal is according to pulse wavelength into n separate channels using a WDM. This step effectively separates the high repetition rate pulses into multiple parallel channels operating at the lower repetition rate FR. Each lower bandwidth optical channel is converted into an electrical waveform by a photodetector and is subsequently digitized using an electronic ADC operating at a lower sampling speed, as referenced to the MLL. In addition to reducing the sampling rate requirements of the electrical ADCs digitizing each channel, this also reduces the sensitivity to aperture jitter, as the achievable ENOB can be evaluated with 5.3 by substituting Fin with the frequency of the downsampled signal actually seen by the electronic ADC, whose maximum value is n times smaller than the frequency applying to the overall system. The photonic TAG architecture offers the advantage that in the ideal case the recorded samples can be directly interleaved to recover the entire signal, without requiring advanced digital signal processing (DSP). However, as a downside, it is also relatively hungry in terms of the spectral comb width required from the MLL, which scales as N2 when the number of channels is increased, while keeping the initial pulse repetition rate of the MLL constant to increase the overall sampling rate of the system. This stems from the fact that interleaving n pulses also requires pulses that are n times smaller, and that each require an n times larger spectrum per pulse. The spectral requirements can be reduced by some amount by introducing a multiple input, multiple output MIMO filter in the DSP28. 552 pulse interleaver and WDM for TADCs in the silicon nitride platform. The pulse interleaver is a key component for the integration of an assisted TADC, following the architecture described in SECT 551. It is advantageous if it can be realized in the same CN platform as the MLL to reduce the number of photonic chips that need to be combined, in particular since the bonding of thin lithium films onto CN waveguide cores also provides a path towards integration of high-speed modulators into the same chip 29. Here we report such a device implemented in the CN technology of SA30, with waveguides etched into an 800 thick stoichiometric C3N4 layer deposited by low-pressure chemical vapor deposition (LPCVD) that is compatible with the MLL platform described in the previous sections. For a first proof of principle, the design was targeted for combs centered on 1550-28, but can be straightforwardly adapted to the center wavelength of the integrated MLL. As a primary advantage for this application, the CN platform offers a high power handling capability, which is essential to overcome shot noise limited operation in analog signal processing schemes. However, the medium index contrast between CN and the CO2 cladding also limits bending radii and thus routing density, and in case of ring resonator-based devices, the FSR of the filters. Here we describe a device concept based on coupled resonator optical waveguide (CRO) add-drop multiplexers (OADMs), in which special emphasis was placed onto increasing the filter FSR and thus the usable spectrum, while minimizing excess optical losses resulting from internal bend-induced resonator losses. Micrograph of the pulse interleaver with 4 CRO OADMs and 3 interspaced delay lines. The inset shows a detailed view of the metal heaters fabricated on top of the rings for thermal tuning. These share common electrodes and allow for a global spectral repositioning of the OADM. The individual rings inside the CRO are aligned relative to each other by design and do not require individual tuning. Figure adapted from 28 under Open Access License Agreement 2022. Figure 5.8c shows a detailed view of the CRO OADM layout and Fig. 5.1, a comparison between the modeled and measured CRO OADM transfer functions. There can be seen to be a very good agreement between the two. Adjacent OADMs are also designed to have passbands shifted by 360G by design, which is achieved by adding small waveguide increments in the layout of the individual resonators forming the CROs. Figure 510b shows the transfer function of the 4 CRO filters that have been individually measured without thermal tuning, which also shows that they have the targeted relative spectral alignment as fabricated. Due to the periodic nature of their transfer function, their absolute spectral position is also not critical so long as the transfer functions of the CROs utilized in the pulse interleaver and the nominally identical CROs used for WDM demultiplexing of the signal after modulation, see Fig. 5.8d overlay with each other. In other words, the repeatability of the process may be sufficient to operate this device without any thermal tuning, which is very desirable to reduce its power consumption in view of the low thermo-optic coefficient of Cn transfer functions of the CRO OADMs. An overlay of the simulated and measured transfer functions of a single OADM. Be measured transfer functions of the 4 CRO OADMs without any thermal tuning and overlay with the spectrum of a semiconductor MLL3233. The transfer functions can be seen to be staggered in wavelength as designed. The partial frequency overlap was designed in and results from a trade-off between pulse width, sampling accuracy, and frequency domain crosstalk 28. See semiconductor MLL spectrum filtered by the CRO filters. It can be seen that the pulses color-coded in blue and in purple each comprise 2 frequency slices separated by 1 filter FSR. This is not a problem as long as the cumulative dispersion in the system stays low enough for these spectral components not to separate. Figure adapted from 28 under Open Access License Agreement 2022. 5.6 Cascaded optical filters for spectral shaping of integrated mode-locked lasers. With the explosive growth of data transport and processing worldwide, increasing strain is placed on communication networks to meet demand. In this context, optical frequency comb sources, OFCs, are investigated as a means to increase network capacity 33-34. The large number of equally spaced comb lines that an OFC generates are ideal for communication systems, since each line can serve as an optical carrier on a perfectly aligned grid to allow massively parallel WDM transmission. OFCs are also instrumental for distance ranging 35, signal synthesis 36, computing 8, 37, 38, and a class of photonic ADCs that perform the optical slicing and DSP in the frequency domain 6, 7. For these applications, the FSR of the comb needs to be in the order of tens of G, since this determines the bandwidth of the tributary signals that can be applied to the comb lines. This is readily achieved with semiconductor MLLs 32 or with on-chip parametric comb generation 39. However, it is currently out of reach of integrated rare earth MLLs due to the extended cavity size required due to the comparatively low gain coefficient of the rare earth gain media. The pulse repetition rate can be increased in the time domain with a passive pulse interleaver in a lossless manner 40. However, this results in the interleaved pulses having different phases and does not increase the FSR in the frequency domain. An elegant extension of this method has been shown in 41, in which the phase of the interleaved pulses has been dynamically corrected with a phase shifter, resulting in an actual increase of the FSR. This does, however, require a high-speed modulator to apply phase shifts that need to be adjusted as the temperature of the pulse interleaver drifts with an update rate that needs to be synchronized with the MLL's pulse repetition rate. We present a simpler to operate and more straightforward approach consisting in designing a higher-order filter with multiple optical ring resonators, ORRs, implemented in the same CN platform as the MLL described in the previous sections. Such optical filters have already been integrated in silicon photonics platforms to select groups of comb lines 42. Here, an additional challenge arises from the OFC starting with a relatively small FSR, assumed in this section to be 2.5 G, which makes it difficult to isolate individual comb lines in an integrated platform with finite waveguide losses that limit achievable quality, Q factors, and thus resonator. While such filtering has been implemented with fiber-based ORRs starting from even smaller FSRs, 43, the 0.2 dB waveguide losses typical for high confinement CN limit loaded Q factors to 1000000 and to a 200 m FWHM, assuming a comb centered at 1550. This in turn limits the rejection of adjacent comb lines to less than 30 dB, which is further reduced to 20 dB extinction if the initial FSR is reduced to 1.25 m, which corresponds to the laser cavity design presented in SECT. 5.4. Operating ORRs as OADMs that pick every nth line from the input bus waveguide and couple them to a drop waveguide exacerbates this problem, as there exists an inherent trade-off between the insertion losses, ILs of OADMs, and their resulting from the loaded Q factor. In order to have low ILs, the extrinsic resonator losses corresponding to coupling to the bus waveguides need to be significantly larger than the internal losses arising from the waveguide losses inside the ring. This in turn spoils the Q factor of the ORR and the ability to select lines from a closely spaced OFC. We circumvent this problem by cascading two ORRs. One is operated as a higher Q notch filter in critical coupling configuration that extinguishes every second comb line and whose loaded Q factor is half of the intrinsic Q factor provided by the platform. This doubles the FSR and reduces the Q factor required from the other ORR that is operated as an OADM picking up every nth comb line of the original comb and whose Q factor can be sufficiently spoiled to enable low ILs. This approach can be configured to the FSR of the MLL to any even multiple, e.g. FSRs of 5, 10, 20 or 25G can be obtained this way from the original 2.5G. While this approach seems deceptively simple on paper, a practical implementation requires a precise adjustment of the coupling strengths to achieve the targeted extinctions, as well as a precise control of the ORR's FSR and waveguide dispersion, as these otherwise limit the spectral width over which the OFC can be effectively filtered without incurring large excess losses due to spectral misalignment between comb and filter. An overview of relevant resonator theory is given in SECT. 561, followed by the design details in SECT. 562 and first experimental results in SECT. 563. 561 Theoretical background for ring-based filters. Schematic of an OADM with two bus waveguides and be an all-pass ORR used as a periodic notch filter. See transmission spectra at the drop port of an OADM with a 20G FSR for different coupling coefficients at fixed waveguide losses assumed to be 0.2 dB. A trade-off between and ILs is apparent. DILs versus assuming different waveguide losses. The coupling coefficients 1 and 2 are assumed to be equal to each other and are intrinsically varied inside the curves. 562 Filter design. Schematic of the OFC filter. The OFC is applied as an input to the OADM and is filtered as seen on the left plot. The signal is then filtered by the notch filter, with the resulting spectrum shown in the right plot. This illustration is based on a 20G OFC filter and a 2.5G initial comb spectrum as discussed in the text. For a 20G filter and assuming waveguides with 0.2 dB losses and a group index of 212, we target coupling coefficients of 120179 for the OADM and 10349 for the notch filter, with ORR circumferences of L7075 and L28302, respectively. The intrinsic Q factor of the ORRs, determined by the waveguide losses, is 1.87 million. The loaded Q factor of the critically coupled notch filter is half, 933,000, resulting in a FWHM of 207 m. The OADM, on the other hand, has a reduced Q factor of 622,000 and a FWHM of 311 m. This results in 3.45 dB ILs from the OADM and negligible excess ILs of 0.01 dB from the notch filter at the targeted comb lines. Without the notch filter, the OADM would extinguish their nearest neighbors that are spaced by 2.5 G from them by 24 dB relative to them, while the second nearest rejected comb lines are extinguished by 30 dB by using the notch filter, an extinction of 30 dB can be obtained throughout. This approach introduces several implementation challenges. As mentioned above, precise control over the group index and minimization of the dispersion are essential to ensure that a OFC can be filtered. Moreover, care has to be taken in the layout to ensure that the larger FSR of the OADM is an exact multiple of the notch filter's FSR, so that they co-vary across process variations. This facilitates guarding against them with a device parameter exploration, since it reduces the dimensionality of the parameter space to 1. To reduce the footprint of the device given the large ORR circumferences required to reach the targeted FSRs, the resonators are realized using spiral waveguide geometries. Each ORR consists of 2 spirals connected by waveguides in the center region of the ORR that also comprises the coupling sections, as seen in Fig. 5.13. Given the large number of bends involved, particular attention was paid to minimizing polarization and modal crosstalk, which can occur due to bends since the waveguides are etched with slightly slanted edges that break their vertical symmetry. A square spiral configuration was adopted, in which the majority of the cavity consists of straight waveguide segments connected via compact 90 bends with a radius of 25. While the resulting bending losses are small for the fundamental TE and TM modes, both below 0.003 dB, the bends introduce significant losses for higher-order modes, contributing to modal filtering. A layout of a filter converting the FSR of an OFC from 2.5 to 20G. The ports of the device are labeled consistently with Fig. 5.11 and BB micrograph of the device. As explained above, the dispersion of the waveguide needs to be minimized to maintain a constant ORR FSR across the comb. See 5.9. For filtering of a broadband comb centered on 1550, the dispersion was studied in the range of 1540-1560. Over this wavelength range, the CN platform exhibits the smallest dispersion for a waveguide base width of 1.05, given the fixed 800 waveguide height. At this width, the waveguide is no longer single mode and supports higher-order modes that are very weakly guided. A short section in which the waveguide width was tapered down to 0.8 in a bend was introduced as a modal filter in each ring to further suppress the buildup of higher-order modes. The ratio of this single-mode section to the total cavity length was kept consistent across different ring sizes to preserve the targeted ratio between the FSRs. Tolerance to fabrication errors. Attenuation of the selected comb lines versus wavelength for different fabrication biases. Attenuation of the adjacent comb lines on either side of the OADM resonance versus wavelength for different fabrication biases. A sensitivity analysis is conducted to quantify this, and its results are visualized in Fig. 5.14. After multiplying the spectral response of a filter, modeled under consideration of process biases, with a train of evenly spaced peaks emulating a 2.5G OFC. Figure 5.14 shows the attenuation of the targeted comb lines across a 20 spectrum, while Fig. 5.14b shows the power attenuation of the adjacent comb lines that should be rejected. Deviations which change the cross-sectional aspect ratio of the waveguide, i.e., with opposite offsets applied to the height and to the width of the waveguide core, cause the biggest degradation in performance. Selecting the 3 dB bandwidth as a performance metric, independent variations beyond 4 in height and 10.4 in width are not acceptable if a 20 comb width is to be maintained. Additionally, these deviations do not only reduce the magnitude of the targeted comb lines, but also raise the level of the adjacent ones, reducing the overall extinction ratio. For the range described above, the comb line suppression worsens by 14 dB, rising from 36 dB below the selected comb line transmission to 20 dB below it. An additional penalty can arise from changes in the directional coupler geometry. In the corresponding analysis, the center-to-center distance between the waveguides is assumed to remain constant and the gap between them to increase or decrease by 10.4, in line with the process compliance limits discussed above for the waveguide width. At the same time, the layer thickness is also varied by 4 in a complete corner analysis. This results in small changes of the coupling coefficients, with varying in the range of 1–2%, too small a change to significantly impact the OADM performance. IL changes are 0–1 dB. Provided the fabrication biases also remain inside these bounds in the junctions, the dominant performance sensitivity would lie in the effective filter bandwidth resulting from the FSR variation. However, different and larger process biases are possible in the junctions. 563 Experimental results. We have characterized a device fabricated in the CN platform of SA that was aimed at decimating an OFC to convert its FSR from 2.5 to 20G. The spectral shaping capabilities of the device was measured using an ultrastable 2.5G FSR MLL from Menhir Photonics SA and a high-resolution optical spectrum analyzer, OSA, from Apex Technologies with a 5M resolution bandwidth. To thermally align the filter resonances to the grid of the OFC, amplified spontaneous emission generated by an erbium-doped fiber amplifier, EDFA, was first combined with the OFC and injected into the device, so that the overlay of the OFC with the resonances could be observed on the OSA. Optical spectrum of an OFC measured over a 20 wavelength range after filtering by a 20G comb decimation filter, thin blue curve. The solid black, red, and purple curves show the amplitude of the targeted comb lines, their nearest neighbor towards larger wavelengths and their nearest neighbor towards smaller wavelengths, respectively. The spectrum of the unfiltered MLL used to perform the measurement is overlaid as a dashed black curve. The unfiltered MLL spectrum and the filtered MLL spectrum are both normalized to have a peak power of 0 dB. ILs are reported separately in the text. After the OADM, the extinction of the lines that are immediately adjacent to the targeted ones, relative to them, is in the order of 11 dB in a 16 range spanning from 192.5 to 194.5 T, 100 target comb lines with a 20G spacing. The lines that are second neighbors to the targeted ones are extinguished by approximately 18 dB. Both numbers are consistent with loaded OADM Q factors in the range of 130,000–150,000, which are much lower than targeted due to the interface losses between straight and bent waveguide segments that amount to 3 dB and will be addressed in the future with adiabatic bends. In this configuration, the combination with a functional notch filter appears even more critical to further extinguish the nearest neighbors. The ILs of the OADM in the order of 21 dB are also limited by the below target coupling strengths. Test structures implemented to independently measure them show that the directional couplers have coupling strengths very significantly below target, with measured amplitude coupling coefficients of 0.105 and 0.18 versus targeted ones of 0.179 and 0.349 for the OADM and notch filter, respectively. Since this discrepancy exceeds by far that expected from the process bias as evaluated from standalone waveguides, it is possible that a different and more significant process bias occurred for closely spaced waveguides in the coupler sections that will require of the junctions in the future. At the edges of the recorded optical spectrum, at 1542 and 1562, the nearest neighbor comb lines directly adjacent to the targeted ones and located towards the center of the spectrum, i.e. the higher wavelength ones at 1542 and the lower wavelength ones at 1562 are almost as strong after the filter as the targeted ones. This points to the average FSR being below target. We evaluate the resonance frequencies of the OADM to be shifted by a cumulative amount of plus 1G at 1562, 192 T, and by 1G at 1542, 194.5 T, indicating that the average FSR is 16 m too small. This is attributed primarily to the difficulty of achieving precise temperature control at 200 C. However, dispersion might also play a role here, since the data indicates that the FSR offsets grow towards the edges of the spectrum. This experimental realization of the filter concept serves as a first demonstration, but also highlights the aspects that require attention in a future fabrication iteration. The 200 C tuning temperate required to adjust the FSR is excessive, but can be very significantly reduced by the design. Even with the observed room temperature FSR offset, broadband alignment of the filter with the OFC was possible. A future device design will also have to address excessive internal ORR loss by implementing adiabatic bends. Based on the sensitivity analysis reported in the previous section, we expect that process control of 4 in waveguide height and 10-4 in waveguide width will enable filters with ILs of 3.5 dB, a 3 dB passband of 20, and an extinction above 21 dB for the rejected lines relative to the targeted ones across the entire spectrum, which would be above 30 dB in the absence of process variations. 5.7 Conclusion and Outlook. This work presents key building blocks for low jitter, mode-locked lasers integrated in a silicon photonics platform. The rare earth doped amplifier design allows for a large mode area within the gain film of up to 102 and saturation energies of about 5J, all within a footprint of less than 10-2. We also developed and characterized dispersion compensating and chirped gratings with a reflection bandwidth of over 150 and a group delay dispersion engineered to be flat across that spectrum. Additionally, we demonstrated a passively Q-switched laser fully integrated in this platform. This laser uses a large mode area waveguide amplifier, a nonlinear interferometer-based saturable absorber, and loop mirrors. It features pulse energies of over 150 Nj in the output waveguide outside of the laser cavity, with pulse widths of 250 at 1.89. This represents an improvement of 20 dB in pulse energy and a 40% slope efficiency, which is well above previously reported values for integrated Q-switched lasers. Although stable mode-locked operation is the ultimate goal, several factors limited its realization in this configuration. First, the effective modulation depth of the saturable absorber was low because it was operating near the peak of the NLI reflectivity curve. This resulted in sub% gain loss modulation, favoring long-pulse Q-switched behavior over the formation of ultra-short pulses. Second, the cavity used loop mirrors without dispersion compensation. Such Q-switch dynamics must be managed carefully to prevent excessive powers that could damage waveguides. Despite these limitations, these results validate the core building blocks of the integrated laser. Future iterations that incorporate dispersion compensating gratings are expected to enable the stable generation of femtosecond pulses, which is essential for enabled signal sampling. In addition to the mode-locked laser itself and its key components, this chapter reports the implementation of pulse interleavers, WDM multiplexers, and comb decimation filters implemented in the same platform that can be directly integrated with the laser and serve the implementation of electrical-optical signal processing systems such as photonic ADCs. Coupled resonator optical waveguide filters with a passband of 360 G, a large free spectral range of 1.44 T, and low insertion losses of 3.5 dB are implemented as an essential building block for 4-channel integrated time-interleaved photonic ADCs. In addition, a first iteration of comb decimation filters aimed at increasing the free spectral range of a broadband optical frequency, comb from 2.5 to 20 G, are reported, with a design study indicating a 3 dB bandwidth of 20, insertion losses of 3.5 dB, and an extinction of unwanted comb lines of over 20 dB to be reliably achievable within typical process variations. The first design iteration will be improved in the future with adiabatic bends. The authors would like to acknowledge funding from the German Research Foundation, DFG, for Project Ultra Assisted Analog-to-Digital Converters, 403,188,360, in the framework for the Priority 2111 Electronic-Photonic Integrated Systems for Signal Processing, from the German Federal Ministry for Research and Education for Project Scalable Photonic Circuits. Grant 3 ZU1106BA, in the framework of the Cluster 4 Future, and from the Horizon Europe under Grant Agreement No. 101,159,229, ICOMB. The authors would also like to thank Menhir Photonics SA for their support. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1R 2008, Analog to Digital Conversion in the Early 21st Century. John and Sons. Tuha A 1993, Noise of Mode-Locked Lasers. IEEE Quantum Electron 29-983-996. 3AJJG FX 2012, Optical Flywheels with Jitter. Photonics 697-100. 4Z KVV-SEBG 2016, a IIIV-on-C ultradense comb laser. Light 6, Article IDE 16260. 5J-AAF-AF-J 2019, Semiconductor Laser Mode Locking Stabilization with Optical Feedback from a Silicon PIC. J Technol 30 734-833494. 6 Fang D D Peng HG CAPP RNJ MJ JCWS 2025, 320G Photonic Electronic to Digital Converter ADC Exploiting Soliton. Light 14, Article ID 241. 7A Does AD, L, R, J 2024, Scalable Orthogonal Delay Division Multiplexed OEO Artificial Neural Network Trained for TADC Equalization. Photonics Raise 1285-105. 8A J 2022, CN Pulse Interleaver for Optically Enabled Analog to Digital Conversion, a device-to-system analysis with cyclic equalization. OptExpress 34444466. 9Li TH, A 2000 Oscillator Phase Noise, a tutorial. IAEJ Solid State Circuits 35-326-336. 10J FX 2010 Precision Photonics. Laser Photonics Rev 43432-456. 11R 1999, Analog to Digital Converter Survey and Analysis. IAEJ Areas, 174539-550. 12B 2025, ADC Performance Survey 1997-025. COM ADC Survey. 13A Spectre SJ Grain ME, AH CW Sandermai, MS Pengmai MW Na JU AJS JP CM MA Sunjay Jo GR HJ JL Smith HI Ram RJ MTM EP FX 2012 Photonic ADC, Overcoming the Bottleneck of Electronic Jitter. OptExpress 24445-44469. 14P FFGA PINA SDC MAVEFA 2014, a fully photonics-based coherent radar system. Nature 507, 7492-341-345. 15 Su S X Ma B J L W 2019, Deep Learning-Powered Photonic Analog to Digital Conversion. Light 81, Article ID 66. 16D XYZ Li Z 2023, Photonic Sampled and Quantized Analog to Digital Converters on Thin-Film Lithium Platform. OptExpress 30-12193-11942. HDSAJ IP FX 2009, Integrated Low Jitter 400M Femtosecond Waveguide Laser. IEEE Photonics Technol, 2112-763-765. 18K PT Lien, EASE A D FX Watts Mr. EP 2019, Integrated CMOS-compatible Q-switched mode-locked lasers at 1900 with an on-chip artificial saturable absorber. OptExpress 27-3354-23556. 19 Sing N, E, FX 2020 towards CW laser on chip, a large mode area and NLI for stretched pulse mode locking. OptExpress 28-1522-56222579. 20 Sing N J M K A C H C S Francis H J M M A Hare T Bradley JDB Sun Z SM FX 2024 Silicon Photonics based high energy passively Q switched laser. Photonics 18-485-491. 21ATDET-MFP J 2021 Silicon nitride PIC-based multicolor laser engines for life science applications. OptExpress 296863586553. 22 Sing N J K M A M Francis H M M Hair T S M FX 2025 a watt class silicon photonics based optical high power amplifier. Photonics 1933-07314. 23 Richardson DJ J WA 2010 high power fiber lasers, current status and future perspectives. J Opt Soch AMB 2711 B63 B92. 24 Sing N J K M A M Francis H M M Hair T S M AL 2025 B watt class silicon photonics based optical high power amplifier. Photonics 1933-07314. 25 Sing N J M K M Francis H J M U M AL 2025 C sub 2 W tunable laser based on silicon photonics power amplifier. Light 14-1 Article ID 18. 26 Becker PM AA Simpson Jr. 1999 erbium doped fiber amplifiers, fundamentals and technology. 27 M FPJ Hammer DN MA Hair T Sing N FX 2025 dispersion compensating silicon nitride waveguide gratings for ultra-short pulse compression. In laser science to photonic applications, CLEO. 28A JSP FangD JCC J 2020 fundamental limitations of sliced optically enabled data converters arising from MLL timing jitter. OptExpress 2813 18790 29 MA FMIR V Co P S 2025 high performance hybrid lithium electro-optic modulators integrated with low loss silicon nitride waveguides on a wafer scale silicon photonics platform. 250400311. 30AJ BAL 2019 open access silicon photonics platforms in Europe. IEEJ Select Top Quantum Electron 25, Article ID 8,200,818. 31 Young IT, Van LJ 1995, Recursive Implementation of the Filter. Signal Process 44 139 151. 32R SG Watts RT AL 2012, High Performance Mode Locking Characteristics of Single Section Quantum Dash Lasers. OptExpress 286498657. 33A JAL 2018 8-channel WDM silicon photonics transceiver with SOA and semiconductor mode-locked laser. OptExpress 2625446254559. 34J VMYD Hertie KP LJ DRC RWJ TJ C 2014 Coherent Communications with Frequency Combs. Photonics 85375-380. 35P MD MHP A Wolf SJP CSW TJ C 2018 Optical Ranging using Soliton Frequency Combs. Science 359 6358887 891. 36D FangD A Peng HC TGT WS TJT C 2025 Optical Arbitrary Waveform Generation using actively phase-stabilized spectral stitching. 241209580. 37A J 2024 Chip-to-chip orthogonal delay division multiplexed network with optically enabled equalization. J Technol 40 222 793 77953. 38J NM H Lee X M M X A Raja ASJ Right CD A TJ PWHP H 2021 Parallel Convolutional Processing using an Integrated Photonic Tensor Core. Nature 589 5258. 39 TJ Al M ML 2018 Dissipative Solitons in Optical. Science 361 6402 Article ID 8083. 40A W Li T M AN YG 2011 Optical Fiber Pulse Rate Multiplier for Phase Noise Signal Generation. Opt 3618 3654 3656. 41T T 2022 mode spacing multiplication of optical frequency combs without power loss. OptExpress 301909019099. 42S AJ Shen B F J 2018 multi-stage Crow filters with relaxed fabrication tolerances. OptExpress 264472344737. 43Y AST K 2017 mode filtering of a fiber-based optical frequency comb with long fiber-based ring resonator for repetition rate multiplication. In 2017 Conference on Lasers and Electro-Optics Pacific Rim, CLEOPR. 44W P Van T K STP P Van D R 2012 Silicon Resonators. Laser Photonics Rev 6 14773. 45R Prince S 2018 Analysis of Serial and Parallel Cascaded Resonators, an FDTD approach. 152 3648. 46S YK Pan Z X X 2024 Integrated Waveguide Coupled Loss Waveguides based on silicon nitride resonators. OptExpress 302217922187. 6. Stitch Spectrum Nonlinear Frequency Division Multiplex Transmission Systems using Photonic Integration. Abstract. We present the concept and design of a nonlinear frequency division multiplex transmission system in which a broadband nonlinear spectrum is stitched together with help of a photonic integrated circuit. 4 independently modulated WDM channels are linearly multiplexed together with trapezoidal filtering and partially overlapping spectra, approximating a seamless nonlinear spectrum in which guard bands are avoided. We show that this approach mitigates the problem of nonlinear interaction between the channels, enabling more efficient use of the available spectrum. The system is highly scalable and allows for add-drop multiplexing using optic-electronic-optic signal processing. Different forms of nonlinear spectrum modulation are discussed, and the system is simulated to establish its performance limits. A data rate of 400 is shown to be supported over 800 with single polarization modulation and a spectral efficiency of 4 bs, with a BER staying below the SDFEC limit for every subcarrier. Acronyms: Analog to Digital Converter, Advanced Micro Foundry, Amplifier, Active Phase Control, Amplitude Phase Frequency Shift Keying, Amplitude Phase Shift Keying, Amplified Spontaneous Emission, Amplitude Shift Keying, Arbitrary Waveform Generator, Bit Error Ratio, Balanced Photodiodes, Bandwidth, Coupled Ring Resonator Optical Waveguide, Digital to Analog Converter, Direct Current, Directional Coupler Splitter, Digital Signal Processing, Deep Ultraviolet, Electro-Optic, Erbium-Doped Fiber Amplifier, Eigenvalue, Error Vector Magnitude, Filter Bank Multi-Carriers, Frequency Shift Keying, Free Spectral Range, Grating Coupler, Grounded Coplanar Waveguides, Hard Decision Forward Error Correction, Input-Output, Insertion Loss, Inverse Nonlinear Fourier Transform, Quadrature, Interchannel Crosstalk, Local Oscillator, Multi-Mode Interferometer, Minimum Mean Square Error, Mach Modulator, Nonlinear Frequency Division Multiplexing, Nonlinear Fourier Transform, Nonlinear Equation, Neural Network, Optical Add-Drop Multiplexer, Optical Delay Line, Optical Electrical Optical, Orthogonal Frequency Division Multiplexing, Optical Hybrid, Optical Spectrum Analyzer, Printed Circuit Board, Photodiode, Photonic Integrated Circuit, Phase Noise, Phase Shifter, Power Spectral Density, Phase Shift Keying, Quadrature Amplitude Modulation, Resolution Bandwidth, radio frequency, relative intensity noise, subcarriers, soft decision forward error correction, space division multiplexing, spectral efficiency, system and package, silicon on insulator, standard single-mode fiber, support vector machine, thermoelectric cooler, wavelength division multiplexing. 6.1 Introduction. Capacity limit of optical fiber communication systems. General structure of a single-channel long-haul NFDM transmission system. CS continuous spectrum DS discrete spectrum. Figure 6.2 shows the generic architecture of a single-channel long-haul NFDM transmission system. The hardware components are the same as in a conventional coherent system, so that the only difference is in the signal processing part. In the transmitter, modulated nonlinear spectra are generated in the form of overlapping and mutually orthogonal functions, transformed into the time domain using the inverse INFT, and processed further like any other time domain signal. After applying the NFT in the receiver, the linear phase rotation is applied before the data is extracted. Other basic steps such as timing synchronization, carrier frequency offset compensation, and phase noise compensation are not shown in this diagram, but are also necessary as in any real system. Despite the intensity of previous research efforts, there are still significant challenges that need to be overcome in order to outperform conventional systems in realistic scenarios. Lumped amplification with erbium-doped fiber amplifiers, EDFAs, in existing infrastructure and nonlinear noise-noise interaction 21, in particular break the regularities of the NFT and present significant obstacles towards achieving higher SC. This has motivated further research into more advanced data processing methods such as neural networks 22-26, probabilistic shaping 27-28, or the use of different subcarrier waveforms 29-31. State-of-the-art NFT-based transmission systems are able to achieve data rates of up to 20.48 s using wavelength division multiplexing, WDM32, 1.004 s with only a single channel 33, and a spectral efficiency of 7.72 bs has been demonstrated for a single polarization system using filter bank multicarriers, FBMC 31. However, most of the work has focused on single-channel transmission with limited bandwidth, and scaling over large spectra, such as the entire C-band, remains an important challenge. The achievable bandwidth is generally limited by the finite modulation speed of electro-optic EO components, and by the high computational complexity of the INFT for signals with a high number of samples 34-35. The combination of NFDM with WDM is not a straightforward solution to this issue because there are no nonlinear multiplexers available, and linear multiplexing requires guard bands between the channels to avoid nonlinear interchannel crosstalk IXD 32, 36, 37. EO bandwidth limitations can be overcome by stitching together spectral slices 38, 39, as already applied to NFDM systems 40, but this does not solve the problem of an impractically high computational complexity. Additionally, solutions have to be found to enable add-drop multiplexing in the framework of NFDM. In the following, we will present a transmitter concept for NFDM-WDM transmission using a photonic integrated circuit, PIC, that overcomes the bandwidth and computational limitations outlined in the previous paragraph. Individually generated and overlapping nonlinear spectra are combined with a weighted average in the linear domain, so as to mitigate the IXD between them 41-43. Guard bands are no longer required, so that all available bandwidth can be used for data transmission, and the SC is increased. The computational complexity of the NFT is kept low, since digital signal processing, DSP, is applied separately to the individual channels. Since spectral stitching requires the relative phases of the different channels to remain stable, implementation of the transmitter with a PIC is highly advantageous over a hybrid fiber optic system. Our solution is highly scalable and is only limited by physical layouting constraints and heat sinking of the PIC. This system architecture concept is also flexible, as it can be extended to allow for add-drop multiplexing using optic-electronic optic circuits 44-48. The chapter is structured as follows. Section 6.2 gives a basic overview over the NFT and the modulation of the two nonlinear spectra. Next, we describe the challenges when building a WDM-NFDM transmission system and present our transmitter concept in Sect. 6.3. The details for its practical implementation are described in Sect. 6.4. After that, we validate the concept through realistic simulations in Sect. 6.5 and extend it to more flexible systems with nonlinear add-drop multiplexing in Sect. 6.6. Section 6.7 concludes and gives an outlook for further work. 6.2 Nonlinear Fourier Transform Basics. This section describes the fundamentals of the NFT and the modulation of data onto the nonlinear spectra. 6.2 Mathematical Background. 6.2 Continuous Spectrum Modulation. Nonlinear continuous spectra resulting from the different methods of modulation. A Q modulation, B modulation, C modulation with transform. 6.2 Discrete spectrum modulation. A modulated discrete spectrum with one eigenvalue. B resulting time domain signal. 6.2 Full spectrum modulation. A modulated continuous and discrete spectrum. B resulting signal in the time domain. C corresponding linear spectrum. 6.3 Transmitter concept. Block diagram of an NFDM-WDM transmission system. BER versus spectral guard band width for a two-channel NFDM-WDM system with 100 subcarriers each. Mean EVM of the subcarriers at the edge of the spectrum versus spectral guard band width. From these simulations, it is clear that there is a significant performance degradation in the subcarriers situated at the edges of the NFDM channels, if these are linearly multiplexed with insufficient guard bands. Hence, it is crucial to find new ways to linearly multiplex the NFDM channels that can mitigate IXD even when channels are independently processed by the INFT. To that effect, we propose a solution whose key concept is to increase the bandwidth of the independently generated NFDM channels in the nonlinear Fourier domain so as to create a spectral overlap between neighboring channels. Subcarriers placed in the overlap regions are loaded with the same data and are processed twice, once for each channel they belong to. Shaped nonlinear spectra with central lobes in the color-coded overlap regions in Fig. 6.9 are thus identical. Note that there are still differences in the overall spectra shown in these regions due to the adjacent subcarriers from outside the overlap region, as they also extend to it, and they are different for the two channels. After mapping to the linear domain with the INFT, linear filters with a trapezoidal-shaped amplitude transfer function are applied. The ramp-shaped filter edges located in the spectral overlap regions sum up to 1 and effectively define a weighted average that assigns, for each, a stronger weight to the INFT of the channel that includes the highest number of neighboring. This provides a gradual transition from the results of one INFT to the other, while accounting for the nonlinear interaction of the subcarriers with their nearest neighbors from within the overlap region and from the neighboring channels. Finally, the resulting signals are modulated and linearly combined in the optical domain. Diagram of the signal generation flow. F refers to the linear frequency and HF to the filter transfer functions 41. This novel concept, first proposed in 41-43, alleviates some of the constraints limiting current NFDM systems. I/EO modulator bandwidth requirements are reduced by splitting the spectrum over multiple channels. The overall computational complexity is reduced by applying individual INFTs to individual channels, and nonlinear interactions are accounted for in a seamlessly stitched spectrum. One of the challenges of this approach is that the individual NFDM channels have to be coherently added up in the optical domain so that the signal does not get destroyed in the overlap regions. This can be achieved using phase-coherent carriers, such as generated by combs as also used in more conventional WDM systems 58, to generate the individual optical channels and by dynamically correcting residual phase errors before multiplexing. By synchronizing the repetition rate of the comb with the clock used to generate the electronic signals and balancing the optical paths implemented on the PIC, long-term stability of the system can be obtained 38. The phase errors introduced by the different optical paths inside the PIC prior to multiplexing of the channels can be corrected using active phase control, APC, as demonstrated in 39. The main drawback of the cascaded solution presented there is that it scales poorly with the number of channels due to the 6 dB losses introduced in each stage. Block diagram of the cascaded multiplexing concept, in which active phase controllers are used to maintain the phase coherence between adjacent channels 41. In order to establish phase coherence between the channels, a small amount of light 1% is tapped off from the two buses every time a channel has been added to one of them and is fed to a 2x2 multimode interferometer, MMI, followed by a balanced photodetector pair. A feedback loop sets an upstream phase shifter, PS, that adjusts the phase of the added channel until the power levels recorded from the two photodiodes are equal, which is the interference condition corresponding to the added channel being in phase inside the overlap region, with the adjacent pre-existing one already present in the opposite bus waveguide. The PSs are recursively set until the entire spectrum is coherently combined. This concept can be scaled up to multiplex a large number of channels, and in its current implementation is primarily limited by the number of modulators that can be fit in the chip and by its overall thermal load, see sect. 6.4. 631 Receiver Architecture. Block diagram of the transmission system simulated for system concept validation. 632 Transmission with continuous spectrum modulation. Burr versus spectral overlap for 16 QAM transmission. Burr versus spectral overlap for 32 QAM transmission. Subcarrier EVM for 32 QAM without and with 4G spectral overlap. Figure 614 shows the EVM for each subcarrier without and with 4G spectral overlap for the 32 QAM modulation scenario. As expected, the subcarriers located at the edges of the channels are most affected, and their performance can be clearly improved by using this overlap technique at the cost of a slight increase in the required EO/BW per channel. 633 Transmission with full spectrum modulation. Up to now, only the continuous part of the nonlinear spectrum has been used to benchmark the spectral overlap concept. To investigate the performance when using the full spectrum, the 4-channel NFDM-WDM transmission system from the previous section was simulated again with the addition of a modulated discrete spectrum. The case with a 4G overlap is selected, resulting in channels with a bandwidth of 28G, each containing 112 16 QAM modulated subcarriers. The overhead of the three 4G overlap regions was equally split among the 4 channels to obtain equal channel bandwidth requirements. Subtracting the shared 3 4G in the overlap regions and the corresponding 316 duplicate subcarriers, this can be seen to correspond to the 100G 400 subcarrier overall capacity already explored in the previous section. In addition, the discrete spectrum consists of 2 eigenvalues per channel, with frequencies offset by 3 and 3G relative to the channel center, keeping them far from the edges of the channel spectrum, and thus reducing spectral clipping and dispersion-mediated broadening of the overall data block. Data is only modulated on the phase of B, using 16 PSK modulation. The spectral efficiency is therefore slightly increased compared to the previous case from 2.67 to 2.72 bs. BER of the continuous spectrum versus different eigenvalue amplitudes. EVM of the subcarriers in the overlap regions and around the eigenvalue frequencies versus different eigenvalue amplitudes. For a more detailed analysis on how the eigenvalues influence the transmission quality of the continuous spectrum, Fig. 6.16 shows the EVM of the subcarriers in the overlap regions and around the eigenvalue frequencies for different eigenvalue amplitudes. Figure 617 shows the EVM for all the subcarriers for normalized eigenvalue amplitudes of 0.75, 1.75, and 2.75. First, it can be seen that the EVM of the subcarriers is degraded most in the frequency regions around the eigenvalues, which has already been shown in 18. For lower amplitudes, fewer subcarriers are affected than for higher amplitudes, but the detrimental effect on these is significantly stronger. The reason for this is revealed when looking at the linear spectrum of solitons. A high amplitude leads to a wide spectrum, and thus to distribution of the power over many frequencies, while at lower amplitudes the power is strongly focused in a small spectral range. EVM of all subcarriers versus 3 different eigenvalue amplitudes. 6.4 Transmitter System Implementation. The implementation of the transmitter presents a number of challenges. Besides the design of a suitable silicon photonics PIC, which is the central component of the transmitter, the hardware needs to support the electrical connectivity required to bring in the radio frequency, RF, and control signals, as well as the chip-scale thermal stabilization required to maintain long-term phase coherence across the channels. A comb generator is also implemented with an EO setup 59 outside of the chip, with a Mach modulator MZM, converting a single carrier into a comb whose free spectral range, FSR, is determined by an RF signal synchronized with the clock of the remaining electronics. This guarantees long-term phase stability between the comb and the signal processing electronics, in particular the relative phase between comb lines referenced to the time base of the electronic clock. While such systems can also be implemented in silicon photonics PIC60, the chip-scale integration of the comb generator was not essential here, as all the comb lines travel down a single fiber up to the input port of the PIC, and the stability of their relative phases is thus not compromised. A block diagram of the PICs. B layout of the PIC 5 m 2.8 m 41. 641 Photonic Integrated Circuit. The system PIC is the central element of the proposed transmitter system. It implements EO modulation and the phase-coherent optical channel multiplexing. Here we describe the architecture of the PIC and its insertion losses and link budget. Device characteristics are based on detailed measurements of test structures located on the same chip that are also reported in the next subsection. Figure 6.18 shows the block diagram and the layout of the system PIC. As visible in Fig. 6.18, the PIC modulates and multiplexes up to 4 comb lines, but only 2 IQ modulators are implemented, one of which modulates the even channels and the other modulates the odd channels. Since the IQ modulators are implemented as balanced nested MZMs, with 2x2 MMIs used as splitter combiner at the input and output of the superstructure, 2 wavelengths with equal index parity can be injected and extracted from each modulator via the pairs of complementary input-output ports. Since coupling to the buses occurs via 4 ring crows, only the intended channel is injected into the buses at a given injection point. Sharing data streams across all the even and odd channels is a common method for the characterization of broadband fiber optic transmission in resource-constrained environments 61. Here it allows marginally shrinking the chip size. The 528M system chip has unused spaces on the 2 sides of the IQ modulator array filled with test structures that could have been allocated to further modulators. The more important benefit is that it reduces the number of required AWG channels to 4. The PIC has been designed into the 220 device layer thickness silicon photonics platform of Advanced Micro Foundry, AMF, Singapore, and is compatible with deep ultraviolet DUV lithography at a 248 wavelength 62. The comb lines are injected into the PIC using one of the grating couplers GCs located at the center of the chip, with an insertion loss IL of 3.75 dB once inside the PIC. Up to 4 comb lines are filtered using second-order Crow OADMs 3 dB BW8G, IL 3.5 dB. Up to 4 optical channels can be supported by tuning these in or out. After that, each carrier is independently routed to one of the 2 input ports of the 2 IQ modulators, as explained above. The IQ modulators are designed as nested MZMs with slotted transmission lines to improve the trade-off between 50 impedance matching and RF losses, interleaved waveguide delay loops, phase recovery loops, to improve the phase matching between the RF and optical signals, and a GSSG driving scheme that suppresses RF crosstalk between complementary phase shifters when operated in a push-pull configuration 63-64. Moderately high doping concentrations, 2-10183, are used to define the junctions inside the waveguides to obtain a high phase shifting efficiency 65 and compact rectilinear phase shifters 1100. Each of the 8 high-speed phase shifters are 50 terminated directly on chip. The IQ modulators have an EO cutoff frequency above 25 G and an optical IL and modulation penalty of 14 dB for a 2-drive voltage, defined here as the ratio of the maximum optical power at their output with the power at their input, when the nested MZMs are biased at the zero transmission point, and comprises the 3 dB losses associated to the coupler combining the I and Q signals. After modulation, even and odd channels are injected into the two buses using fourth-order Crow filters, 3 dB BW 32G, IL 2 dB, architectured following the design approach in 66, so spectral crosstalk in each bus can be neglected. After each filter, a small portion of the signal, 1%, is coupled out from each bus and sent to one of the APCs. These consist of a 2x2 MMI, a balanced photodiode pair BPD, and a phase shifter applied to the corresponding IQ-MZM output, as seen in Fig. 6.18. Diagram of the waveguide routing in the multiplexer. Finally, even and odd channels are combined from the two buses using a 2x1 MMI IL 3 dB, and the signal is coupled out to a fiber using a second GC IL 3.75 dB. The total losses of the PIC, including the IL from all components, the modulation penalty, and the cumulative losses of interconnect waveguides and monitor taps, IL 3.5 dB, are 33.5 dB. This IL can be directly improved by using a higher drive voltage, e.g. 4 that reduces the IL and modulation penalty from 14 dB to 10.5 dB. Further improvements require a redesign of the PIC. For example, changing the optical IOs from GCs to edge couplers can reduce the cumulative IO losses from 7.5 dB to 3 dB micrograph of the fabricated PIC. A transfer function to the Crow OADMs drop port after spectral alignment of the rings. BMZM phase shift when applying a DC voltage to a single arm. See normalized S21 of the MZM. 642 Comb source implementation and measurements. Block diagram of the comb source generator. A optical spectrum, BRF spectrum and CRIN of the generated comb. The optical spectrum measurement in A is limited by the RBW of the OSA. PCB multilayer stack concept. 643 RF and control PCB implementation. The RF printed circuit board, PCB, has been fabricated in a multi-layer stack that supports high-density routing of the RF and control signals, see Fig. 6.24. The RF transmission lines are implemented as grounded coplanar waveguides, GCPW, in the top two conductor layers, with the thin interlayer dielectric allowing to shrink the lateral dimensions of the GCPW and enabling a compact pad frame that matches that of the PIC. Control signals are routed through the bottom two conductor layers. An opening provided in the PCB allows placing the PIC directly on the underlying heatsink, which is required due to the high hit load of the PIC. That comprises a total of 39 thermally tuned phase shifters, which require between 29 MW PS embedded in the rings and 44 MW PS embedded in the MZMs, each to reach a 2-phase shift and 850 terminated high-speed phase shifters that consume 40 MW each when driven with a 2 signal. Since PSs are actuated to an average phase of and only half of the PS, configured in push-pull configuration, are actuated in the IQ modulators, the total power dissipated in the chip is W. In order to minimize the length of the wire bonds, a thick substrate core is provided so that the surface of the PIC is flush with that of the PCB. The overall temperature of the PIC is controlled by a thermoelectric cooler, TEC, placed at the bottom of the aluminum board serving as a heat sink. 6.5 System Setup and Simulation Results. In this section, we model the performance of the proposed system, taking into account transmitter and receiver non-idealities, i.e. the optical losses of the PIC, the excess amplified spontaneous emission, ASE noise resulting from pre- and post-amplifying the light before and after the PIC, the RF and optical of the comb, the transfer functions of the OADMs, the cutoff frequency of the IQ modulators, and the of the local oscillator laser in the receiver, in addition to the non-idealities already considered in SECT. 6.32. A drawback of sharing equal data streams across even and odd channels is that dispersion precompensation cannot be applied. To determine how much this will handicap the experiments, we also run models with and without precompensation, wherein the former assumes a PIC with 4 independent IQ modulators. Block diagram used for the simulation of the transmission system, including the transmitter and receiver non-idealities. On the optical side of the system, the EO frequency comb provides 4 optical carriers with an FSR of 25G, an optical below 100K, an RF below 1, and a power per line above 10D. Since the comb is already preamplified, as shown in the diagram in Fig. 6.22, it would in principle be possible to amplify it further, so that the power is limited by the damage threshold of silicon-on-insulator SOI GCs instead, which is in the order of 1820D. The total comb power of 16D is thus chosen to remain below it with an adequate safety margin. Given the overall PIC loss and modulation penalty of 33.5 dB, see Sect. 641, the multiplexed NFDM channels have an average power level of at the PIC output, which is reamplified with a second EDFA by setting the output power to 0D to reach the optimal launch power before being sent over 12 spans of 80 SSMF, as in the link configuration assumed in Sect. 6.3. Burr versus spectral overlap for 32 QAM transmission, with the SDFEC limit indicated in black. Comb lines are injected with 10D into the PIC. Investigated scenarios include using or not using precompensation at the transmitter, and using MMSE or SVM equalization at the receiver. Figure 626 shows the simulated BER versus the spectral overlap, as obtained after applying MMSE and SVM equalization when the comb source is set to inject 10D per line. There is a clear improvement once overlap of more than 12G is applied, but the performance remains above the SDFEC limit of 210.2 for MMSE equalization. Therefore, higher performing equalization techniques such as SVMs or neural networks, NN, are required. In general, the obtained results are slightly worse than the ones we previously presented in 41. There are several reasons for this. The comb source we have finally implemented offers higher output power, but also a higher optical compared to the initially assumed 100K versus 20K. The PIC losses are 3.5 dB higher based on actual measurement data, and SVM with a linear kernel equalization is a much faster technique, but improves the BER less than NNs. It is interesting to note that the SVM equalization performs better in the absence of precompensation, similarly to what was observed for NN equalization in 41, but in contrast to how MMSE equalization behaves. 6.6 Add-drop multiplexing concept. Routing is an essential capability that is required to send data to its intended destination in communication networks. In conventional WDM systems, this is typically done by using add-drop multiplexers, which are able to add or drop a channel at a certain point in the network. The application of this concept to NFDM is illustrated in Fig. 6.27. Multiple channels are created and multiplexed together in the NFDM transmitter. When using guard bands as shown in the upper spectra, the function of the add-drop multiplexer is the same as for conventional systems. Since each channel is separate and independent from the others, it can easily be filtered out and a new channel can be added in the vacated space. However, in our case, we generate a seamless spectrum, as shown in the lower spectra in Fig. 6.27, so that this method cannot be applied directly if only a portion of this spectrum is to be replaced. The channels are not independent from each other, so that information from the neighboring channels is needed to create and add a new channel. Due to this dependency, the new channel must also be placed in the same time slot as the dropped one, constraining the operation further. Add-drop multiplexing for WDM, NFDM transmission systems. The spectra in the top row represent the case of NFDM channels with guard bands, while the spectra in the bottom row represent the case of a seamlessly stitched spectrum. 661 Add-drop multiplexer architecture. In the following, we present a concept for applying this add-drop multiplexing operation to a seamless NFDM spectrum, adapting the spectral overlap concept to this context in a manner that can also be supported by a PIC-based realization. The system architecture is an extension of an optical-electrical-optical OEO interferometer previously applied to a similar problem in the linear spectrum 48, and is shown in Fig. 6.28. It should be noted that for the NFDM receiver, it makes no difference if add-drop multiplexing has been applied or not. The signal is and demodulated in the same way as in the previous sections. In the OEO interferometer, the incoming optical signal is split using a 3 dB splitter, after which one path is delayed using an optical delay line, ODL, e.g. an SSMF loop, while the other path is coupled into the PIC, where a Crow filter selects the channel to be replaced together with a portion of the surrounding spectrum as needed to be known to perform the nonlinear add-drop multiplexing operation, as explained in the following. A laser is provided as a local light source, whose output is also split to function as the local oscillator of a receiver used to analyze the incoming spectrum, and as the carrier for a transmitter used to generate a signal that cancels and replaces the dropped channel. Once the spectrum selected by the Crow filter has been digitized, DSP is used to compute a signal that, when coherently combined with the original signal, will remove the target channel and add a new one. This signal is then converted back to the optical domain and amplified with an EDFA to reach the necessary launch power. A 2-2 directional coupler splitter, DCS, finally combines the new signal with the delayed original one. The delay introduced by the ODL that is applied to the initial optical signal before the DCS is matched to that of the DSP part, so that the resulting summation cancels out the channel to be replaced and coherently replaces it. Since the coherent receiver and the IQ modulator share the same laser, its phase noise, PN, is first applied in a phase-conjugated manner during coherent detection, after which is it applied in a non-phase conjugated manner during the optical signal generation, so that its PN can be cancelled as a net result. For this to hold true, a second ODL applies a delay to the local laser, prior to feeding it to the IQ modulator, that is also matched to the DSP part. Additional dynamic phase errors caused by the propagation through the two optical fiber loops can be corrected using a phase shifter, PS, cascaded with the output of the IQ modulator 45. This phase correction is controlled by measuring the power of the combined signal at the complementary port of the DCS with a monitor photodiode, PD. Since the subtraction of the cancellation signal from the original one within the main optical signal path corresponds to a coherent summation at the monitor, the power detected by the PD has to be maximized by the control system. Block diagram of the PIC-based add-drop module. Additional discrete components are shown in black, the PCB in blue, and the PIC in orange. In principle, the cancellation signal could be generated from the data transported by the dropped nonlinear channel. To recover the dropped channel taking nonlinear interaction into account, the analyzed linear spectrum, as provided at the drop port of the OADM, would then need to contain at least the channel with its two adjacent overlap regions, with some additional subcarriers added from the adjacent channels to account for nonlinear interaction. The cancellation signal could then be generated from that data following the DSP flow of the transmitter. This approach may, however, be compromised by noise and attenuation occurring in the fiber link that break the regularities of the NFT. To circumvent this difficulty and facilitate data processing, the cancellation signal is directly generated from the recorded linear spectrum without using the NFT framework. For this data processing flow to work without excess penalties, any region of the linear spectrum that contains spectral content of the dropped nonlinear channel needs to be fully extinguished. In order to achieve this, the width of the trapezoidal filters used in the OEO interferometer, that also defines the range in which the initial signal is extinguished, is widened compared to the one used in the transmitter, with the filter's flat top region now also encompassing the initial overlap regions and with new overlap regions defined at their edges. This extended filter bandwidth configuration is illustrated in Fig. 6.3. The extended filter is applied to the recorded spectrum to generate the cancellation signal that is to be subtracted from the main signal path. Without this bandwidth extension, spectral content of the dropped channel would remain and would interfere with the new data. Since the new overlap regions now extend into the adjacent channels, the of the added spectrum also needs to take of the adjacent channels into account in a wider range, including the new overlap regions. These have thus first to be known and need to be extracted from the incoming signal. This further broadens the spectral range that has to be provided by the OADM multiplexers beyond the outer edges of the extended filters to adequately take nonlinear interaction into account. Additional steps are also necessary in the DSP part to recover these adjacent. Therefore, the whole receiver DSP has first to be applied as depicted in Fig. 6.29. The added spectrum is generated by applying the INFT to the added channel concatenated with the adjacent subcarriers of the adjacent channels and feeding the result to the trapezoidal filters with extended bandwidth. DSP chain for the PIC-based add-drop module. Extended filter bandwidth configuration. 662 add-drop multiplexing with continuous spectrum modulation. Block diagram of the simulated transmission system, including add-drop multiplexing. EVM per subcarrier with and without phase noise imprint. EVM per subcarrier with an extended filter bandwidth. Figure 632 shows the EVM per subcarrier with and without PN imprint. It can be seen that the PN imprint is essential and that data cannot be transmitted in the overlap regions without it. This is expected, as explained above, because phase differences lead to random interference conditions in the overlap regions. The change in performance resulting from extending the add-drop filter bandwidths is depicted in Fig. 6.33. Here too, the stark change in performance at the edges of the channel is expected. Burr per subcarrier with MMSC and SVM equalization using 400 or 800 subcarriers. These results show that the add-drop concept is sound and can be used to increase the flexibility of NFDM-WDM transmission systems with seamless spectra. If in addition to the continuous spectrum, the discrete spectrum is also to be used for data transmission, some additional important points have to be considered. 663 add-drop multiplexing with full spectrum modulation. The simulation setup models the same hardware as before, with the continuous spectrum created to contain again a total of 400 subcarriers with 4G overlap regions. The subcarriers are now modulated with 16 QAM, to which a discrete spectrum consisting of 2 eigenvalues per channel with I175, which proved to be optimum in sect. 633 is added. However, in comparison to sect 633, more degrees of freedom are used to increase the SC. The amplitude time position B is 16 ASK modulated, the phase B is 8 PSK modulated, and the soliton frequency R is 32 FSK modulated, resulting in an overall modulation format of 4096 APFSK per eigenvalue. This leads to a total data rate of 282.67, and the SC is therefore increased from 2.72 bs to 2.83 bs. The equalization in the receiver is done using an SVM for the continuous spectrum and an MMSC for the discrete part. In order for the frequency modulation of the eigenvalues to feature a high contrast, the frequency range should be as large as possible. However, it must be ensured that solitons are not positioned too close to the channel boundaries, as otherwise their spectrum will be excessively clipped by the trapezoidal-shaped filtering. This not only leads to the discrete spectrum, but also to the continuous spectrum to feature an increased burr, as this also compromises the between the two. This is especially important to consider in the context of add-drop multiplexing, as the extended bandwidth of the filters further constrains the spectral range available to the soliton pulses of the adjacent channels. Even if the solitons are positioned adequately in the transmitter, this can again lead to a partial clipping in the add-drop multiplexer for channels adjacent to the one being replaced, as shown in Fig. 6.35, since the extended filter encroaches deeper into them. Moreover, the reconstruction of partially clipped soliton pulses in the add-drop multiplexer would require a very significant EO bandwidth increase, as the channels adjacent to the one being replaced would then also need to be fully recovered. Consequently, the possibility of add-drop multiplexing must already be taken into account in the transmitter when designing the modulation format. Comparison of solitons partially overlaying the overlap region before and after trapezoidal-shaped filtering. BER of the different modulated spectral components of the NFT for varying highest eigenvalue frequency modulation. CS spectrum or overlap region. Continuous spectrum BER for each subcarrier for different highest eigenvalue frequency modulation. 6.7 Conclusion and Outlook. We have presented a WDM-NFDM transmission system which uses spectral overlap between adjacent channels to mitigate nonlinear inter-channel crosstalk. This highly scalable concept uses the whole available spectrum since no guard bands are required. We have numerically evaluated its performance with a 4-channel WDM system, seamlessly filling a 100 G spectral range using both continuous and full spectrum modulation. Flexibility of the system is increased by an add-drop multiplexer concept, which is compatible with the replacement of nonlinear channels in this seamless spectrum. The performance of the system was evaluated using different modulation formats and equalization schemes, showing that the system can achieve high spectral efficiencies of 4bs using the continuous spectrum with a single polarization over 800, applying a simple SVM equalization with a linear kernel. Further improvement may be possible by using neural network equalizers, dual polarization, and probabilistic shaping. The WDM-NFDM link has also been simulated taking the non-idealities of a fabricated transmitter PIC into account. As expected, the overall performance decreases a bit, but we achieved also here a burr remaining below the SDFEC limit with SVM equalization using the 400 subcarrier configuration, SC of 3.33 bs. The concepts described here are not only applicable to the framework of the nonlinear Fourier transform, but to any optical signal processing scheme in which wide seamless spectra are to be launched with nonlinear precompensation. As such, they may be instrumental in increasing the data throughput beyond the current limitations of the nonlinear Shannon limit in future communication systems in a more general nonlinear signal processing and synthesis context. The authors would like to acknowledge funding from the German Research Foundation, DFG, for Project Nonlinear Fourier Transform-based optical transmission using electronic-photonic signal processing, 403,153,975, in the framework for the Priority 2111 Electronic-Photonic Integrated Systems for Signal Processing. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 RJG PJ Al 2010 Capacity Limits of Optical Fiber Networks. J Technol 2846622701. Org 101109 JLT2 0092039464. 2 BJG RS 2021 Space Division Multiplexing for Optical Fiber Communications. 8911861203. Org 101364 OPTICA 427631. 3SK JE SD Al 2017 Nonlinear Fourier Transform for Optical Data Processing and Transmission, Advances and Perspectives. 4330732. Org 101364 OPTICA 4000307. 4 GUI T C Apt Al 2017 A high-order modulation on a single discrete eigenvalue for optical communications based on nonlinear Fourier transform. OptExpress 2517-202862027. Org 101364 OI 25020286. 5 GUI T TH C Al 2017b Alternative Decoding Methods for Optical Communications based on Nonlinear Fourier Transform. J Technol 30 59154215550. Org 101109 JLT 201726544493. 6M H Suzuki KL 2000 Recent Progress in Soliton Transmission Technology. Chaos 10-34-86-514. Org 10-10-63-113-11394. 7S AM de EP Al 2018 Dual Polarization Nonlinear Fourier Transform-Based Optical Communication System. 532-63-270. Org 10-1364 OPTICA 5000263. 8AJ O Al 2022 Silicon Photonic Integrated Circuits for Soliton-Based Long-Haul Optical Communication. J Technol 40 10-32103222. Org 10-1109 JLT 202-23170-250. 9MI FR 2014 Information Transmission Using the Nonlinear Fourier Transform Part ISI. IIEA Trans, Theory 6743124369. Org 10-1109 TIT 20-14232-1143 MathNet. 10 SD-V, H 2018b, High-Speed Precompensated Nonlinear Frequency Division Multiplex Transmissions. J Technol 30-66129611303. Org 10-1109, JLT 20-172787185. 11X-V, SD Al 2018, 400 Dual Nonlinear Frequency Division Multiplex Transmission with B-Modulation. In Proceedings of the 44th European Conference on Optical Communication, ECOC, Rome, Italy, 23-27 Sept 2018. Org 10-1109, ECOC 201885355128. SD-V, H 2017, Nonlinear Signal Multiplexing for Communication Beyond the Nonlinearity Limit. Photonics 11-575-76. Org 10-10-3820-17118. 13JW, MI, Y Al 2017, Polarization Division Multiplexing based on the Nonlinear Fourier Transform. OptExpress 25-22-643-7264552. Org 10-1364-OI, 25-0-26437. 14 SD, K, F Al 2018, a 100 B-modulated nonlinear frequency division multiplex transmission. In Proceedings of the Optical Fiber Communications Conference and Exposition, OFC, San, USA, 11-15 Mar 2018. Org 10-1364 OFC 20-18W1G6. 15X SD, V Al 2019, a experimental demonstration of dual polarization NFDM transmission with B-modulation. IEZ Photonics Technol 3111-885-888. Org 10-1109, LPT 20-1929111600. 16Q, FR 2021, Correlationated Nonlinear Spectrum Detection. J Technol 39-1549234931. Org 10-1109, JLT 202-130-78700. 17V, SD, H 2016, Demonstration of Fully Nonlinear Spectrum Modulated System in the Highly Nonlinear Optical Transmission Regime. In Proceedings of the 42nd European Conference on Optical Communication, ECOC, Germany, 1822 Sept 2016. Org 10-4855-0-16110-8420. 18V, SD, H 2018, Modulation over Nonlinear Fourier Spectrum, Continuous and Discrete Spectrum. J Technol 36-612-891295. Org 10-1109, JLT 20182-794475. 19R Xi L, X Al, 2022, B First Demonstration of 113S Full Spectrum Modulated Nonlinear Frequency Division Multiplexing Transmission System. In Proceedings of the Conference on Lasers and Electro-Optics CLEO, San, USA, 15-20 May 2022. Org 10-1364 CLEO C2022 SM2J5. 20 Wei J Xi L, X Al, 2022, Improvement for a Full Spectrum Modulated Nonlinear Frequency Division Multiplexing Transmission System. OptExpress 3017-3119531208. Org 10-13640E 465574. 21M, A, SA Al 2020, Signal Noise in Optical Fiber Communication Systems employing Nonlinear Frequency Division Multiplexing. Rev 1350-54021. Org 10-1103, Rev Applied 13054021. 22WQ, TH, SA 2022, a serial and parallel convolutional neural network schemes for NFDM signals. Rep 127962. Org 10-10388S4159802-21211414. 23X Ming H. Li C. Al 2021, a two-stage artificial neural network-based burst subcarrier joint equalization in nonlinear frequency division multiplexing systems. Opt 467170011703. Org 10-13640L422195. 24O-M, M. Al 2021, convolutional long short-term memory neural network equalizer for nonlinear Fourier transform-based optical transmission systems. OptExpress 29-711254-11267. Org 10-13640E4-19314. 25O-M, M. Al 2020, combining nonlinear Fourier transform and neural network-based processing in optical communications. Opt 4513-3462-3465. Org 10-13640L394115. 26L Y Han L Al 2024, CNN-based equalizer in NFDM system with B-modulation. In Proceedings of the 22nd International Conference on Optical Communications and Networks, ICOCN, Harbin, China, 26-29 July 2024. Org 10-1109 ICOCN 632766202-410648-413. 27 Wei J. Zai L. X. Al. 2021, Probabilistic Shaping and Neural Network-Based Optimization for a Nonlinear Frequency Division Multiplexing System. Opt 46-1536-9737000. Org 10-13640L430859. 28 Li C. X. Z. Al. 2021, Capacity Increase in Dual Polarization Nonlinear Frequency Division Multiplexing Systems with Probabilistic Shaping. In Proceedings of the 26th Optoelectronics and Communications Conference, OECC, 3-7 July 2021. Org 10-13640 OECC 202, 1W1B2. 29M, S 2022, a nonlinear spectral carriers for optical communication systems employing the nonlinear Fourier transform. IEEE 2611091112. Org 10-1109 LCOMM2 0213121541. 30M, S 2022 B, enhancing the spectral efficiency of nonlinear frequency division multiplexing systems via subcarriers. J. Technol 40, 1860-716077. Org 10-1109, JLT 202-231888577. 31M, Bari L. S. 2023, Enhanced Achievable Information Rate for NFDM Systems using FBMC Wave Carriers. In Proceedings of the 49th European Conference on Optical Communications, ECOC, Glasgow, UK 1-5-2023. Org 10-1049202-32254. 32X, F, X Al 2022, a 20.48S over 1200 WDM transmission with nonlinear frequency division multiplexing. In Proceedings of the Asia Communications and Photonics Conference, ACP, Shenzhen, China 5-8-2022. 33X, Fang X, X Al 2023, ultra-high-speed NFDM transmission over G654E fiber with 103 probabilistic-shaped 64 QAM signals. In Proceedings of the Conference on Lasers and Electro-Optics CLEO, San, USA, 7-12 May 2023. Org 10-1364 CLEO SI 2023 SM3I1. 34S PJ S 2019, fast nonlinear Fourier transform algorithms using higher-order exponential integrators. IEEE Access 71451611451776. Org 101109, Access 201929454480. 35 SB DI is AL 2024, New Fast Exponential Splitting Schemes for Nonlinear Fourier Transform. In Proceedings of the 21st International Conference Laser Optics, ICLO, St. Petersburg, Russian Federation, 1-5 July 2024. Org 101109 ICLO 597022024106241005. 36X Fang X Yang F Al 2021b 6.4s 16x400s Nonlinear Frequency Division Multiplexing WDM Transmission over 640 SSMF. In Proceedings of the 26th Optoelectronics and Communications Conference, OECC, 3-7 July 2021. Org 101364 OECC 2021T5A4. 37X Fang X Yang F Al 2022b 10.83s over 800 Nonlinear Frequency Division Multiplexing WDM Transmission. J Technol 40 1653855394. Org 101109 JLT 20223177413. 38 Fang D A J Al 2021 Optical Arbitrary Waveform Measurement OAWM using Silicon Photonic Slicing Filters. J Technol 46 17051717. Org 101109 JLT 20213130764. 39 T A C Al 2022 200 G bead 16 QAM signals synthesized by an actively phase-stabilized optical arbitrary waveform generator, OAWG. In Proceedings of the Optical Fiber Communications Conference and Exhibition, OFC, San, USA, 6-10 Mar 2022. Org 101364 OFC 2022 M2I2. 40X Fang X Yang F Al 2021 C All Optical Synthesis of 100 PDM 16 QAM Nonlinear Frequency Division Multiplexing Signal. In Proceedings of the Asia Communications and Photonics Conference, ACP, Shanghai, China 24-27-2021. Org 101364 ACPC 2021T4D5. 41A O A Al 2023 Stitched WDM Nonlinear Frequency Division Multiplex Transmission System. Optics 546-129-809. Org 101016J2023129809. 420 A J Al 2023 A Full Spectrum WDM Nonlinear Frequency Division Multiplex Transmission System using Spectral Overlap. In Proceedings of the Advanced Photonics Congress, Republic of Korea 9-13 July 2023. Org 101364 SPPCOM 2023W3E3. 430 A J Al 2023 B Highly Scalable WDM Nonlinear Frequency Division Multiplex Transmission System using Spectral Overlap. In Proceedings of the Optical Fiber Communications Conference and Exhibition, OFC, San, USA, 5-9 Mar 2023. Org 101364 OFC 20231F4. 44 MS JN MAL 2020 Optic-Electronic Optic Interferometer, a first experimental demonstration. In Proceedings of the Conference on Lasers and Electro-Optics, CLEO, Washington, USA, 10-16 May 2020. Org 101364 CLEO SI 2020 SF1L1. 45 MS P MMH AL 2023 Coherent Add-Drop Multiplexing using an Optic-Electronic Optic Interferometer. In Proceedings of the Conference on Lasers and Electro-Optics CLEO, San, USA, 7-12 May 2023. Org 101364 CLEO SI 2023 SM2I6. 460 A J Al 2024b Add-Drop Multiplexing for Overlapped Nonlinear Frequency Division Multiplex Transmission Systems. In Proceedings of the Optical Fiber Communications Conference and Exhibition, OFC, San, USA, 24-28 Mar 2024. Org 101364 OFC 202 4W2A26. 470 A JAL 2024, a add-drop multiplexing for full-spectrum WDM and FDM transmission systems using spectral overlap. In Proceedings of the Advanced Photonics Congress, City, Canada, 28 July 1, 2024. Org 101364 SPPCOM 20241H2. 48 PJ 2013, an electronic interferometer and its use in subcarrier add-drop multiplexing. J Technol 30 1111775 1782. Org 101109 JLT 201322 57687. 49 VA OB 1972, exact theory of two-dimensional self-focusing and one-dimensional self-modulation of waves in nonlinear media. JXP 3416269 MathNet. 50 MX 2020, linear and nonlinear frequency division multiplexing. IAEE Trans, Theory 66 1478495. Org 101109 TIT 2019294147 MathNet. 51 JE, SA Blow KJ AL 2014, nonlinear inverse synthesis and eigenvalue division multiplexing in optical fiber channels. Rev 113013901. Org 101103, Rev 11301391. 52S 2017, generation of time-limited signals in the nonlinear Fourier domain via B modulation. In Proceedings of the 43rd European Conference on Optical Communication, ECOC, Gothenburg, Sweden, 1721 Sep 2017. Org 101109 ECOC 201783462231. 53X V ST AL 2019b, dual polarization nonlinear frequency division multiplex transmission with B modulation. J Technol 30 761570 1578. Org 101109 JLT 201929022961. 54S M O AL 2021, channel model and the achievable information rates of the optical nonlinear frequency division multiplex systems employing continuous B modulation. OptExpress 29 563846406. Org 101364 OE4 14885. 55I Safari M 2016, dispersion precompensation for NFT-based optical fiber communication systems. In Proceedings of the Conference on Lasers and Electro-Optics CLEO, San, USA, 5-10 June 2016. Org 101364 CLEO SI 2016 SM4F4. 56V 2018, fast inverse nonlinear Fourier transform. Rev E980-13304. Org 101103, Rev E980-13304 MathNet. 57JK Winter M, K 2009, scaling of nonlinear threshold with fiber type and channel spacing in WDM transmission systems. In Proceedings of the Optical Fiber Communications Conference, OFC, San, USA, 2226 Mar 2009. Org 101364 NFOEC 2009J A41. 58A JAL 2018, 8-channel WDM silicon photonics transceiver with SOA and semiconductor mode-locked laser. OptExpress 26192544625459. Org 101364 OA 26025446. 59R Wu GAL 2023, Electro-Optic Frequency Combs, Theory, Characteristics, and Applications. Laser Photonics Rev 1762-200353. Org 101002-202-200353. 60L E DPAL 2021, Silicon Photonics Phase and Intensity Modulators for Flat Frequency Comb Generation. Photonics Res 910-2068276. 61J V M AL 2014, Coherent Communications with Frequency Combs. Photonics 8375380. Org 101038201457. 62 SY Lee B. F. Al. 2021, Review of Silicon Photonics Technology and Platform Development. J. Technol 39 1343 744389. Org 101109, JLT 20213066203. 63 F. S. J. Al. 2013, Silicon Photonics Plasma Modulators with Advanced Transmission Line Design. OptExpress 2117 19593 19607. Org 101364 210199593. 64 SS J. F. Al. 2014, Advances in Silicon Photonics Segmented Electrode Mach Modulators and Peaking Enhanced Resonant Devices. In Proceedings of Photonics North 2014, Canada, 28-30 May 2014. Org 1011171220 65J 2018, High-Speed Silicon Photonics Modulators. Proc IAIE 106-12-2-1582-182. Org 101109, JPROC 20182-877636. 66J A GV Al 2021, Optimized hourglass-shaped resonators for efficient thermal tuning of Crow filters with reduced crosstalk. In Proceedings of the 17th International IEE Conference on Group IV Photonics, GFP, Malaga, Spain, 7-10-2021. 67 Yang Y Ma Y Guan H Al 2015, Phase Coherence Length in Silicon Photonic Platform. OptExpress 2313 16890 16902. Org 101364 OA 230 16890.